Good morning, Professor Lee.
Hey, good morning. Hi, Lakshmi. Good to see you.
How are you doing?
I'm doing well. A little bit sleepy.
Sorry for that. Yeah, because of the time difference. So I think we have about 10 minutes to start. Just, so you're in Boston now, or?
I'm at home now.
Oh, you're at
So,
home.
where are you now?
I'm in Delhi, only, IIT Delhi. So Cambridge campus. Yeah. So we are none of us are really traveling right now. More or less, everyone is cooped up in India. So, once I think things open up a little more after this Omicron variant probably goes away, I think then we can probably think of travel.
Yeah.
That is
We had MRS this week.
right. Right.
So this week, quite a number of visitors in person. So
Okay.
seems to be getting back to normal
Yeah.
here.
Yeah. Good. Good. I think yeah. We have about 10 minutes. I think then we can start.
Yeah, mine is 10:30 p.m.
Yours is 10:30 p.m.
Yeah, so
there,
we
right?
yeah, we are 10:30. Yeah.
Yeah.
I think we're just 10 minutes away.
Right. We are just 10 minutes. All right. So I think we can sort of kick off the day, I think, so that we have enough time to introduce Professor Julie, one of our hosts. So before that, welcome to everyone for the second day of this conference. And we will kick off today with a couple of keynote lectures, followed by about there will be two parallel sessions where we'll have several invited lectures as well as some of the contributed talks. So without further ado, since it's already 9 a.m. in India, I will introduce Professor Julie from MIT. So Professor Lee has held various faculty positions. He was at the Ohio State University, the University of Pennsylvania, and is presently a chair professor at MIT. And his group works on energy materials and systems. Professor Lee is the recipient of the 2005 Presidential Early Career Award for Scientists and Engineers, the 2006 Materials Research Society Outstanding Young Investigator Award, and the TR35 Award from Technological. Professor Lee was also elected Fellow of the American Physical Society in 2014 and is a Fellow of the Materials Research Society in 2017 and also a Fellow of the AAAS in 2020. And one of his his seminal contributions have also been recognized, and he now is he has in fact co-founded the MIT Energy Initiative Low Carbon Energy Center, the Center for Materials in Energy and Extreme Environment, and Professor Lee is also the chief organizer of MIT A+B Applied Energy Symposia, where he helps to develop solutions for global climate change challenges. So it is my personal privilege and honor to introduce Professor Lee, who will now take over and present his keynote lecture.
Thank you, Lakshmi. It's a great pleasure to be among friends and colleagues and give this early keynote session. Can you see my slides?
Yes, we can see that, Professor Lee.
Wonderful. So I will talk about batteries today, and there's quite a lot of mechanics in battery materials, especially when we use solid electrolyte and try to have this lithium metal as the anode, as I will explain. So I would like to first introduce the basic working mechanism of battery, which is very similar just to two water reservoirs, where the lithium chemical potential is analogous to the height of the water. And when we charge a battery, we are essentially moving these lithium atom from lithium cobalt oxide to the graphite electrode. The reason, however, that we can have electrical current is because intentionally people put two medium between the upper reservoir and the lower reservoir, so you cannot directly transfer lithium atom because in the electrolyte you only allow lithium ion, the lithium cation, and then the external metallic wire does not allow ions, but it can only allow electrons. So in this case, the lithium atom has to essentially split where the electron goes through carbon black and goes through this mixed ionic electronic conductor and eventually gets collected onto the metal wire and goes through the external circuit to do work or have work be done to the electron, whereas the lithium cation kind of have to swim through the electrolyte. And on the other side, they will have to do this charge transfer reaction again to be deposited as a lithium atom in the graphite anode. And the battery that we have now use liquid electrolyte. However, this is what it looks like. So it's made out of these organic solvents and with these lithium salts that's dissolved in these liquids. But as you can see, with liquid, you have a high vapor pressure, and also the cathode it actually have internal oxidants. So this is not very safe. And 10 years ago, there's work from Toyota that showed that with this solid lithium, germanium, phosphorus, and sulfide, you can get very high ionic conductivity for lithium, as high as this standard liquid electrolyte. And also because this have lower vapor pressure, it improves the safety. And also another actually benefit is that the solid electrolyte pretty much only allow lithium to move, and the anions and other ions basically cannot move in the electrolyte, and that prevents a lot of crosstalk between the anode and cathode. And also, when you use the solid electrolyte, you don't have to have the graphite anymore. And so you can directly electrodeposit pure lithium metal in the body center cubic structure. And this phase has a huge capacity, which is 10 times that of graphite. So you can get very high energy density by using the lithium metal. But it's well known that this lithium metal in the solid state battery context have three kind of big problems. One is a moving interface problem, because one is essentially depositing lithium metal, which is growing thicker and thicker. And so you have to maintain ionic contact between the solid electrolyte and the lithium metal, as well as electronic contact. That may sound easy, but as we're going to show, it's actually not straightforward. And so generally people put so-called stack pressure onto the solid electrolyte to have a big contact area and maintain adhesion. The second problem is also mechanical problem, is a fracture problem of the solid electrolyte. And basically, so imagine this area is the solid electrolyte, which can conduct lithium ion, and outside is the lithium metal, and you have a notch here, which is filled by the BCC phase, which conduct electrons. So the electron can go all the way to the notch tip, where it can meet a lithium ion and basically generate a lithium atom. However, that lithium atom requires space to accommodate. And each lithium atom requires 20 angstrom cube atomic volume. And so from the Nernst equation, we basically say that if you have a local overpotential of 135 millivolt, then you can actually work against 1 gigapascal of pressure, and that can create the volume to insert this extra lithium. But that kind of a pressure is quite dangerous, because this solid electrolyte very often is a ceramic, and so 1 gigapascal can very well crack the ceramic and further propagate this notch. And so what needs to happen is that you're going to generate this local pressure here to be able to keep plating atoms, but that pressure needs to be relaxed by plasticity or by creep. It's kind of like a Poiseuille flow of lithium metal to relieve the local pressure. So if you do not stress relieve quickly enough, then you will accumulate gigapascal kind of pressure, even with kind of a small overpotential, and that can have this electromechanical propagation of the crack. And lastly, there is a problem of chemical stability. So in fact, there is a stress corrosion cracking problem going on here, because a lot of the solid electrolyte actually is not even chemically stable against the lithium metal. So it is represented in this voltage window, but essentially this is the chemical potential of lithium atom. So 0 is a high chemical potential And we see that a lot of these oxides and nitrides, they are absolutely stable in contact with lithium metal, but not this LGPS material. Here, they actually are unstable against the lithium metal. They're also not stable against the cathode, but that's another story. And among the high conductivity solid electrolytes, this lithium lanthanum zirconate is relatively more stable. It's nearly stable against naked lithium metal, but that's only for the bulk. If it has grain boundaries, and the grain boundary may have a different grand potential stability window, and so in fact the grain boundary can be reduced at 0 volt and gradually becomes electronically conductive, and eventually it destroys this solid electrolyte, which is supposed to be an electron insulator and ion conductor. And just to show the mechanics feature, this is a cryo-TEM imaging done by Professor Mongu. And this is taken out of an ether-based liquid electrolyte after the lithium metal has been stripped away. And we see almost like this crumbled solid electrolyte husk. And so this I will show later is actually a cavitation problem. And it can generate stress that cause a big change in the surrounding solid support. And I want to put out a pretty provocative analogy here, which is to say that this solid state battery have this working fluid, which is this lithium metal, which is analogous to our internal combustion engine, which use a working fluid of air and gas, petroleum mixtures, right? So this is what drives the Industrial Revolution, but now we really need to replace this because of the CO2 problem. Now, obviously, it's a provocative idea because lithium metal should be a solid, but as I'm going to show you that even for high melting point solids like gold or silver, there is this kind of room temperature creep behavior, which make it kind of like a liquid-like. So 15 years ago, there was an experiment at UPenn where people made this mechanical break junction. So they just tear two gold pieces out apart. And initially in the TEM, it has take this profile. Then they take it out of the TEM and store it for 4 months. After 4 months, they re-image this tip again, and they found that it has shrunk, not by a lot, okay? but there is this room temperature diffusive creep going on. And later, we have collaborated with Northeast University in China, and I've shown that silver can actually do this. So when you have silver crystalline particles, they deform almost like a pseudoelastic manner, where they can recover their shape almost like a fluid. But what is interesting is that at any given moment, if you do electron diffraction, you still get FCC diffraction pattern. And we have also done this with tin. So this is room temperature deformation of tin, where the breakup look like a liquid meniscus. But as I said, if you do a diffraction at any given time, you have a single crystal. And we have done very high resolution imaging. This is at Xi'an Jiaotong University in collaboration with Professor Zhiwei Shan and Professor Evan Ma. When we look at this tin at very high resolution, we see this very gradual recovering of the profile. And we don't see kind of slip steps. So this recovery after this initial push doesn't seem to be by dislocations, but it seems to be a diffusive phenomenon. And generally, it is well known, that you have this smaller is stronger trend that for nanomaterials, as you reduce the size scale, the flow strength would harden where you have this exponent of minus about 1/2. But what we have found in 2013 is that there is a transition length scale below which your diffusive cobalt creep takes over, and it goes from smaller is stronger to smaller is much, much weaker. In fact, the strength goes as k to the d to the positive 1/3 power instead of minus 1/2 power. And based on this measurement in Ting, the transition length scale is about 100 nanometers, and Ting has a similar melting point as lithium. So it's actually a bit bigger than lithium. The homologous temperature is about 0.6. So this is the basis for us to ask the question, is this liquid-like cobalt creep, because once you are in this regime, you have an effective viscosity that drive this kind of liquid-like motion. Is that valid for lithium? And recently, there's also some very nice work on wire drawing when the substrate is heated to kind of 60–70% of the melting point. We see this kind of almost like Kroski, crystal growth, but it's not liquid. It's drawing single crystal wires that indicate this kind of diffusive behavior. And generally, we have this Frost-Ashby deformation mechanism map where horizontal axis is the homologous temperature, vertical axis is shear stress normalized by the shear modulus, and we have the low temperature, high strength, strain rate independent displaced plasticity. At high temperature, we have this diffusional creep, and then at intermediate temperature, we have the power law creep, where the strain rate is given by dislocation glide mostly, but it's rate controlled by diffusive processes. So what we're talking about is really something like 10⁻⁵ shear modulus and liquid-like behavior. So if you sort of just tolerate me for a second and pretend that lithium BCC is like a Newtonian fluid, or between Newtonian and non-Newtonian fluid, the next question is, to make a solid-state battery like an engine, what do you need to contain this fluid? Because this fluid is actually very corrosive in a reductive sense. And you also do generate a pressure in this fluid. And so what do you use to contain this fluid? And like I said, there are these good solid electrolytes. However, they are not really stable against lithium metal. And generally, we can classify solid by how well they conduct lithium ion versus how well they conduct electrons. So a solid electrolyte would be an lithium ion conductor, but is an electron insulator. Okay. Whereas metal is a good electron conductor, but they do not have a lithium ion inside, so they are not lithium ion conductors. But we also have two other quadrants, which are not often discussed. You can have so-called a mixed ionic electronic conductor, and these would conduct both electron as well as lithium plus. So you can also say that, if their transference number is comparable, they would also conduct lithium atom. They would have solubility of lithium atom. And then you also have a medium which conduct neither, which is electron and lithium ion insulator. So the observation is, while there are not many good solid electrolytes which are absolutely stable against lithium metal, there are many these mixed ionic electronic conductor, these mix, which are absolutely stable against lithium metal. So on the phase diagram, the way you determine absolute stability is to see whether there is a direct tie line between the phase and the lithium metal. So kind of like a direct flight to lithium metal. So for example, lithium nitride wouldn't be, because if you put it side by side, you would have these intermediate products, and depending on whether you have excess lithium or excess lithium nitride, you can work out the volume fractions. But you can put titanium nitride side by side with lithium, and lithium would not be able to rob titanium nitride of its nitrogen, as guaranteed by the phase diagram. And so, in fact, many end member phases of our aluminum or silicon, so these would be meek materials that would be very comfortable in naked contact with lithium, and there will not be any side reactions, a solid electrolyte interface, none of those things happening. And so my ex-postdoc, Yuming Chen, when he was working with Professor John Goodenough at UT Austin, he have developed this electrospinning approach where he can make these carbon hollow tubules, where you can have a tubule which is 100 nanometer across, but inside it's porous, inside it's empty, and the wall is about 10 nanometer. This carbonaceous wall. And so we put it in contact on the left with a solid electrolyte, and on the right with a current collector. And we are just putting a voltage bias between them. And we see this sloshing of lithium metal in the TEM. So this was done at MIT, and the key was that lithium is not a high Z metal, so you don't see very strong contrast, but you can see something is moving in this hollow tubule. This is fast forwarded for 100 cycles, both plating of lithium and stripping without a degradation of this hollow tubule. And what is very intriguing is when we do the electron diffraction, we only see one set of crystal peaks with the 110 direction aligned with the axial direction of the hollow tubule. And so it's actually a single crystal that is moving morphologically in the tubule. And when we strip it, we even see this crystallographic facet, as you could see here. You can see it moves with faceting. And when we look carefully, we can see the 110 lattice fringe of the body center cubic lithium phase. And people may question, okay, is this a electron beam artifact? So we have reduced the beam current, we have done blind experiment, we have tried everything we can. And in fact, if we have a lithium metal outside of the tubule, if we irradiate with this current for 2 minutes, we see this broad peak. So the lithium turns amorphous. But in the tubule, we can see the crystalline structure up for 20 minutes. So we think the encapsulation actually protects the lithium metal from amorphization. And in the first half cycle, this is basically a engine of lithium metal, but it's controlled by voltage. So when we reduce the voltage in the first half cycle, we actually lithiate the carbon hollow tubule walls. And then we start to deposit lithium metal with an overpotential that's on the order of 100 to 200 millivolt. And that's pretty significant because like we said before, from the Nernst equation, if you don't relieve the stress, that can generate gigapascal level of pressure inside. So based on this idea, we have scaled up this hollow tubule to this honeycomb structure, which is made out of this meek material. So this is not solid electrolyte. It only has a very small amount of contact with the solid electrolyte. So most of the lithium solid interface, most of the moving interface is with this absolutely stable meek material. And the benefit is you do not need to have a stack pressure, which most of the current commercial technologies need to maintain lithium metal to be in electronic and ionic contact. So we solved the first problem, which is the contact problem. And we also solved the second problem, which is we can use the creep to relieve the mechanical stress and to prevent the solid electrolyte from cracking. And lastly is that we believe we have now an architecture which can also greatly reduce the chemical corrosion problem, because in fact, we believe that when you strip the lithium metal, you first strip from the solid electrolyte side, so you really don't actually have a lot of lithium metal directly contact with the solid electrolyte. And by judicious engineering of the wetting of the lithium metal, so-called lithophilicity, as well as engineering the lithophilicity of the current collector, you can, we believe, induce the lithium metal to be nucleated preferentially initially away from the solid electrolyte. And then later lithium atoms would actually prefer to either move as an add atom on the surface and be coarsened directly away from the solid electrolyte, or even if they form this so-called beta phase, the BCC phase, this would generally be coarsened away and drained toward the current collector side. So this is an idealized architecture that we believe have a chance of working as the solid metal engine. So if we put in some numbers, so if you look at the modulus of the beta phase, the lithium BCC phase is a soft metal. The shear modulus is 3 gigapascal. And we are actually at 2/3 of the melting point. 300K is actually exactly 2/3 of the bulk melting point of BCC lithium metal. And so we are in the diffusional creep regime way below an atmosphere of pressure, okay? So that is feasible. However, if you look at the strain rate, it's 10 to the minus 10 per second. And that obviously is too slow to drive a battery. But what is really interesting was that this was for traditional coarse grain nickel, where the grain size is 100 micron. But now, if by the magic of this nanoporous meek honeycomb, we can reduce the size scale from 100 micron, 0.1 millimeter, to 0.1 micron, which is 100 nanometer. We can reduce the size scale by 3 decades. Then by the Kobo creep formula, we will get 9 orders of magnitude boost in the strain rate. So the prediction is with less than 1 atmosphere of pressure, if you're in the pure diffusive creep, you can actually get 10 to the minus 1 per second kind of strain rate. And that will be completely serviceable in typical kind of battery cycling. And we also have to entertain the possibility that we could move into the power law creep regime, where you may have some dislocation activity and some stress. Okay, so we could be operating in this kind of regions, generally depending on what kind of rate you're trying to drive the battery. So we can consider both diffusive cobalt creep along this red meek, which is about 10 nanometers, so that'd be the carbonaceous wall. Or we could have this interfacial diffusion between the meek and the BCC phase, which is generally an incoherent interface, which is only 2 angstrom in thickness. Or we could have a bulk lithium diffusion through the beta phase, so that's Nabarro-Herring creep, through the lithium metal. Or we could have dislocation power law creep in the lithium metal. So generally, we would have all these 3 or 4 deformation mechanism operating. But we found that at least under certain conditions, you do not have to have the power law creep. And this is because in this stripping experiment, the solid electrolyte is on the left. So in fact, what we are seeing in this faceted strip is we're seeing lithium atoms actually leaving the material completely through either the meek ore or through surface diffusion. And you do not need to have displacive motion of lithium metal. And that also is verified because actually this meek ore have internal barriers, and we can see the lithium metal kind of can climb over these barriers with no apparent dislocation motion. So when we put in the numbers, I would not bore you with the details. Of course, we do not know the precise numbers of lithium diffusivity in the meek. We can only kind of estimate them. And we also do not know precisely this interfacial diffusivity. We approximate them by surface diffusivity. Now, the surface diffusivity, there is a scaling formula which was pretty well validated by previous experiments that Campanano have done. So this is pretty well validated formula. And the general sort of conclusion is that the effective diffusivity is that of the bulk diffusivity of the meek multiplied by this ratio of diffusivities and this geometric factor. But as it turns out, that regardless of whether it is this kind of meek materials or even these metallic meek material where you have to rely on the interface for diffusion, generally this 2 angstrom incoherent interface would actually contribute more at room temperature than through the bulk of the meek itself. And that's a very good simplification because it basically liberates the choice of materials for this meek material. And there are also some battery requirements because generally, to make a reasonable anode, we need a certain capacity for the battery. So 3 milliampere hour per centimeter squared anode capacity is generally what's required. And that basically requires 15 micron of fully dense lithium. And so this meek honeycomb, because we also have dead space occupied by the meek, needs to be about 20 micron in thickness, in H. And in terms of the rate capability, if we want to have 1C charging, discharging, then the effective current density will be 3 milliampere per centimeter squared. And that would also put a requirement on the effective conductivity, which is related to this effective diffusivity that I just computed. And the general conclusion is yes. So we can pretty much accommodate 1C or a half C charging with cobalt creep, maybe with a little bit of a power law creep if push come to shove. So there is also a problem of interfacial contact. So there is this concern of how to fix this MIC channel into the solid electrolyte. So imagine that we have this naked contact between the red MIC and the green solid electrolyte. Because the green solid electrolyte can transport lithium ion, and this MIC can transport electron. So you will be able to have lithium atom here. And that lithium atom may be able to have a heterogeneous nucleation and nucleate this silverish BCC phase. And you can actually have a wedge crack that basically jack up the interface between the green and the red. Now, once that have happened, because the BCC is really, really soft, then it'd be really easy to pull out this MIC pillar from the solid electrolyte. So philosophically, there is actually a big problem of directly fixing this MIC solid into the solid electrolyte. So our solution is to use, in addition to the metal solid electrolyte mixed ionic electronic conductor, we also use this electron and lithium ion insulator, which conduct neither lithium ion or electron, and just use it as an inert mechanical binder so that it has a strong purple-red interface and a strong purple-green interface. And the idea is that even if you say you have this overhand situation where the solid electrolyte is a bit taller than where this ELI is, because in real processing, you can never guarantee it to be exactly right at this level. And even if you have this electron coming down and lithium coming up to here, and you have already nucleated a lithium BCC phase, and that phase would wedge all the way to the ELI. But because we have a strong lithophobicity between the ELI and the lithium metal, and this wedge crack would stop at this point, and it will not further propagate and grow around the ELI. So we have actually performed material genomic searches of which ceramic compounds are electron insulators, so they need to have a big electronic band gap above, let's say, 3 electron volt. And also, we're looking for ceramic compounds which do not have any lithium solubility, so they will not be able to conduct lithium. And also, they're absolutely stable in contact with lithium metal. For example, beryllium oxide, if you put it side by side with lithium metal, this lithium will not able to rob beryllium oxide of its oxygen. They would be completely peaceful in contact with each other. And so the general idea is, generally, like a high voltage electrical grid is made out of, aluminum or copper wires and, steel grids, but you do need these dielectric insulator ceramics to have an electrical grid. So the same story is you do need to have these ELIs to fix the MIC with a solid electrolyte. And in the cases where there is an underhand where the solid electrolyte is lower than the MIC, then you need a spark, or you need some kind of asperity to start the nucleation of the lithium metal. And as long as you have some residual lithium metal in the system, you can keep cycling this engine. So based on this paradigm, we have scaled up the material. We have tried many different things, anodized aluminum and silicon mesh. The silicon mesh didn't work out very well because, first of all, it's not a nanoporous material. And secondly, upon lithiation, it kind of fractures. But eventually, we're able to develop this carbonaceous MIC material, which is many centimeter by centimeter in area and tens of nanometer in depth. And that is actually pretty amazing because the aspect ratio of this channel is 200. So it's very longish channel. And we have also developed inorganic MIG channels. And we have made them into solid state batteries without any liquid, without any stack pressure, and we can cycle them. This is in collaboration with Samsung for 200 cycles with a very significant area capacity. And we can maintain constant electronic ionic contact, and we can relieve the stress and basically defeat this crack-based degradation mechanism. There is no stress corrosion cracking, no SEI, because the MIG core is absolutely thermodynamically stable with SEI. And in addition to lithium metal, we have also pumped up and down sodium metal as well. So in the last 2 minutes, I would like to just talk about one peculiar feature, which is called the cavitation damage. Because most people, when they study lithium metal, they focus on the dendritic growth, where you are depositing lithium metal and the lithium metal have a net pressure. But it turns out that when you have a fluid, what is more damaging is if the fluid is under a negative pressure, which is tension. And this, in the case of engines, so if you just search for cavitation damage in turbines and pumps, you have these fluid metal interactions because you're going to have cavities, and when these cavities collapse, you can damage the metal. Similarly, in trees, to pump up the sap, you need a negative pressure. And in fact, in this redwood tree, the negative pressure is very big, like 10 megapascal, to be able to pump the water up by 100 meters. It's very high, very tall trees. And trees are amazingly robust against cavitation damage. So what this is showing is a lot of trees, there are like 30 different trees, where they can sustain 5 to 10 megapascal of tension before they suffer cavitation and 50% loss in the water conductance in the xylem of the tree. And by that time, the tree probably would die at that point. So just like I mentioned, if you apply 1 millivolt in stripping instead of 7.4 megapascal of compression, you're going to get tension. And so the question is whether you're going to have lithium metal cavities in the bulk or in the lithium metal solid contact. And our hypothesis is actually that it is well known that regardless of whether it's liquid electrolyte or solid electrolyte, having a few megapascal of net external compression is generally very beneficial for cycle life. And our hypothesis is that this is to prevent cavitation damage in the solid structures inside. And so that regardless of the Nernst equation, you can prevent this kind of cavitation damage. And generally, if you look at water bulk can sustain negative 20 megapascal of tension without bubbles. And because lithium metal is about 5 times stiffer than liquid water, then the bulk lithium may be able to sustain 100 megapascal of tension in the bulk. But the key question is whether if we have this MIG nanostructure, whether the surrounding solid can take that. And we really don't know the precise pressure inside, but even just based on the surface tension, because we do know the surface tension of BCC metal with vacuum, then just using this Young Laplace pressure 2 times the surface tension divided by the radius of curvature, if we have 100 nanometer nanopore, then the tension inside would already be about 20 megapascal. And so recently, in collaboration with Professor Huolin Xin, we found that indeed, when we are doing stripping, when the thickness of this solid supporting structure to the diameter, when it is above a certain ratio, we have no cavitation damage. But when it is smaller than a certain ratio, then we see damage of this supporting solid lithium oxide. And so actually from this, we can estimate the cavitation, the true strength of this pressure vessel is about 300 megapascal. So this is my last slide, and it is basically to say that we are now developing this, lithium metal room temperature nano engine with open porous mixed ionic electronic conductor channels, trillions of them, gazillions of them, and also with this Eli binders with the current collector and the solid electrolyte. And the goal, kind of ironically, is to defeat the original internal combustion engine, so we can remove CO2 from the globe. So with that, I'd like to stop and see if I have any questions.
Thank you very much, Professor Lee. That was indeed a very nice talk and has a lot of perspective for the future. So I have two questions. One is by Professor Praveen Kumar from Indian Institute of Science. And he has a question where he is asking that in the pseudo-elastic / liquid-like behavior of tin at room temperature, how many grains do you have in these particles? Or can we approximate D, capital D, as the size of particles?
Yeah, in this case, I believe this region is a single crystal actually. So the D is indeed the sample size, not the grain size.
Okay. And if there were nanograins, how would they behave? I mean,
well, yeah, in that case, then we should use the grain size. Yeah.
Okay. I have another follow-up question. It's a sort of a more generic question as to if you are doing this. These are all room temperature tests, I suppose, right? I mean, more or less.
Right.
So
everything is room temperature, yes.
Right. If we are going to look at, let's say, batteries for space applications as such, so the conditions that are there, we are also going to look at things like cryogenic temperatures and so on, right? Or maybe even higher temperatures. So how do you really look at the behavior of these materials at different temperatures? Or is that not?
That's a fantastic question. Yeah. So in fact, if this is room temperature, then this would be, I think, outer space temperature, and then we have already guidance provided by us by metallurgy. So you would need a significant higher stress, but in fact, this is still only less than 1 megapascal. Okay, so I think this is as long as the supporting ceramic have that nano open porous structure, this honeycomb can take that kind of a pressure difference, then we can still cycle the engine. Okay. You would have some displacement. You may even have some kind of sliding. So it's no longer just the plating and stripping. You would actually have some interfacial sliding, and there might be some damage. But the hope is it's not so high to damage the surrounding ceramic.
Okay. That's a fantastic question. So there is another question by Professor Varla, and he's saying, what about these battery materials performance in an environment where the temperature is continuously fluctuating? If you have a lot of fluctuation.
So I think, so we can see indeed, the stress that's required to maintain a certain strain rate on this iso strain rate contour. It's going to have this kind of variation. And so indeed, the supporting solid structure, even though, that's why we think if you just make graphene, it's not going to work. It has to have certain wall thickness. That's why we think, this kind of, as it turns out, this kind of carbon hollow tubule have the right mechanical properties to be able to take that kind of stress fluctuations, and in both, regardless of whether the lithium is in compression or in tension, this tubule can take it. Okay.
If I can I'll just wrap it up with one final question as to what are the real future perspectives, and what do you think is going to really happen in terms of development of these lithium ion, because I think everyone is concerned about, let's say, especially the people who are developing EVs and all, especially in India also, you see that a lot of focus is there on developing vehicles that use these batteries. So what kind of opportunities are there where it can really replace conventional carbon fuel?
Yeah, so there's a lot of processing challenges. It's actually not cheap to make this kind of open porous structures. But I would say that right now, I think that even the fundamental philosophy of how to build, this solid structure to contain this very corrosive and stressful lithium metal, I think that is still sort of being debated. And I think there's really a lot of traditional metallurgy and the mechanical insight. This is fatigue and fracture of these nanostructures and size-dependent mechanical behavior that can come into play. And I think people in this conference can really, I think, contribute a great deal to this field.
Right. Thank you so much, Professor Lee. Thank you again for your time and excellent talk. We wish you a lot of luck again, and thank you for honoring our conference with your really exciting talk on lithium-ion batteries, and I hope everybody will be inspired. Without further delay, I will thank you, and you can stop sharing the screen. And if there are any more questions, I would request the participants to, if Professor Lee is fine with that, email any questions if they have, because in the interest of time, we need to move to the next speaker. I think we are already, I think it's 9:50, so we have the next speaker also in the room. And so I will just introduce him, and it's a great pleasure for me to introduce Professor Upadrasta Ramamurthy. He is my PhD supervisor, so it makes it more sweeter for me to introduce him because such an opportunity really does not come often, and I'm very happy to have him here. And so a brief description of his profile. After obtaining a PhD degree from Brown University, and he had a couple of postdoctoral stints at UCSB and MIT. He has held faculty positions at NTU as well as Indian Institute of Science before again returning to NTU in 2018, where he holds the President's Chair from the position. He has published more than about 300 papers and has a very high H index of close to 67 on and 62 on Web of Science. He is also the editor of Acta Materialia and Scripta Materialia, and is a fellow of several societies and academies, especially the National Academy of Sciences and Engineering of India. For example, some of them such as INSA, INA, and he is also the fellow of the World Academy of Sciences. He is a recipient of the National Metallurgist Day Award, the coveted and the prestigious Shanti Swarup Bhatnagar, as well as the J.C. Bose Fellowship. He is also an honorary professor at various departments, and with that, I would like to, the list goes on and on. So I would like to stop here and introduce his topic, and he's going to give a talk on the structural integrity of 3D printed metals and alloys. So without further ado, Professor Ramamurthy, I request you to go ahead and present your talk. Thank you.
Sir, please unmute.
Okay. Thank you very much. Good morning, everybody. You can hear me now. Can you see my slide?
Yes, we can see.
Okay, great. Thank you, Lakshmi Narayan, for that introduction. Thank you very much, Kiran, for the invitation. I'm glad to be able to participate in this conference, which seems to have a stellar cast of speakers, and I hope there are many interesting talks, and I hope many people are benefiting from it. Okay, so I'm coming to you from Bangalore. I've been here for a long time, and in a couple of days I'll be traveling back to Singapore. Okay, so for past now nearly a decade, we have been interested in mechanical properties of 3D printed metals and alloys. So this work that I'm going to present is actually work done by two of my students, Jyoti Suryavanshi and Puneet Kumar. And so I will present that work. So given the diverse nature of the attendees, I thought first I will just introduce you. So we are going to only focus on metal 3D printing. Which is technically called additive manufacturing. 3D printing is a technical name, because you are essentially layer-wise adding, bottoms-up fabrication of metallic parts. You are doing that. The raw material most of the times is in the form of powder or wire, and you need to melt it, and so you need a heat source. So laser or electron beams are used most often, and the material is deposited. I'll just give you some more details as we go along. So one of the key advantages of 3D printing, especially in the context of metals, is you're able to construct or build, fabricate 3D complex parts in one go. So imagine if you have to sort of make a component like this. In conventional manufacturing would mean you have to cast, forge, and then machine, and maybe even weld. So that is one of the advantages of 3D printing. You basically just make this part straight away. Okay. The other thing that is particularly advantageous is because you can make such complicated parts, you can also optimize design. So which is not really always accessible for conventional manufacturing. So the design optimization and manufacturing go hand in hand in the context of 3D printing. Whereas in the context of conventional manufacturing, metallurgist lives in her space, and then mechanical design engineers live in their space. Here they talk to each other directly, continuously. Now, there are a variety of 3D printing techniques. Two of them are listed here. One is powder bed fusion. So what you do is basically you spread the powder in a bed, and then with a predetermined layer thickness, and then you take either a electron beam or a laser. This is sometimes also called selective laser melting. So what happens is you take a beam and melt wherever you want to the powders to be fused. So the remaining parts, the powders are loose, and you can take them out afterwards. There is another technique called laser directed energy deposition, or DED. Okay. So in the powder bed fusion, just or same thing with electron beam. Instead of laser, you use E-beam in that context. So the inputs are, you have a 3D CAD model of the component that you want to build, say something like this. And as I said, metal powder. So you spread the powder, you hit it wherever you want to powder to fuse, you hit it with a laser or a electron beam. And then what you do is you lower the platform and spread another layer of powder and come back again with the laser and hit it. Okay, and so that you get the final product in one go. Okay, in the case of electron beam melting, what happens is instead of using a laser beam, you use a E-beam. Okay, and the thing is, in the laser case, you raster the laser. Here, you basically just use the lenses to do this. And the other thing that we do here is generally heat the whole container, so residual stresses are low. Especially printing of high temperature materials like Inconel 718 is more easier here. Now, this is also typically done in vacuum, so the contamination, etc., are not much. Now, there is this directed energy deposition technique I mentioned to you. So what happens is you feed powders, and then you essentially, as they are in their flight, you essentially heat them with a laser beam. So you are essentially, so they melt and you deposit that. You are illustrated here. Okay. So, so materials are fused using focused thermal energy as they are being deposited. So otherwise, the technique is similar to that of the thing. So each of these techniques, laser beam or E-beam or DED, they have certain advantages in terms of residual stresses, resolution, ease of setting up, ease of usage, build rate, product cleanliness, geometrical complexity, and materials library. And so you have to pick and choose depending on your kind of application and how costly you want to make it to be. Now, there is one more technique which is called binder jetting. Okay, here it's completely different principle as far as how the metal powders are fused. So what you do is you spread the powder just as in the SLM, selective laser melting. But here, what you do is you take some polymer and you bind it at regions where you want it to be bound. Okay, so you end up with a green part, and then you take that green part, which is somewhat fragile, and then you burn out the binder and then sinter it. Okay, so this is a binder jet printing, and there are desktop metal. HP is particularly Hewlett Packard, which is a giant in 2D printing, is pretty keen on this. They're developing their own 3D printers. So here you are essentially sintering. So what you get is a sintered part, and but it's relatively cheap, and you can have a high throughput fabrication. Now, there are lots of advantages of 3D printing, basically, from a manufacturing point of view. Okay, one of them I already told you that you can build complex parts, so you can optimize them. The other thing is it's flexible manufacturing. You can change the kind of component, the kind of alloy that you want to print, etc., very easily. And that gives you the ability to print on demand. Whenever you need the component, you can print it. You don't need to print and keep the components ready like we do in conventional manufacturing. It's digital manufacturing. That's why people are excited about it. And you get new near-net shaped final products with one manufacturing step. That's a particular advantage. If you think of conventionally manufactured components, there may be several tens of steps sometimes before you see the final product. This leads you to very high usage of the raw material. So if you think raw material is powder, so if you buy 100 kilos of powder, your final part could also be 100 kilos. So this is what we term as buy to fly ratio. So you can get very good usage of your raw material. You can enhance the functionality by lightweighting, conformal cooling channels for heat transfer, efficient heat transfer, and so on and so forth. Actually, these techniques have come up, more now. They are in the realm of manufacturing, but they all have originated in rapid prototyping. So, if you have a new design concept and you want to check it out, you can actually quickly build the part using this, however complex the part may be, and then test it. This is what rapid prototyping means. So all that means reduce lead time. So instead of years, if you have a new design concept, you can check it and take it to market in a couple of months. Now, and some processing costs are sometimes cheaper too. The machines are costly, but maybe with the scaling up, they will economies of scale will bring them down. Now, so there are some key questions with respect to 3D printed parts. First one is benchmarking. Okay, so if you have an existing component which is already optimized in service, everybody is comfortable with it. So you say, oh, I'm making this 3D printed part. First question everybody will ask is, how good or bad are these parts compared to the conventional manufactured components? So in particular, so this is the proof is in the pudding. Now, the thing is, a lot of people do testing for quasi-static properties, but the key thing, as I will show you later, is fatigue. Okay. So that is where certification, etc., come into play. Then, as I already showed you, there are several different 3D printing technologies, even in the context of metals, and which one is the best option. Okay. So in terms of mechanical properties, in terms of cost, remember we are talking about manufacturing, so cost is primordial in that context. Now, we often take powders. So these are powder metallurgy components. Powder metallurgy components obviously means they have porosity. So porosity immediately affects the structural integrity of the component. So structural integrity means fatigue and fracture properties. So eliminating the porosity altogether is rather a challenge. It's probably very costly. So we have to live with porosity. So how much of porosity can we live with? That is another question. Then 3D printing is a different manufacturing process. You are rapidly melting and cooling the alloy, solidifying the alloy. So it gives you options for microstructural design. So this is another the thing. Okay. So there are several opportunities for materials engineering. There is, of course, mechanical engineering aspects as well, but materials engineering with 3D printing. A lot of people are focused on this process optimization and benchmarking that I alluded to you earlier. What I will try to show you in my talk is that you can actually also get interesting combinations of properties. So a lot of the talk that I'm going to give you, and a lot more, is in this review that just came about. So fatigue and fracture in additively manufactured metals that we wrote with, I wrote with Puneet and Thorsten. Now, so if you look at these 3D printing technologies, especially laser beam or E-beam or even DED, what happens is you're essentially taking a laser, for example, and scanning one line at a time, right? And these lines overlap. So then you build one layer, and then you go on building layer after layer. So if you sort of decouple everything and look at the very basic thing, you are doing a line by line, layer by layer manufacturing of the components. So this particular processing gives you imparts a mesostructure to the build piece, okay, which is not there in the conventionally manufactured material. Okay, so for example, the one kind of illustration is here. So scan direction, this is transverse direction, and you're building a component in this direction, build direction, right? So for example, let's say you scan the nth layer like this, n plus one layer, you can do rotation by 90 degrees, you can rotate at some other degree, 63, 71, whatever you choose. Or you can also have this checkerboard kind of scanning strategy. Okay. Now, if you do that kind of scannings, right, in addition to conventional microstructure, you know, these alloys have microstructures, but you also get a mesostructure that is illustrated with this nice micrograph that Jyoti got some time back. Okay, so you see, let me illustrate. This is for aluminum 12% silicon alloy. Okay, so you see here these overlapping hatches. So each is a line. Okay, they need to overlap, and that's how you get this. And then there is a 73-degree scan rotation between successive layers. Okay, that's why it looks a little complicated. But you do have fairly complex mesostructure. One, you know, it's just I want to differentiate with respect to microstructure. That's why I call it a mesostructure, which is imparted by how you build the component, what kind of processing scanning strategies you used. Okay, you know, you can have a single melt, or which have different rotations, or you can have a checkerboard style. Okay, now what consequences will you have if you do build, if you have a mesostructure, because which is an inherent attribute of this processing strategy that you employ. So let me illustrate that with aluminum silicon that the mesostructure I showed you, right? These are the tensile properties of this tensile stress strain responses. We test in 2 different orientations, and the properties that we get from that are here. Okay, so I mentioned to you about benchmarking, right? This is same alloy if we do cast it, and that is a widely used aluminum silicon alloys are widely used cast in the casting conditions. So the yield strength is about 100 MPa and the UTS is about 200 MPa, and you get reasonable ductility, 9%. So these are all the 3D printed alloys. You see that the yield strength goes up quite substantially, actually more than 100% improvement. UTS is not so much, okay. But the thing is, ductility tanks, right? Ductility is really very poor, and if you were to take this to a mechanical design engineer, he immediately will say, look, this material is no good because it's very brittle. Ductility is very low. Okay. Now, okay, so what are the reasons why we get such a substantial strength enhancement? One of the reasons why is that there is a microstructural refinement. Okay, so at any given instance, what you are doing is you are taking a laser beam or a E-beam or whatever, you are melting a very small volume of material, which is sitting on a huge heat chamber, right? A heat sink rather. So what happens is you melt it and it instantaneously solidifies. So you have rapid solidification situation. So rapid solidification immediately means you have substantial microstructural refinement as well as enhanced solid solution. And so as a result, you get solid solution hardening. And that is the reason you get this very high yield strength. Okay. Now, we all know, at least metallurgists know, that if you increase the tensile strength, the toughness comes down. Okay, this is the conflict between strength and toughness that Rob Ritchie wrote some years back, actually a decade back. Okay, so when you increase the strength, as you see this line, the toughness comes down, and you want both these properties. So what we try to do is push this envelope this way. Okay, and what I'm going to show you is that this mesostructure in the SLN components actually does that. Okay, so when we tested the fracture toughness of this aluminum silicon 3D printed alloy, what we found is that we were expecting, because the strength has gone up quite substantially, the fracture toughness should come down. And if you go back to this, right, if you look at the ductilities are very low. So immediately we would think that the fracture toughness should be very, very low. So the as cast alloy 11 MPa root meters. So we were expecting it to be 2 MPa root meters or whatever, the 3D printed aluminum silicon. Lo and behold, we got the opposite. Actually, you see the fracture toughness values are now anisotropic, and more importantly, they are almost 3 to 4 times more than the as cast alloy. So the expectation was that they will be 1/3 or 1/4. Whereas actually the fracture toughnesses are now 3 to 4 times. So that is the surprising result, right? The reason that happens is, this is the front view of this 3D printed thing. So you have these hatches, right? Each of these, so for example, if you take, that is a one scan line, okay? So they're overlapping. So what happens is when these hatch lines are decorated with silicon rich. Silicon is brittle, okay? So silicon rich phase. So what happens is when a crack comes here, this is a brittle thing. So it essentially thinks it's a easier path. So it diverges here. But then once it comes it has to climb up, right? So its mode 1 crack driving force decreases dramatically. So let me give you an analogy here. So if you are running or bicycling in particular on a parallel road, right, on a flat road, it's much less of a strenuous exercise. On the other hand, imagine you're bicycling on this kind of a terrain. Okay, so you're going here, going like that, right? So going down is easy, but coming up is very, very difficult, right? So that is the same thing that the cracks experience. And in fact, it is not just two-dimensional. It's because we have rotate the scans by 73 degrees, etc. So there is a three-dimensional tortuosity to the crack path. As a result, what happens is the cracks get deflected substantially. So you can see that from these fractographic images. You see how cracks deflect. You can see how much deflection happens, and as a result of that, the toughness goes up, because once the crack is deflected, its crack driving force decreases. So you need to apply much higher far field stress to keep it going, and as a result, you get this high toughness. Okay, so what you are able to get is in this 3D printed aluminum silicon. You not only, conventional alloy is here, right? You not only get high yield strength, that is because of the microstructural refinement, as well as enhanced solid solution strengthening. You also get enhanced toughness, that is mesostructural result of the mesostructure you have. Okay, so we have also tested these mesostructures also impart the resistance curve behavior, R curve behavior. So you have very nicely working out solution here. Now, so you are able to push both toughness and yield strength. Now, is this one of the questions that people can ask is this still good? Can I use this material? Because remember, ductility is very poor. Now, this is where I would like to argue that why do you need ductility? See, if you are a conventional metallurgist, we do pay a lot of attention to ductility, okay? Because of two reasons. One is typically you do casting and then you do rolling, forging, extrusion, etc., right? And all those mechanical operations, will not be possible if you don't have ductility. Right, so we do deform, cold work, and then anneal it to get recrystallization, and do cold work again, or whatever. Right. So if you don't have ductility, you will have cracking. It's useless. So in this context, in the 3D printed metal context, you are getting the final part directly. Right. So then why do you need ductility? From that perspective, you're not doing secondary mechanical operations anymore. Okay. So that is one. The second reason is ductility is, if you take steels, for example, the higher the ductility, higher is the toughness. So in fact, we say ductile to brittle transition, not tough to brittle transition, because ductility and toughness are synonyms as far as we understand. But here, we are able to derive the toughness from a different perspective, right, with the mesostructures. So it doesn't matter if the ductility is low, but our fraction toughnesses and R curve behavior are very good. So that way, this material is good. We can go ahead and use it for designing. Okay. Now, just let me give you an idea how we engineer the mesostructures. So this is for Ti6-4, titanium 6 aluminum 4 vanadium, which is a workhorse titanium alloy. And it gives you a wide range of microstructural choices. Now, if I take this Ti6-4 and print it using these kinds of parameters, okay? So the layer thickness is 30 microns. So each layer is only 30 microns. And the scan, the beam spacing is 140 microns. And the scan rotation is 90 degrees. That means if you rotate, if you scan in this direction, one layer, next layer you rotate by 90 degrees. It's perpendicular to it. Okay, and you keep building it. Now, what happens when you have 30 microns is, if you look at the top view, you get this pretty square, nice grains, right? Now, you can't get this kind of grains in conventionally manufactured, the square, perfectly square grains. Okay, and if you look from the side, these are actually very columnar. Okay? And you also have this alpha prime lattice, these martensitic phases, because you are rapidly cooling it. Okay, now this happens because the layer thickness is only 30 microns. So what happens is, the one that you deposited before, the grains in that act as seeds and they keep growing. Okay, that's why you have these columnar grains, and a lot of people are worried that you may have significant anisotropy properties. Okay, so what if you rotate it by, in the previous instance, it was 90 degrees. If you rotate it by 67 degrees, the other two parameters are kept constant. Okay, what happens is now you see that you broke away from that square thing. It's approximately the grain size is 140, but more equiaxed. In this also you broke away the columnar nature, but the grains are still aligned along the build direction. Okay, now from this layer thickness of 30 microns, I go to 60 microns. Okay, so this is 60, 90. That means I go back to 90-degree rotation, but 60 microns. Okay, so I increase. So what happens is I go back, because it's a 0, 90. I go back to the square grains, but now because the layer thickness is much larger, there is no overlap. Okay, so as a result, in this side I don't get in these columnar grains. The grains are broken up. Now, if eventually I go to 60 microns and 67 degree scanning rotation, I get equiax structure on either side. So, what it illustrates me is by changing these parameters, right, layer thickness and scan rotation, I can actually kind of change the kind of mesostructure that I get. Okay. Now, Puneet looked at the properties, a whole host of them, the tensile properties, fracture toughness values, fatigue crack growth threshold values, and fatigue crack Paris exponents, and fatigue strength of these materials. Okay, so the tensile properties are much higher than conventionally manufactured Ti-6-4. Ductility are okay. The fracture toughness values, you see, it's about 50 MPa meters. Okay, but the fatigue strength is not very good. The fatigue strength to ultimate tensile strength ratio, which should be around 0.5, is only 0.28 to 0.41. Okay. All right, and the strength enhancement in this case comes about because you have rapidly solidified and you have a martensitic microstructure that is illustrated here. Okay, and the ductility we got compared to other reported literature is because we have equiaxed grains, which we engineered by changing the scanning parameters. Now, this metastable alpha prime is not very, Ti-6-4, you can use it for high temperature applications, and some people may not like to have such metastable microstructures in, microstructural features. So we thought we will heat treat to see if we can give up a bit of strength to get better ductility and toughness and get rid of this alpha prime. So we did these are the rotating bending fatigue test results, by the way. Okay, so conventional manufactured alloy is here, and our alloys are here. So you see these cases, it's quite poor compared to that. So this would be a limiting factor in terms of applications, and we need to ponder how best we can push this. And we thought first we can try to do heat treatment. By the way, just sorry, before I jump. See, the poor fatigue resistance is always because of porosity. There is a pore that initiated the crack, fatigue crack, and fractured, and you always have such pores initiating. That's why you get low fatigue strength. Okay, and in fact, Puneet went and did X-ray tomography, and these pores are also organized, and they depend as well on the processing conditions used. In 3090 case, for example, you see all the pores are aligned with the characteristic spacing, whereas in 3067, when the rotation between successive layers is 67 degrees, they are randomized. Okay. Same thing with 6090, you see there are all pores are aligned. 6067, the pores are randomly distributed. Okay, and we went ahead and did a lots of characterization about the shape of the pores, size of the pores, how much acicular sphericity they have, etc. Okay, and the reason, let me just go back here. If you look at, right, these 3067 and 3090, for example, they have very poor fatigue strength. And the reason they have very poor fatigue strength is this, compared to 6067, is that you have, this is cumulative probability as a function of equivalent diameter of the pore. right? So if there is some critical pore diameter that you identified, so in the 3090 case, the red, you have much higher probability of finding a large enough pore in this case compared to the 6067 case. Okay, this is all fracture mechanics based approaches we used. Okay, so we wanted to see if we can push, we can improve the fatigue response by and fracture toughness response by increasing, the toughness of the material, etc. So we explored different heat treatment options, some of them above so-called beta trances of the thing, and some of them are below beta trances, and one step and two play heat treatments, etc. Okay, and we get a lot of different kinds of microstructures. Due to paucity of time, I will not go. So in some cases, you have significant coarsening. In some cases, you have this alpha, that primary, grain boundary alpha that forms, which is again not desirable. So we picked one of those heat treatment schedules below beta trances, duple heat treatment, and picked that up. And then this is the one which we chose. And then heat treated. So we wanted to still retain the mesostructure that we have, and we feel that it's not really causing a lot of problem, and we want to keep that. Okay, these are all the microstructures. Sorry, I am just flashing, but you can get a lot of colorful microstructures now. This, with EBSD, and so this is the kind of things one can go and look at them very carefully. A lot of stuff. Okay, now this is more important. Okay, so here is a very busy table, lots of data, but it's the same sort of data that I showed you earlier on, but after heat treatment. Okay, so now what these there are red and green, right, or blue, red and blue, sorry. So red means the property change from before heat treatment to after heat treatment. After heat treatment, how much of the property change? So if you look at it, right, so the yield strength came down by about 20%, anywhere between 11 and 20%. Okay, so slight reduction in yield tensile strength. So that is something that we can afford to give, because these yield strengths are still higher compared to conventionally manufactured alloys. You get substantial enhancement in ductility. Look at the fracture toughness values. We nearly doubled fracture toughness values to 100 MPa root meters. These are excellent. Okay, and we also improved the fatigue crack threshold. Okay, now, but our objective is to enhance the fatigue resistance. Okay, this is the structural integrity of the component. Means you not only increase the fracture toughness, but you also want to increase the fatigue performance. We didn't get much mileage on that. We got small increases, and in some cases it remained the same. Okay, and the reason for that, we did a lot of this analysis, and what happens is a lot of the defects that initiated fracture are all still very large, right, compared to this what this Kitagawa diagram predicted. Okay, so so heat treatment, because the heat treatment that we did doesn't eliminate porosity. The pores remain, unless you do hipping, it won't change. So this is the reason we have this. So we said, okay, maybe we will do short peening, which is a method where we introduce compressive residual stresses, and we can also close the surface pores. And they are the ones which are pretty bad ones, right? And when we do that, all right, we are able to get, I'll show you, the substantial enhancement in fatigue properties. Okay, so in the just heat treated cases, you see the surface pores that are the ones, are near surface pores that are the ones which initiated cracks. So when we short peened it, SP is short peening, see the pores that initiated now are much deeper inside. So for example, here, it's about 240 microns in deeper, and that means we get enhanced fatigue strength. Okay, so I showed you this slide early on. This is as fabricated, and these are the 3D printed alloys, Ti64. This is the conventional manufactured alloy, that's above 500, right? After heat treatment, in these two cases, no change. In these cases, slight improvement, but still not good enough, right? And after short peening, we are able to, at least in 60-67 case, we are as good as the conventional manufactured case. Okay, so we are able to do that. So In heat treating and short peening is, doesn't take away the unique selling point, USP of the 3D printing, because heat treatment is all you have to do is put it in a furnace, and short peening is also a fairly straightforward process. Okay, so this is, you see that in some cases we are able to push this to 0.5 or 0.55 of the ultimate tensile strength, which is what you would want. Okay, now see, a lot of people talk about 3D print additive manufacturing as if it's all one. Okay, but different techniques give you different kinds of microstructures, and which means different kinds of properties. For example, if you do binder jetting, so this is a 316 alloy binder jetting, I already showed you. These binder jetting alloys have lots of porosity. In fact, we thought it will be useless, but surprisingly, so for example, the microstructure of the binder jet alloys looks similar to that of the same 316, but conventionally manufactured, except you have porosity, right? This is the 3D, the selective laser melted. You have the mesostructures and all these kinds of other kinds of pores. Okay, now the binder jet alloy has similar stress strain response as conventionally manufactured, so it shows two-stage work hardening, whereas the selective laser melted alloy doesn't, and ductility is much lower. Okay, here is the surprise. Actually, we were expecting very poor fatigue strength because this material has very high porosity. You see 5.5%, anywhere between 3.5 to 5.5% porosity. So we started very low because the selective laser melted alloy has only about 100 MPa fatigue strength. So we were expecting similar value. But we kept testing, and eventually what we found is the samples, this material has 270 MPa as the fatigue strength. Okay, 6 samples were tested. You see these porosity levels are quite high. These brackets actually indicate porosity levels. Okay, now the reason that happens is this. Okay, this is a published paper, very long paper in ICAMMC. If you are interested, read about it because I'm skipping a lot of details. So Jairaj and Puneet went and tested, checked it. So the run out samples, the samples that didn't fail. Okay, so if you look at a pore, you see cracks have initiated. In fact, there is an initiation, but these cracks seems to have arrested. There are 3 different pores. You can see all of them arrested. So the coarse grain size means, and lower hardening rate in the stage 1 means cracks, the planar slip, the cracks grow, but they are, they get arrested at the boundaries because their driving force is not there. Okay, and that is the reason why, although porosity levels are quite high in this material, you get fairly high fatigue strength. Okay, so there are surprises like this in these materials. You can't treat all the 3D printed methods as the same. Okay, that's, so for example, this illustrates, right? It's selective laser melted, you get only 100 MPa, whereas binder jet printed, you get something like 250 MPa as a fatigue strength. That is because you have all these arresting mechanisms, intrinsic mechanisms. Okay, I'm way beyond my time. So, so you have the microstructural engineering that all of us metallurgists do all the time. And then you also have this 3D printing gives you these mesostructural features that you can tune, okay, to obtain desired combinations of properties. I'm talking about strength, toughness, and fatigue properties. So this gives you a new opportunity to design alloys. Of course, a lot of interesting stuff, a lot of challenges still remain, in particular about structural integrity related issues. So anytime you want to put anything in service, okay, people want to make sure the components will last a particular amount of time, a number of cycles. So and so you need to worry about this, and this is where there are lots of challenges in terms of reliability assurances and structural integrity. And the other thing that I wanted to emphasize is that not all 3D printing technologies yield the same results. We are within the metal 3D printing, and yet still there are a lot of variations and alloy to alloy variations as well. So it gives us a lot of opportunity to do good science, which is not just good enough to publish, but it actually has consequences for manufacturing and productivity and economics, etc. Okay. Thank you very much for your time and attention.
Yeah. Thank you, Professor Ramurthy. That was a very, very good talk and a very good primer for other manufacturing talks that will follow in the subsequent talks sessions. So we don't have a lot of time, but I think we can. I will just ask two of the questions that have been posed in the chat box. Maybe if you have more time, you can take a look at the other ones and respond to them. But the first question is by the I think, yeah, first question I'll take is by Professor Ishwar Prasad. So the idea is he's talking about the issue of dwell fatigue, cold dwell fatigue in Ti-6-4. And he wants to know how do you come, if we have an additively manufactured Ti-6-4, how does the cold dwell fatigue performance, will that change with compared to a conventionally manufactured one, or would it be the same?
Oh, okay. I don't know the answer upfront. I will venture to guess. So now, see, typically cold dwell fatigue, if you have very large colonies of alpha, that is what, if my basic, I didn't do any work on that. But that's my understanding. So what happens in the case of 3D printed metals, you are unlikely to have such large colonies. So it may actually do well with that respect. But there is even bigger problem upfront before porosity, right? So if you were able to completely eliminate porosity, then cold dwell fatigue issues will come up. And I suspect if you then compare, a pore-free 3D printed metal with a conventionally manufactured Ti-6-4, I have a feeling that the 3D printed alloy will do better from the cold dwell perspective. Okay, that's my guess. But porosity not excluded.
Right.
That's totally, yeah.
So just a small follow-up. So porosities, do you think they can be eliminated completely? Because I think that is generally a big challenge, right?
Yeah, you could, the hipping can eliminate, but the issue is economics, right? See, so hipping will add substantial cost. It's also adding to one more complex step to your processing. See, ultimately, if you say USP is, my USP is able to manufacture in the complicated shape in one shot, right? Then hipping may actually add costs to what is already a costly method, and then add complexity. So I'm not a big fan of hipping because this is what happens. So there is also sometimes coarsening of the grains.
Okay.
So in Inconel 718, there is substantial coarsening of the grains. Right. So that's another thing. So it just complicates the process.
Right. So one last question is slightly related to processing. So this is a question by Vaibhavi, and I also want to sort of add to that. So is there any condition on what kind of laser should be used for different alloys or metals? And as an additional question, I just wanted to know what are the disadvantages of, let's say, electron beam melting over laser? Because we see that laser is more or less more commonly used for most of the alloys. But the electron beam melting, we do not hear too much about that compared to laser processing.
Oh, okay. So I don't, the laser beam has to have sufficient energy to melt your particles. So if you are taking aluminum silicon, a low energy beam, should be able to melt it easily, right? Whereas if you take 718, you may require tungsten. So people are trying to build 3D print tungsten. You may need, so that is where the energy considerations come into play. You asked about the electron beam versus, so electron beam, actually the electron beam advantage is a very fast manufacturing process compared to this. So, but I think you don't hear, because electron beam melting, what happens is right now, you can't say you can have a tabletop SLM. You can print new alloys and explore those. Electron beam means you need 200 kgs or some kgs of powder, even if you want to try. So that is where I think a lot of things, and then heating, etc. So for example, I don't hear much about aluminum silicon alloy, that is electron beam, ABM
Right.
manufacturing. Yeah.
Right.
So it's mostly Ti64 and
Super alloy.
so yeah.
Yeah.
So I think that's the kind of considerations, and others may know, Shubham and Function may know more those kinds of details.
Sure. Yeah.
Yeah.
I think we will have several of these talks later in the day.
Yeah.
So with this, I think I thank you. There are some questions in the chat box. You can take a look and answer them if you have some time. I think then this is the end of the keynote session in the morning, and I thank everyone. I think we'll now split into two sessions, two parallel sessions of mechanical behavior of materials and advanced materials and characterization. And I think that will start around 10:45. So there's a small break before we can sort of go to different links. I think link 2, which is provided to everybody, that is the mechanical behavior of materials session, and link 1, which is this one, is advanced materials and characterization, and this will be chaired by Dr. Ishwaraya Varra. So I think he's already here. So with that, I thank everyone, thank the keynote speakers for the session, and hope you all had an enjoyable time. Thank you.
Professor Christopher, can you hear me?
Yes,
Hi, hello.
it's a pleasure.
Okay, so we could hear you, so no issues. Would you like to check your PowerPoint presentation?
Sure.
Yeah.
You see my screen?
Yeah, excellent. So slides are very visible. So yeah, so it's 10:45. I would like to begin with a very good afternoon, attendees and panelist members. Now, in this session, we have three invited talks. Professor Christopher from Drexel University and Professor Knyansham Krishna from University of Hyderabad and Professor Tata Narsingh Rao, ARC International. So this invited talk is for, each invited talk is for 30 minutes and 25 minutes for presentation and 5 minutes for the questions and answers. So I would like to, the first invited talk goes with Dr. Christopher. Briefly, I would like to introduce Dr. Christopher here. So Professor Christopher is a research assistant professor at the AJ Drexel Nanomaterials Institute, Drexel University. Is a Fulbright scholar and received his PhD in 2018 from the University of Notre Dame in Chemical and Biomolecular Engineering, and BSc in 2013 from Princeton University in Chemical and Biological Engineering. His research interests include chemical kinetics, material synthesis, and 2D materials. Professor Christopher interest broadly focused on the relationship between how materials are synthesized and the resultant properties, mainly structure property relations. And with this brief introduction, I would like to request Professor Christopher to start the presentation, and please share your exciting results with us.
Wonderful. Thank you so much for a great introduction. And I want to thank you and the rest of the organizing committee for putting this together. I want to apologize in advance to everyone. It's after midnight here, so I'm presenting from Philadelphia, Pennsylvania right now. So I'm going to be a little bit more tired than I normally am during presentations, but I hope you enjoy. So today I'm going to be focusing primarily on two classes of materials. The first is max phases, and then using those max phases to actually produce maxenes. Before I start talking about my specific results, I want to first convince you why maxenes are important. So they were discovered only in 2011 at Drexel University, so about a decade ago. They have very high metallic conductivity. So maxenes have conductivities above 20,000 Siemens per centimeter. They have an oxide hydroxide redox capable surface, so you can use them for electrochemical energy storage. They are the strongest solution process 2D material, with their Young's modulus actually exceeding about a terapascal now. They're transparent. You can use them for optoelectronics, and they're readily dispersible in water. I'll talk more about some applications that you can use later on, but we've produced actual single flakes from solution processed techniques that are well above 20 microns in size. So they're able to be used for many devices or studying fundamental properties. They are also tunable in terms of their electronic properties, including work function, and you can change their surface chemistry. So you can lead to hydrophilic, hydrophobic materials. You can change their work functions or their optoelectronic properties, kind of however you want. There's over 30 stoichiometric maxenes experimentally synthesized, with a countless number of solid solutions available. So to give you an idea of how easy it is to process maxenes, the typical synthesis process we use leads to them being produced in water itself. And so using water, you can spray coat it, spin coat it, dip coat. You can use it in any way, shape, or form that water is normally in. And so this is without any additives, no surfactants, nothing of this sort. You can do solvent exchange to put maxenes into different solvents, whether it's ethanol, DMSO, NMP, or others. Anything that is essentially hydrophilic, you can mix into your solvents, your maxenes into. And so maxenes, if you would do spin coating, for example, for optoelectronics, you can make these thin transparent films that take advantage of that very high electrical conductivity. And so I'll talk more about all of these properties later on. But so these are all real life examples of things you can use maxenes for. And so this is a picture of TI3C2 coated on a glass film produced in our lab. So like I said, maxenes were only discovered a decade ago, but till now, they're being used in a huge variety of applications. Initially, they were studied for electrochemical energy storage, so for very high rate supercapacitors. But within the last couple years, they've been used for environmental remediation, so using it for desalination or capturing heavy metals from water, for chemical catalysis or oxygen dehydrogenation reactions. A number of MAXenes are biocompatible, so tantalum, titanium, molybdenum ones. And so you can use them for photothermal therapy or anti-tumor, anti-cancer treatments, or as gas sensors, optoelectronics, or even spray-on antennas. So MAXenes are a very kind of broad family of materials that can be used in many different applications. And to be honest, this list is even out of date. So we made this figure in 2019. And so since then, this figure is even out of date. There's new applications coming out, honestly, every couple of weeks. It's getting to the point where it's too hard to follow all of the papers published, as there's about 20 or 30 published per week at this point. So before we get into the two kind of primary MAXene systems that I'm going to be talking about, I first want to go over how they're actually made. So there's a wide variety of different precursors you can use to make MAXenes, broadly classified as MAX phases, which have the p63MMC structure, or non-MAX precursors with similar structures. So if you look at any of these precursors here, the MAXene is going to be these blue atoms and the black atoms in between. So these blue atoms are early transition metals, so titanium, vanadium, niobium, molybdenum, so on and so on. The black elements are carbon and or nitrogen, and the red ones are typically aluminum for MAXene synthesis, but within the MAX world, it could also be silicon, gallium, tin, lead, arsenic, some many other things. And so this rotating diagram here shows you generally what the structure of MAXenes looks like. I'm sorry, of what MAX phases look like. And so what we want to do is we want to selectively remove this red layer of atoms. And so because this red layer of atoms is a complete plane, if you selectively remove them, you're left with these large sheets of 2D material, so the MAXenes themselves. Once you do this etching process, this topochemical etching, you can use pure HF, in situ HF, molten salt, alkali treatments. There's many different ways to do it, depending on what you want to accomplish. But what this leads to is, depending on what your etching environment is, you'll put on these surface terminations. So if you're working in an aqueous environment, so hydrofluoric acid or a mixture of acids, this leads to oxygen, OH, fluorine, surface terminations. And so if you put in different things, you can also add those onto the surface. So if you're adding hydrochloric acid, you'll get chlorine terminations. Or if you're doing it in a bromine molten salt, you'll get full bromine terminations, for example. So it all depends on what you want to get and what your final properties you actually want to get are. And so these will be held together with van der Waals forces. So to separate them, we'll put in different delaminants or different intercalates. So this could be inorganic ones, so lithium ions, for example. Organic ones, so tetramethylmonium hydroxide, tetrabutyl ammonium hydroxide. You can use different solvents, so DMSO, or you can just sonicate your materials. And what this does is this will actually separate all of these flakes, and you'll have a stable colloidal dispersion that you could then use to process however you want. So before we continue, each of those steps is readily scalable. So producing the MAX phases is a bulk powder metallurgical technique. Topochemical synthesis is aqueous-based, volume-based synthesis, and the delamination is as well volume-based synthesis. So each of these steps can be readily scaled up, and so we've actually done that in our lab previously. So we have our own reactor that is a liter, but we also have a 2-liter reactor, so we can make 100 grams of MAXene at once. And so that's really crazy for a 2-dimensional material, making such substantial quantities kind of in one go. And so this is kind of what that looks like. So seeing is believing, 1 gram versus 50 grams of multi-layer powder, or we can delaminate and make this thick dispersion. And so I do want to remind you, this dispersion is only in water. So this is it's just Ti3C2 in water. And so with the amount we've produced here, this can lead to about 240,000 printed supercapacitors, or you can cover the equivalent of a football field in an EMI shield that covers 40 decibels of protection. So just with the basic properties of MAXenes, so their normal synthesis properties and hydrophilic nature, it already leads them to being incredibly versatile materials. Adding on to that is kind of a versatility in the chemistry that's available. So max phases have been known since the 60s. So they're a relatively older class of materials. And what's very unique about them is there's a huge variety of chemistries available that you can kind of tune or tailor. So these red elements here correspond to elements that are found in the M layer. So in this diagram, the red elements. And so you can essentially mix and match M elements. You can do pure M elements. So if you want just pure titanium, you can do that. If you want to mix titanium and niobium or molybdenum and vanadium, you can do that as well. You can do the same thing with the A or X layers. And so you can tune and choose kind of whatever chemistry you want. There's a little bit more complication depending on if you want to actually separate out your atomic layers or have patterns within the M layers themselves. That's something I'm not going to focus on too much in this lecture. But if you're interested, feel free to email me afterwards and I can point you to some really interesting references on that. So what I wanted to do, and I'm going to go through this pretty quickly because I'm already running late, is the actual expansion of the MAX and MAXene systems to include a new family. And I'll talk a little bit about solid solution MAXene. So if you're using two different M elements, how you can control the properties of MAXenes however you want. So one of the things that we found within our lab, so like I said, max phases have been around for 60 years at this point, but we discovered 2 years ago that you could actually create these M5AX4 layers if you use multiple M elements. So in this case, we used an MO4V ALC4 chemistry, and we can get this max phase that's even thicker than any other ones. Now, you may ask me, why would you even want to do this? And doing something like this leads to an even stiffer material. So it's even stronger than any other solution process material. Not only that, it has an interesting kind of unique structure here. So typically, and I showed you the diagram of the previous slide, max phases will have their M elements kind of in a straight line. But in this case, we have this kind of herringbone-like structure. So that's pretty interesting scientifically and something that has never really been seen with these thicker MAXenes before. Now, this max phase is also pretty unique, or MAXene is pretty unique, in that there's only one chemistry that is actually stable in this system. All of the other ones will lead to kind of decomposition into many different max phases. So the MOV system is actually very unique, because you could have the M2AX structure, you could have the M3AX2 structure, M4AX3 structure, or the M5AX4 structure. So this is the only chemistry we've ever seen that this is possible. So depending on how you change your synthesis conditions, just changing the ratios of the M elements leads you to make this huge variety of different structures. So for this section, I'm going to only focus on this one, so the MO4 VALC4 structure. So we were able to successfully synthesize it using a pure HF approach. And so what you see here in these TEM micrographs is the complete removal of the A elements that you saw before, and instead you have the addition of these surface termination groups. And so here's a single flake after delamination using TMAOH and an AFM graph showing kind of the thickness of this. And so this is just showing that we have a successful synthesis, but in the end, scientifically this is interesting, but what can we necessarily use it for? Now, there's a few things that are very interesting and very unique with this one. This MAXene is stable to over 1,000 degrees Celsius. This is more stable than any other MAXene we've discovered, and more stable than almost any other two-dimensional material that I've ever seen. It also has very interesting magnetoresistance properties. So it has a positive magnetoresistance, unlike most other MAXenes which have negative magnetoresistances. But what is kind of more interesting for applications is this MAXene actually absorbs essentially no light. So this artifact is actually because we had to use two different machines and kind of stitch the data together, because one is in the visible, one's in the IR region. But this MAXine absorbs essentially no light. So it has no characteristic absorption peak or plasmon resonance peak. And so this is very good on an optoelectronic device. As you can see, it has a very high conductivity. So a conductivity on the order of 500 Siemens per centimeter. And so you can imagine if you're working with like perovskites or something where you need an electron transport layer where it can't interfere with light, you can spray coat this on, then put your perovskite on, and it acts as an electron transport layer without absorbing or kind of. So that's incredibly unique. And so this is about a 50 nanometer thick film, this one here, and allowing 90% of light to transmit. So even though this is the first one discovered, we did a number of DFT studies, and it's predicted that there's a wide variety of different MAXines that fall within this M5X4 motif. So this is something we're very interested in doing more work in discovery of these, but there's so many different chemistries available that it's going to take us quite a while to kind of sort through all of this. But I can assure you, in due time, there will be a wide variety of other M5X4 MAXines available, in addition to the already 30 plus MAXines discovered. Now, let me switch to the other project really quick. So if we look at published max phases that are solid solutions, the list with aluminum is quite large. What I want to do is draw your attention to 3 of these. So the vanadium titanium, the niobium vanadium, and then the titanium niobium ones. So each of these has a complete solid solution. So this means you can choose any ratio of vanadium to titanium or niobium to vanadium or titanium to niobium. So you can go over the entire range and choose kind of whatever you want. And you can imagine within Max world, this isn't super interesting, but within MAXine world, if you can choose a 2-dimensional material with whatever chemistry you want, that's very important. That's actually also why TMDs are studied so thoroughly as they are, because they also have a similar wide range of chemistries available. Now, we were able to successfully synthesize all the max phases. And so what I'm showing you here is the 002 peaks of each of these changing kind of in a linear controllable way. The same is true with the 110 peaks. So the 002 peak, so this graph, this graph, this graph are related to the C lattice parameter, so the height of the max phase. And then the A lattice parameter is related to the thickness of it. And so with these, there's only one characteristic max phase. So all of the properties we're studying are only related to the M2X structure. And so the only thing changing is the ratio of the chemistries between it. And so with all of the different graphs I'm going to show and all of the different information I'll show you as we go forward, it's all with a 20% variation. So each kind of point is a 20% shift in between the next one. Okay. And so starting off, we see a linear change in the both A lattice parameter and C lattice parameters for all of these different max phases. And so this is a very nice trend to see because it's exactly what we expect. So this is kind of a secondary term of validation showing that the chemistries are what they are. We also have a number of EDS, and we have tons of EDS analysis, XPS analysis that I'm not showing just for posterity in this presentation, but if you're very interested, you can check this Jack's paper down below where we do all of this characterization ad nauseum. Now, what I want to show you is you see this variation of the color of the films as we switch between it. Sorry, let me jump out really quickly. My screen is changing color on me. Okay, sorry about that. So what you see here is we have this kind of continual variation of the film thickness, or the film color, so the reflectivity of the films. We go from this kind of greenish color down to this kind of gold, but you see each point is kind of in the intermediate between it. And so the same is true in going this direction, so between titanium and niobium. But if you look at this one, they look honestly kind of very similar to me. And so I'll kind of talk about why each of these is so different and what kind of unique properties we're looking at. So these XRDs are showing that it's a complete etching and delamination of the MAXines. So there's no max phase peaks left. And so the Raman spectroscopy is showing that you have a kind of a very varying of the characteristic A1G peaks and other peaks as we go from kind of a lighter elements to heavier elements and kind of a continual trend. Now, one of the first things we wanted to confirm is that this is actually a true solid solution. So there's no agglomerations of kind of other element. So if you had different islands of elements, it wouldn't really be a true solid solution, and the properties we're seeing would be kind of different. I'm only showing you the titanium vanadium ones, but we did this for all of them. We see no islands, no agglomerations, no kind of short range or long range order of the elements. So that's very good. Now, if we switch to transmission mode, so instead of looking at reflectivity, you look at transmittance through the actual solution itself, you can see this gradual shift in the transmission color of these materials. So the titanium vanadium one's kind of the most stark one, where you see this purple, and then it goes over to this green. Now, what I want to draw your attention to is kind of this plasmon resonance peak and this one here. So this one here is related to niobium. So niobium 2C has a plasmon resonance at around 1200 nanometers, whereas Ti2C is around 550. But what we see is as you change the ratio, you see a nonlinear change of a plasmon resonance of this peak. And so you see the same thing here if we kind of went out farther like we did in the previous one. And so you see this with all three of these. The vanadium has this plasmon resonance peak a little higher out, around 1400 nanometers. So the niobium vanadium one, you really can't see too much of a difference in, but I can assure you it's happening out in the IR region. Now, this is something that's huge. Not only are we seeing two different plasmon resonance peaks, so we see one for the titanium, one for the niobium, but both of them are shifting in a nonlinear way. So this allows us to essentially tune the plasmon resonance of this MaxScene in a way that we choose, in a way that no other MaxScene can do. So a single element MaxScene can't do this. And if you have essentially an ordered MaxScene, it also wouldn't do it. So you have to have the solid solution one. Now, another property that's baffling to me and absolutely amazing is the electronic properties, so the electrical conductivity. We see a 7 order of magnitude change in the electrical conductivity by just changing the amount of titanium to niobium along with temperature. So I don't know that many properties where such a essentially minor change in the kind of chemistry affects the properties over 7 orders of magnitude in this kind of shocking way. And so you can change it like the other properties, essentially however you want. So if you look at this, it's a controllable thing. If you would take the intermediate titanium niobiums or kind of the extremes, it would be in the extreme values. And so if you're looking at a specific R versus T that you need, so a specific, Hall coefficient or whatever, you could choose it. So you could directly choose it based on the chemistry of the MaxScenes itself. So that's, absolutely phenomenal for many applications, depending on what your actual goal is. Now, what I want to point your attention to is something that is still a little shocking to us, and it's something we've been spending the last, 2 years at this point, trying to figure out what is exactly happening. So I don't want you to look at these entire graphs. There's way too much data going on. What I want to draw your attention to is just this peak here. So this is, the black one is related to the total density of states for the electronic property. And so what I just want to show you is qualitatively, you see a change in these properties as it moves. So you could look at the titanium one as well. You see a qualitative difference in the electronic density of states as we move. And so the branching ratio is kind of related to the number of electrons on the titanium itself. And so you see with the titanium vanadium, there's a linear change, whereas titanium niobium, there's not. And so what all of this means is not only do we're seeing this nonlinear change in the optical properties, we're seeing a linear change in the electrical properties, but we're seeing a nonlinear change in the electronic properties itself. And so this is something that's really interesting and very important for future applications. We're able to essentially change the oxidation state of a single element on our MaxScene without affecting the other one in some cases, but in some cases it affects both. And so we have the kind of more complete branching ratios in the SI for these, but I just wanted to show you this as it was kind of the most extreme example. Now you may ask, okay, cool, you could change these properties, so what? But changing these properties allows you to change the EMI shielding, kind of the shielding, the absorption to reflection ratios. It allows you to choose the actual total shielding effectiveness. You can change the electrochemical energy storage properties, and I will go through this real quick as I'm running out of time. But what I want to draw your attention to is in both cases, one of the middle compositions actually outperforms either of the extremes. And so by changing these electronic properties, you can induce better properties in the overall material than you would normally get with either material in the pure state. And this is opening a completely new realm, a whole new way to deal with MAXenes and actually improve their properties past kind of the state of the art now. So with that, I would like to thank you all for your attention. And like I said, right now we have over 30, this is out of date even as well. We have more than 30 stoichiometric MAXenes discovered. And by kind of tailoring the max phases and discover new max phases, it allows us to discover new MAXenes and find how to make their properties better. And with that, I thank organizing committee, my support, and all of the wonderful scientists who have made this possible. And with that, I would absolutely love to take any questions you may have.
Oh, that's a very nice presentation, Professor Christopher, because we follow Professor Yuri Gogotski's research, and a couple of times he has given presentation to us in the last 3 years. Well, we're glad to see your major driving force in the latest research in MAXene, and glad to see that the new max phages like MO4, VC4, and M5 export phages you are discovering. So okay. So I have a couple of questions from my side, but I would like to take first question from the Professor Ghanshyam Krishna. So he has a question for you. What is the origin of plasmon resonance? And have you calculated any optical constants?
So the origin of the plasmon resonance, it's a transverse plasmon resonance due to kind of the electrical properties of MAXenes itself. And so each different MAXene has different plasmonic properties. We have measured different optical constants such as extinction coefficients. I did not include any of those in this work, and I will actually post a link to that figure, to that paper where we talk about this. So you can look at that, and we talk about 8 or 9 different MAXenes and their kind of optical properties there. But that's a little bit outside of the scope of what I wanted to talk about here, but we have looked at that, and it's something that is absolutely super important for optoelectronic devices.
Okay, thank you, Christopher. So before take the questions from the attendees, I would like to ask a question I have. So you are talking about, I mean, we could see the 2-liter batch processing method where you can generate even in grams also when you can produce the MAXene, right? So when you scale up the process from milligrams to the grams or kilograms, so how do you make sure that to retain the same property that you got when you prepared a small amount of sample and the large chunk of the same sample? So what are the correlation parameters which you make sure that the same property you are obtaining?
Yes. So I love this question. So my background is in chemical engineering. Now, what it is because all of these steps are actually volume-based steps. So we're not doing anything that's surface limited. All of the MAXene synthesis processes follow standard chemical engineering approaches. So if you essentially have a continuous stirred tank reactor, for example, or a batch reactor with high enough stirring rates, where you can ensure that everything's uniformly distributed, you can linearly scale these reactions. So you take the exact same thing we do, 1 gram, so 20 milliliters of etchant per gram, and you scale it up. So you do 1 liter of etchant for 50 grams, and you see a no loss or change in properties. Because it's a pure solid liquid based reaction, all you have to do is make sure that everything's uniformly distributed. So we checked this. I didn't list all of this in the presentation, but we did extensive kind of verification over multiple batches to ensure that there's no difference in surface terminations, flake size, conductivity, so on and so on, to ensure that even as you scale it from 1 gram to 50 grams to 100 grams, there's no change in properties.
Okay, so I have the follow-up question for the same things, because I work in 2D materials. I thought I will put the same thing for the Maxine. Because all these are solvent processing of 2-dimensional nanosheets, isn't it? Now, when you prepare 1 ml of some suspension where 2D materials are there, we always get a polydispersed sample. And when you apply the same concept to the Maxine, the surface termination and the relative percentage of the surface termination for the fixed flake size will definitely vary. So when you say that the polydispersity and the number of nanosheets in that particular nanometer range will definitely vary when you scale it up. So that eventually change the physical properties, isn't it? So how do you correlate the polydispersity and the surface termination and retaining the physical properties that we're talking about the lab scale experiments?
So here, let me share my screen. I have a slide just for this. So whenever we actually scale this up, so you can see my screen again, right?
Yep.
So when you actually scale this up, we don't see any difference in the surface terminations in the global scale. It's true, individual single flakes may have slight differences in surface terminations. You may have single flakes that have higher fluorine versus O versus whatever. But in the overall grand scheme, we see no quantitative differences in the global averages, whether it's in flake size and dispersion or in the surface terminations themselves. And so if you look at this advanced engineering materials paper, that's what this whole paper is about, just showing that this is the case.
I see. Wow, that's a great result. I think I've seen a paper, 2D materials zoo. Now the Maxine zoo will come up in the coming years. And thanks a lot for sharing your exciting results. And thank you very much for accepting our invitation and sharing your results with us. Thank you, Christopher.
Thank you so much.
There are no further questions. So if somebody is interested, maybe they will contact you. But as of now, I don't see any questions. And thank you very much for joining the session.
Wonderful. Thank you so much. I really appreciate it.
Thank you. Okay. So now our next speaker is Professor Ghanshyam Krishna. Professor Ghanshyam Krishna is here. I would like to introduce Professor Ghanshyam Krishna. Sir, I'm Dr. Ishwaraya. I'm an assistant professor in the physics department. So Dr. Ghanshyam Krishna, he's currently as a professor and head for advanced studies in electronic science and technology, School of Physics, University of Hyderabad. Sir, Professor Ghanshyam Krishna is currently also a dean. He was dean in charge for School of Engineering, Sciences and Technology in the same university during 2016 to 2020, and professor in charge for Center for Nanotechnology since 2014. And Professor Ghanshyam Krishna received several honors and recognitions. Some of the awards I'm going to read out here. He's a fellow of Andhra Pradesh and the Telangana State Academy of Sciences, and he's a member in National Academy of Sciences, India, Allahabad since 2011. And he's also visiting academic at Department of Engineering Sciences, University of Oxford, UK, and Department of Physics, University of Trento, Italy. And he's associate editor in a Bulletin of Material Science, published by the Springer for Indian Academy of Sciences since 2011. And Professor Ghanshyam Krishna published 150 journal papers, and he holds US patent and European patent and Indian patents, and is the 2 book chapters. And currently, Professor Ghanshyam Krishna guided 14 PhD students and currently 6 students, ongoing students. And he received several awards worth 30 million Indian rupees projects. And Professor Ghanshyam Krishna's research interests are thin films, electronic and optoelectronics devices, sensors, and nanomaterials. So with that brief introduction about Professor Krishna, so I would like to request Professor Krishna to give the invited talk to us. And sir, please.
Thank you, Dr. Ishwaraya, for the kind introduction. And thank you to the organizers for giving me an opportunity to share some work that we've been doing for the last few years. Is my screen visible and am I audible?
Yes, sir. Your screen is visible and you are audible, sir.
Should I go to full screen mode then?
Yes.
Is this okay? I just check if the
Perfect.
slides are changed.
Oh,
Yeah.
perfect.
Yeah. I should also acknowledge that one part of the introduction where you talked about patents is related to Dr. Kiran's work. I'm very happy that he's here. I can see him. So what I'm going to do today is not talk about Kiran's work, but I'm going to talk about some other work that we've been doing for the last few years on understanding the growth of zinc oxide nanostructures and using different kinds of techniques and examining the role of seed and catalyst and see whether they are really essential. And if they are essential, then or do a comparison between seed-free and catalyst-free growths. So before I go on, I would like to acknowledge my student Rajesh. Much of the work that I'm going to present is based on the thesis he's going to submit soon. Then other students like Umar Pasha, Durga Prasad, my collaborators in other institutions. So this will be my the outline of my talk by zinc oxide. Then I'll tell you briefly, give you results about the seeded hydrothermal synthesis and self-catalysis, which is a seed-free kind of growth, and then seed and catalyst-free hydrothermal synthesis, and then some properties of the zinc oxide wires that we have grown. So today, essentially, I'm going to talk about growth and our understanding of why things grow the way they grow. And this audience is very familiar with zinc oxide, so I don't have to go through this. It's a very interesting material because it lends itself to all kinds of applications, and it continues to attract interest because of the ease with which you can actually deliver it in many forms like thin films, nanowires, nanorods, and particles, and so on and so forth. It has got good band gap, good semiconducting properties, high dielectric constant. So there are a variety of applications where zinc oxide can be used. It is, in some sense, a replacement for titanium oxide, which was when in the early 80s and 90s, everyone used to work on titanium oxide. And zinc oxide has replaced that in the nano world. So you can do many things with nanowires, such as lasing, waveguiding, use them in solar cells, electronic applications, and so on and so forth. One of the main applications that people have been looking at is gas sensing. Then because it has got very tunable photoluminescence, zinc oxide vertically aligned zinc oxide nanowires are very useful for LEDs. Then more recently, the pointer. So more recently, they've found some use in resistive random access memories, which is a new emerging area of electronics, where zinc oxide films can be used to switch from high resistance state to the low resistance state. So it can act as a sort of a memory device, which is very interesting. So you can make nanowires of zinc oxide and use them in electronic memory, non-volatile memory type of devices. So that is a very interesting application for this. So typically the nanowire growth strategies are vapor liquid, vapor solid methods, laser electric field assisted growth, and hydrothermal methods. So what I'm going to describe today is one of these methods, and a method that we sort of developed in our own lab some time back. So what is vapor liquid or vapor solid transformation? Essentially that you evaporate the source material in a furnace, and then you transport the reaction gas, and then at a very high temperature there is a reaction between the source and the gas that you are carrying, and because of the nature of the reactions, as the vapor melts and makes a phase transformation into the solid phase, they grow in particular fashion, especially because of the oxygen that is present. It pulls out the material and forms nanowires. But the problem here is the sort of high temperature that has to be used, which is close to 800, 900. So it is restrictive in the sense that the kind of applications that you can use them for are sort of limited. Our interest is to look at possibly flexible electronic, flexible optoelectronic applications, and which is what I will show you in a little while. So the other method which is used sometimes is this so-called laser decomposition of zinc acetate, and then doing very clever manipulation of the surface, you can actually focus the laser beam at points where you want to convert the precursor into the oxide, and then because of the process of stress relief, again it grows in the form of wires and so on. So this again requires slightly higher temperatures, and but the advantage of this technique is that it can be locally grown, so you can do a sort of a targeted growth of these nanowires wherever you want. So some of the disadvantages of these techniques essentially are that they require high temperature or a catalyst or both. And because our interest is in flexible substrates like polymeric substrates, so we the high temperatures places constraints in substrates and catalysts, so it is not compatible industrially. Now, while they are good for studying the properties, it is not very good in terms of actual application and scale up because of the number of steps that are involved in the process. So the idea, therefore, is to develop a technique that involves relatively low temperatures. It's catalyst free, not dependent on the substrate, and allows isolation of a single nanowire, and also industry compatible. So the aim of this work essentially is to compare, again, we would like to reduce the number of steps which are required to make the wires, because if I have to transfer this to for an application, then the number of steps that are required to make the nanowire should not be more than one, ideally, but it could be that you can do it in 2 steps, but we would like to avoid the second step. So this is the normal thing that is done in hydrothermal synthesis, that you basically take a substrate, do a surface treatment, and then coat a seeded layer like zinc oxide or gold, put it in an autoclave at high pressure, and temperatures are typically between 90 degrees C to about 150 to 180 degrees C, and then there is a decomposition of the precursors, and that which leads to a reaction between the zinc precursor and the reactants, and that leads to the formation of zinc oxide. And because of the way the reaction takes place, these objects grow in the form of wires. So you can control them by basically controlling the temperature and duration, and also the seed layer that you're using. So, so you can grow them in the form of wires and so on. So these wires are fairly, they grow quite nicely. And if you're able to control the process well, this is from literature, early literature, that you can grow them with large aspect ratios, very high density. And this layer here is zinc oxide. And then on top of that, the zinc oxide seed layer is grown either by sol gel or thermal evaporation or something like that. And then this layer is introduced into the hydrothermal reactor, and because of the process of reaction, these wires grow because of the nucleation sites that are provided by the zinc oxide seed layer. So this is the conventional one. So initially we repeated this. So the objectives of the work essentially, so I'm only going to present this part of the work mainly, but we have published a lot of work on properties also. But in this talk, I'm going to only focus on understanding the role of the seed and catalyst in hydrothermal synthesis, compare seeded and catalyst aided growth, and compare the properties of nanostructures. So some properties I will sort of show you. So what we do is essentially that we deposit the metal oxide thin films on a substrate, which is typically glass, to thicknesses of 10 to 300 nanometers, and then we heat the if it is a metal film, then we heat it in air at 200 to 400 degrees C to get thermally oxidized zinc oxide, and then introduce these samples in the hydrothermal reactor, and then process at 90 degrees to 180 degrees for about from 10 minutes to about 12 to 15 hours. And then we see that on top of this, we get arrays of nanowires. So this is a detail of that. This part is not very important. We use an aqueous solution containing zinc acetate or zinc nitrate mixed with HMTA, and these are introduced in the reactor and at different temperatures. So the aim is to see, as I said, the effect of the time and effect of the duration, the temperature on what happens to the shape, the density, and how they grow, and so on and so forth. We have used many seed layers, but I'm only going to talk about the zinc oxide layer, seed layer mainly. Indium, tin, thermally oxidized indium and tin, gold, and zinc oxide. These are all grown thermally by thermal evaporation on glass substrates, and we put them in the autoclave to look at the growth patterns. So just a little basic about what the role the HMTA plays in this. So this is a step. It basically provides the hydroxyl ions for the zinc precursor to convert from the precursor part to zinc oxide and water. So it acts as a pH buffer, and also more importantly, it generally attaches to the the non-polar facets of zinc oxide. It also facilitates the crystal growth, and so if you want to orient your nanowires in a particular direction, then it is also important for you to choose the correct the kind of precursor. So HMTA plays several roles. One is to essentially control the growth in a particular direction, and also the crystallographic texture of these wires that you grow. So you can play around with all these things and then see what happens. So the first part of the work was essentially to see what happens to the. So I'm only going to talk about the seed layer. The seed layer here is zinc oxide. So we deposited using thermal evaporation different kinds of things. The microstructure is fairly clear. At 100 nanometers, you get very small grains, and the grain size grows as a function of thickness. So at 300 nanometers, it is basically flaky in structure. They're very sort of nanocrystalline. And then we looked at the defects in these structures from photoluminescence. And the interesting part is essentially that the near band edge emission of zinc oxide in these seed layer is very low in intensity. So there is, and the defect related peaks are very high in intensity and very broad. This basically tells you that there are a number of defects in the zinc oxide seed layer, which are related to oxygen vacancies and interstitials and so on. This is confirmed by the Raman spectra that we took. Very unusually, we get these low wave number peaks, which clearly tell us that the zinc oxide that we have made through thermal evaporation has a large number of defects. So the impact of this on the nanowires we'll talk about in the subsequent slides. And the band gap is fairly large. It's of the order of 3.2 electron volts, and the transmission is fairly high. So they're good quality materials. So these are the seed layers. These are not the nanowires. And then when we grow the nanowires on top, we find very interestingly that the defects are propagated in the into the nanowires, and so they also show a defect-related peak. Now, this I would like you to remember that this will be very different in the case of the nanostructures that we grow without the seed layer. So these defect peaks continue to exist in the nanowires, and so you get two very sharp photoluminescent peaks, which can be tuned either by duration of hydrothermal synthesis at fixed temperature or changing the temperature at a fixed duration. And the intensity of these defect peaks is very important. What it tells you also is that the surface of the nanowires that are growing also have a large number of surface defects, oxygen vacancies, which for a particular application that I'm going to talk about a little later is very important. So this was confirmed using Raman spectroscopy. So we did some work on water contact angles, and we found that that on different layers like indium and tin oxide, they were hydrophobic, whereas on the zinc oxide seed layer, if you grow the nanowires, they're super hydrophobic. The reason for this, as I said before, is that we believe that the oxygen vacancies on the surface, in the presence of in the presence of water, because there are oxygen vacancies, they're able to attract the OH ions very well, and therefore depending on the kind of defect structure that is on the surface, the contact angle also changes. And so if the seed layer is zinc oxide, then it is super hydrophobic, whereas if the seed layer is gold or other kinds of materials, then the water contact angle is a little lower. And then the impact of this under ultraviolet radiation, because we also wanted to see what is the, look at the self-cleaning applications of these. So within about 10 minutes of ultraviolet irradiation, they all become either hydrophilic or super hydrophilic. But it takes about 3 to 4 hours for us to recover the angle. But the important part is that within about 10 to 15 minutes, they change the water contact angle. And the reason for the transition, again, as we have said in our papers, is the fact that under the impact of radiation, these oxygen vacancies become very reactive with the OH ions, and therefore the contact angle changes as a function of UV radiation. So just to give you an example, some images of these things. As you can see, as you change the temperature, there's a lot of change in the aspect ratios and the dimensions and the lengths. So typically, the lengths are of the order of 2 to 5 microns. The diameters are of the order of 50 to 200 nanometers. And as you increase the time at a fixed temperature, you can see that they are fairly long. But the other interesting part is that if you do the process for a very long time, then it appears that they all become hexagonal in nature. So all the rods take the hexagonal form, irrespective of the temperature, if they are hydrothermally synthesized for a fairly long time. Okay, that is because the basic structure, crystal structure of zinc oxide is hexagonal, and so we think that the equilibrium shape of all these wires, if you give it a long time to relax, is going to be hexagonal, and we have a lot of evidence for that. I'm not presenting all that. Sorry. The other part that is quite interesting is that if you want very thin and long wires, then you have to do the hydrothermal process either at a low temperature and short time, or high temperature and a short time. So the nucleation of these wires takes place within the first sort of 5 to 10 minutes of the process. And so if you really want to make very thin wires and very, the aspect ratio of 1 or 2 you want, then you must do the process for a very short duration. So this is on gold films, and you can see how nice they also form hexagonal rods and nanotubes and so on. So I will not go into details of this because I'm running out of time. So I will quickly go to the other part, which is, so we have seen that there is a certain pattern to the growth on the seed and seeded growth, which is basically that you get high density wires and you get very thin and long wires and so on. So let's see what happens if we do the same process without any seed. So the first example that I'm going to quickly go through is which we did some time ago, which is called self-catalysis, where you make a metal film and then you put it in oxide atmosphere. And when you take the metal film to close to its melting point, it reacts with the oxygen in the ambient atmosphere. And as the reaction takes place, the liquid, molten liquid, basically pulls out material and it forms nanowires, which then eventually break. So this process was done. I will quickly go through this. So we did zinc metal films on substrate. Then we heated it to above its melting point, which is 419. And then it melts and it forms these kinds of wires. So this is the process that we believe takes place. So the melting takes place, there is oxygen adsorption, then dendrites of zinc oxide form, which collapse after a certain time. So SEM evidence clearly shows this. So this is, I'll go through this later. So it forms these balls of molten solid, from which if you look closely, you get these kind of wire structures. So this is a process which is self-catalysis, which means that I am not using any seed layer, but I am essentially doing an oxidation reaction, and I'm quenching the reaction. So I keep it in the furnace I introduce the sample at 500 degrees for about 30 minutes, and then at 500 degrees, I pull it out of the furnace and allow it to rapidly quench to room temperature. And then I get this kind of growth. So we did some very basic TEM studies, and we really see that this is the molten seed, and then you have these dendrites which are sort of coming out. So this is one form of seed-free growth. So crystallinity, texture, and all these things I studied. I can, if somebody wants. And then we have also done doping of these things. So these are all the. Now in the hydrothermal synthesis also we have tried this thing where we have grown these structures directly on the glass substrate. So the question that we are asking is whether it is really necessary for us to have a seed layer. If you remember in the earlier slides, I showed very high density kind of nanowires which are very thin and long. But here what happens is, so this is directly grown on glass. You can see that the number of nucleation sites is very limited. This is a large area, low magnification image, 10 micron scale. And you can see that in some spots it is growing, and it is from that spot it is growing out like a sort of a hexagonal nanoflower or tetrapod. And so, and within a very short, I mean, this is for 3 hours. And then you see that all the, as I said in the earlier part, that they all grow in the form of hexagonal rods. So this is a very basic difference between the seeded growth and the seed-free growth, that the number of nucleation sites is less, and also the energy is directly transferred to the growing nanostructures, and therefore they take the equilibrium shape, which is the hexagon. So we have done all kinds of other types of studies. Sorry. they also have a lot of defects which can be exploited for application. This is an experiment we did on polyimide substrates, and you can again see that they grow as nanowires, and but the density is very low. There is a lot of porosity here, and so which we think is related to. So this is work on polyimide substrate, which is a flexible substrate used in electronic applications. And so we get very short wires which are not vertically aligned, and but they are horizontally aligned. So the kind of application these can be used for will be very different. The interesting part is that the photoluminescence does not show any, or very negligible presence for the defect-related peaks. So the only emission that you get is the near band edge, which is good in some sense that you can use them for blue light emission. And the lack of defects is also reflected in the Raman spectrum, where the high wave number peaks are completely absent. So the red color is the zinc oxide on polyimide directly. Okay, in the next couple of minutes, I'll just go through some of the interesting applications. So these are a lot of applications, but some of them I'll show you. This is a experiment we did using a scanning near field optical microscope to just see if we can isolate a wire and see, because these are transparent, so we wanted to see whether we can basically use them for optical interconnects. So what we do is we shine light at one end of the wire and then look at what happens at the other end. So you can indeed see that this is bright, and at the other end it is not so bright. So there is propagation, but it is slightly lossy propagation. So we need to improve this thing. But this tells you that these wires can be isolated and you can use them for photon propagation. Then we also use them for SCRS kind of application, which is basically you take the wires and decorate them with silver nanoparticles and then look at the detection of explosive molecules. And we do see a lot of enhancement. I mean, this is the wires decorated with silver nanoparticles of different sizes. And you can see that these are two molecules, ANTA, and we used another one, which is a plastic explosive. I think it was called CL6. So they are very sensitive to, so they can be used for surface enhanced Raman spectroscopy. I've already talked about superhydrophobicity. Then we also made nanowire field effect transistors, which is again an area of a lot of interest because they can then be used for gas sensing. And so we did a fabrication, developed a fabrication process where we can actually make field effect transistors. So these are the sort of characteristics, and this graph tells you that these act as p-channel MOSFETs, which is quite an interesting thing for electronic applications. So the road ahead basically is to see how well we can isolate single nanowires. So the summary essentially is that the seed layers provide a larger number of nucleation sites, so the density of nanowire arrays is higher. They also enable vertical alignment because we think there is a sort of a free energy template which allows them to that. The seed-free growth lacks the energy to enable vertical alignment because the nucleation sites are fewer and it requires larger energy for the alignment. So the shape evolution takes place before the alignment of the wire happens. And most interestingly, the defects in the seed layer propagate through the nanostructures. And therefore, if you have a seed layer, then you can essentially tune the defects and you can have luminescence both in the visible and in the near band edge. These can be made, the contact angle of these kinds of structures can be tuned by tuning the surface oxygen cases. So I think I'll stop here. We want to see whether how well we can control the aspect ratio. Can we disperse them uniformly? And our long-term aim is to deposit these things on fabrics and other flexible substrates, and also make FETs and sensors. Thank you very much for your attention. I'll be happy to answer any questions if there are.
Thank you very much, sir. It was really interesting because even though zinc oxide and titanium dioxide are very old material, but whenever we look at their morphology, we'll be keep looking at their morphology and amazing, very good microscopic images. And thanks a lot for sharing your research experience with us. Maybe before audience ask the question, I just have a quick one. So
yeah.
Very long zinc oxide nanorods by this both seeded and seed free. Sir, how easy is to align them, these zinc oxide nanorods, on any substrate? Is it easy to align them like a vertical carbon nanotubes? Can we make a vertical, in a really lots of because by chemical approaches, if that is possible, maybe 1 centimeter, 1 centimeter, even beyond that. Is it possible, sir?
See, the short answer to your question is yes. What we have found is that if you have a zinc oxide seed layer fairly thin, then the zinc oxide, the free energy at the interface is very low, and therefore it enables the growth in the vertical direction. Okay, and these substrates are fairly large. They are like 1.5 centimeter by 1.5 centimeter. So they are grown uniformly on these substrates. So scaling up is not a problem at all. The problem that we find is the quality of the seed layer that you're growing. If they are uniform and they have very small grain size and their crystallographic texture can be controlled, then by hydrothermal synthesis, it is very easy to get vertically aligned nanowires. So the vertical alignment is natural, but don't go for very long synthesis durations. Then they break and they form these hexagonal rods, which are not very useful.
Okay. So we have one question from Professor Pradyuman. Does a seed layer behave like a seed crystal?
Yeah, I mean, that is a long-standing debate in the literature. Yes, I mean, depending on so the seed layer has two roles. One is to provide these so-called, nucleation sites. The other one is that it also helps you to get the texture. So in that sense, it acts as a seed crystal. But there is a role for the things like the chemical precursors like HMTA and NaOH and KOH. What they do is they expose the facets in the zinc oxide. So they also play a role in the texturing of and the alignment. So the answer is that there is a role, but it is not the dominant role for the seed layer. So it's a combination of the seed layer and the precursors that are using, which determine the alignment and the crystalloid texture. Okay, I hope that answers the question.
Yeah, I hope that answer is okay. I don't see further questions. If there are no further questions, I would like to thank you, sir. Thank you for inviting our invitation, and thank you for sharing your research experience with us.
Thank you, sir. I'll log off. I'll stop sharing.
Yes, sir.
What do I do?
There is you have to stop sharing, sir. Maybe on your screen you will be seeing one button. Stop share.
Oh, stop share. Yeah, sorry.
Yeah. Yeah.
Okay. Thank you.
Fine. Thank
you
very
much. Thanks.
Ishwar. Ishwar. Ishwar.
Yes, I can.
Narasimhan is joining just in a few minutes.
Yes, yes.
If there are any more questions, I can answer meanwhile.
Yes, sir, I'm checking.
There doesn't seem to be any questions. Okay.
No questions, sir.
Okay.
If maybe the audience will directly contact you.
Yeah. Okay. Thank you.
Thank you, sir.
Thank you, sir.
Thanks, Kiran.
Yes.
Yeah.
I just called him. He's joining. Huh?
Okay. Yes, Kiran.
Schedule is 12, right?
Huh?
Yes, yes, done.
12 o'clock. 12 to 12:30.
Share that.
Sir, your mic is mute, sir.
Yeah. Sorry, am I late or okay?
No, sir, you are on time. Your session is actually about.
You're exactly on time.
You are exactly on time.
Thank you.
Thank you so much. Yeah.
Okay.
We'll make you co-host now. Yeah, you can please, you can
Yes.
share. Yeah, Ishwar, please.
So I can share my presentation. Start.
I will, sir. Please give me 3 minutes, sir. I will,
Okay.
I'm myself. I'm Ishwaraya. I'm a faculty in physics department, sir. I'm chairing this session. So, dear audience, I would like to introduce about Dr. Tata Narsingh Rao. Well, the CV is very long, but I would like to give a brief details because Dr. Rao is a very well-known scientist in India because of his notable contributions. Because myself, I could see when I was as a graduate student, when I attended Bangalore Nano in 2012, so I could see ARCI knowledge generation in nanoscience and nanotechnology. Lots of books have been published in that area. Well, Dr. Narsingh Rao received his PhD degree in chemistry from Banaras Hindu University in 1994. After working at IIT Madras as a research associate, he moved to University of Tokyo as a JSPS fellow and subsequently became a lecturer in the same university in 2011. After that, Dr. Rao joined ARCI, that's the popular name, in Hyderabad, and as a senior scientist. After that, he a lot of contributions, and now currently is the director in charge at the ARCI. He was also guest faculty at IIT Hyderabad and University of Hyderabad in the past. He is a recipient of several awards and honors, including MRSI Medal 2009, Tokyo University of Science President Award 2014, and Academician of Asia Pacific Academy of Materials 2015 Award, and Technology Day National Awards. And he's a fellow of Telangana and AP Academy of Sciences received in 2017, and Bangalore India Nano Award in 2018. Dr. Rao published more than 175 research papers and filed and granted more than 20 international and Indian patents. And his publications got total citations more than 16,000 with an index of 46. And one of the significant research from Dr. Rao's group is that there's a translational nanomaterials research. He has developed a lot of novel, scalable, and low-cost process for suspension, powder production of nano silver and nano TiO2 for self-cleaning, and the list goes on. So with that short introduction, I would like to request and invite Dr. Rao to go ahead with the talk. Sir, please.
Okay. Thank you, Mr. Ishwaraya, and all the members, organizers for giving me this opportunity. SRM anyway, many times I give talks both at Chennai and AP SRM also. Now Professor Narayan Rao, he doesn't leave me for any opportunity. Already this AP itself, several times I visited, and very recently I am on my governing board also, research council, where our Professor Dr. Saraswat was chairing that.
Yes, sir. Yeah.
So thanks a lot. It is very nice to be back with you. So let me put that my presentation, upload it, share the screen, and this one, share. So you're able to see my screen?
Yes, sir. We are able to see. We are able to hear. So what the
now it's a full screen now. Okay.
Not yet. Yes, sir. Now it's fine. Now it's fine.
Okay. Right. Fine. So let me just. It's blocking mine now. Fine. Okay. Yeah. Translational metal research in energy storage technologies. I think many people may be familiar with my talk, but I can't help because I cannot give new talks every time. But material is almost the same. So I am presently additional charge director of ARC after a very sad demise of our beloved past director, Dr. Padmanabhan. We really miss him. And ARCI is a institute under Department of Science and Technology with a mandate of transforming laboratory research into technology and transfer to industries. So all our projects are directed towards application research, and then we make sure that we go from the lab scale research and publish papers in good journals, and then we have a lot of PhD students working with us, and wherever we have in many cases, because we choose the topic in such a way that the topic leads to some application, and we are successful in several cases, and then all our students are also benefited because they know when they join us what kind of technologies are required, and then how translation happens and all. Everyone knows about technology readiness level, TRL language here. So that's one good thing. Then today's talk, I just want to present a focus on more energy storage technologies, because that is the topic of the day everywhere. And there's a huge push from the government or globally to meet the carbon footprint. And COP26 recently also we promised that we'll bring down the carbon footprint to as minimum as possible in coming decades. With that, I will start my talk. And ARCI, when I say translational research, which means that we should know that what is TR, technology readiness level of our work where we stand. Usually in India especially, we have two kinds of groups. One is most of the universities, research institutes falling under government or some private. And our job, if you are an academic institute, you have to do this, you have to train your students and do all this basic research. That is TRL, technology readiness level, TRL 1, 2, 3. There is basic technology research, research to prove feasibility, and technology development. And you can file a patent and leave it here. And there is another sector, there is a private sector. What they do is they get the basic components from abroad, import it, and in the case of battery packs for electric vehicles, the primary cells means the basic cells is not primary, it is second is the lithium-ion batteries, and the cells of 18650 or 22650 or the small cells, they bring it, import it, and then use a BMS, battery management system, and make a battery pack in series parallel combination. The pack requirement depends on what motor you are using in your electric vehicle. If it is a scooter with 48 volts, you have to put your battery pack in such a way that it gives 40 volt output and specific energy density of at least 1.5 to 2 kilowatt hours, so that the scooter will run up to 100 or 150 kilometers. So these are all known. So these private sectors, whoever makes the battery packs, they do import components. And the technology for making the primary component, what is required, that is the key, and then that will miss, which is the gap. So unless you do that, then the gap will not be filled, and then you cannot become a total technology provider. And unless you become technology provider in total, and your cost of the electric vehicles will not come down if it is a battery-driven vehicle, and then you can never compete with the other countries. There are three components in battery technology, because we are talking about storage. One is the cell making itself, and cell making you can always do on a turnkey basis. You pay money and then you import the machines, and those guys will come and then install your machine. There's a 1 kilowatt, 1 gigawatt or 1 megawatt, whatever it's plant, and then they will show you that how to get the battery cells out of it. And you import the material, you import the copper foil, you import the aluminum foil for the current collector, and the separator, and the electrolyte, everything, and make the battery. So that only gives you some experience on how to make it. You import the cooker, and then you import the basmati rice, import the pulses, import the spices, everything. And then finally you make biryani. That means you only got some expertise on making biryani, but you can never compete with the biryani of what is being imported. Right? So that's what exactly happening at the moment. But that's fine. Way ahead, if you want to compete and if you want to realize your car cost should come down, 40% to 30% cost of the car, electric car, is the battery cost. And out of that one, more than 50% cost is coming because of the imports. Right? So unless you indigenize the technology, at least at this point of time, you make the technology indigenize for materials part, because 60% of the battery cell cost is the materials, whether in the form of cathode, anode, lithium iron phosphate cathode and graphite anode. And the current collectors, aluminum foil, Hindalco can make the aluminum foil of 20 microns thick. So making that thin, they can make, maybe already they are 30 microns. So making so thin is the most important. This, otherwise, if it is thick aluminum foil, you can use, but you cannot use enough material in the battery so that your energy density is not enough. Right. At the same time, you cannot have too small a foil like your kitchen foil. It will tear away and punch the battery. So these are the critical things what the Indian industry should think at the component level. And then we can save the cost up to 40-50% of the battery. And the remaining will go of the, so now I already talked in the biryani, basmati rice, pulses, everything you can get it in India itself. You grow in your fields and then crops and all. But the cooker cost is still you are importing. So the battery making machine pilot line is almost 50 to 60%. That still is being imported. And no efforts are being made for that. Either the material itself, the lithium iron phosphate, you may have copper foil, aluminum foil, that can, but lithium iron phosphate or lithium cobalt oxide or lithium nickel manganese oxide, what is cathode, that has to be made in India. There, at least one component you have to depend, that is the lithium carbonate is the source. There is no lithium in India. So you can get from Bolivia or Argentina at low cost. And we have a lot of tie-up with our Indian companies because international cooperation with South American countries. So not even that, so far, Amar Raja, Exide, so many, Hyderabad Batteries Limited, so many companies are starting their facilities to make the batteries, which is very good, but the materials inside still have to be imported. So ARC has started to make the lithium iron phosphate, which is a key material for the Indian automotive, electric vehicle technology, because lithium nickel manganese cobalt oxide, you have cobalt and nickel, they make the material costly and they have higher voltage, around 4 volts. And if you cross beyond 3.5 volts, there is always a danger of fire because your electrolyte may decompose, and when you draw current, it may get heated up. A lot of accidents happen because of that one, because cobalt tries to release oxygen very fast from lithium cobalt oxide from the cobalt. But if you have phosphate network, phosphate holds the oxygen tight, and then lithium iron phosphate, the flash point is at least 100 degrees higher than lithium nickel manganese oxide. And iron is so cheap. So even Tesla is looking for lithium iron phosphate cars, batteries in India and China because they have a better market. If it is cobalt based, then it is expensive. They may not be able to sell in their cost. So with this, now bridging the gap is very key if you want to go to high TR levels of 7, 8, 9. So ARCA does that one. And dissolved pollution, 30 to 40% of combustion engines about diesel, petrol, which gives a lot of carbon. Remaining all 60% goes into carbon, soot and all, and unburned hydrocarbon pollution. And you have red part is a nanoparticles, use numbers, they come off the carbon particles coated with unburned hydrocarbon. And when they float, and because of Brownian notion and low density, they travel long distances and people inhale them, and inhalation toxicity is very dangerous. Your lungs get choked, and all these problems are there just because of your fuels, which you are importing by paying used prices. So there's a need to cut down the dependence of imports and then encourage the electric vehicles. This is what is the mission now. And a lot of companies in India are already there. If you see the cost of the electric vehicles, it is with the same performance of Wagoner. If you take E2O, it is 3 lakhs because the 60 to 50% cost is batteries, which we are importing. But if you see the consumption, 10,000 kilometers per year, if a car goes around, and 5,000 rupees per year only you will spend on electricity, whereas 75,000 per year is the fuel, petrol, when 75 rupees per liter, but it is 2015. But today it is more than 1 lakh. That means in 3 years you will get your 3 lakhs back. If you use electric vehicle, even you pay 8 lakhs. And no noise pollution, no air pollution. But if you can make the batteries within the country, then it is totally economical. And a lot of companies are making their cars, buses, especially 2-wheelers and 3-wheelers. Is a huge market in India in next 5 years. And then all the batteries for these vehicles come from abroad, and the materials, everything is imported. So indigenization of technology is very important. And when you use the imported batteries from, see, in the EV market, because EV is being pushed so much, and then everyone wants EV, user wants EV, the companies wants to produce EV, and a lot of companies. But in the process, if you are importing the basic cells at the cell level of batteries, the problem is you don't know what kind of battery comes, and if you are properly not packing the battery, and if there is small hotspot, for example, I'm telling, I see for a battery pack of scooter with 48 volts, you need more than 100 cells of 18650, and then even if one cell in that battery pack goes bad and gets heated, whole battery pack gets the heat through it, and then finally it will blast. That's why all these fires happen. So if you make the batteries in India, at least you know that who are the company which is making, and then you have to put restrictions and the standardization implications and all can be imposed. So that is one need. And second is, you should not import all these while problem being there for the cell itself. And if you do the chemistry of lithium, nickel, manganese, cobalt chemistry, then there is a second danger which is coming. So all this will lead. So indigenization of battery technology, recent battery fires, we have a roundtable EV discussion where we're all discussing about this. And I told that 60% of the cost of battery cell is materials, and we have to work. And today, LG-CAM, CATL, BYD, Panasonic, Tesla, all these cells are being imported to make battery packs. But if these are imported, it's okay. They are little expensive, they are still safe. But people get from all kind of sources, because when you have a cost competition and the business, then you need to sell your scooter at low cost. So you start compromising on getting some low cost batteries, where the problem comes. And it also disrupts the mission, National Electric Mobility Mission, because if there are 10, 15 fires on the electric vehicles, then people stop using electric vehicles, which is another danger, and all these companies will shut down. So we need to have a quick need of the hour is that indigenize the technology. And if you come to the battery materials here, the voltage of the cell depends on what anode and cathode you are using. And if you see the voltage on the y-axis, it is the 0 is the lithium-lithium couple voltage, the 0 as a reference if you take. That is the anode. If you have a lithium foil, it is a 0. In half cells, coin cells, you use lithium foil and start looking the voltage of cathode, what you are using. If it is LiFePO4, it is 3.2 volts versus lithium in a coin cell. But in the real big cell, you cannot use lithium because it's very difficult to handle it. So people use graphite. Graphite is very close to lithium. You can see 0.2 or 3 volts, which is very close. And you can use graphite to store the lithium because through intercalation, and use this as anode, then you will have 3 volts of the battery with graphite and LFP. And if you use lithium nickel cobalt oxide, which I'm showing is a NCM, and that has 3.5 volts too. You can change the nickel content and go up to more than 4 volts. Then your voltage is very high. But always you can see the shades of the red. The red shades are the ones which are going to be a dangerous level. Graphite is also not so excellent, but the thing is, graphite has got a good property that when you charge the battery, first few cycles, it will start forming a SEI layers, solid electrode interface, solid electrolyte interface layer, SEI layer. That contains lithium carbonate and a lot of inorganic material, which forms a very thin layer on the graphite electrode, which does not allow any more current to pass it, but it will only pass the lithium ions, and then current will pass only through the external circuit, and this will act as a barrier for that one. That's why formation, when you do the battery, you will stable, very thin layer of SEI is formed during the formation cycle of battery. So that's how graphite is still safe. That's what we are using. But cathode side, the moment you start using lithium cobalt oxide or the bigger ones, you are going to the red zone. That means even you start seeing some kind of chemical reactions, even on the cathode, on some SEI formation, when you have the high voltage cathodes. So it is, people are looking, including Tesla, to look into lithium iron phosphate, because in the white region, there is no big danger with this, as long as used as cathode, and anode still graphite, because already well established with the SEI protection. But if you want 100% safe battery, you better go to LTO LFP battery. It only gives 2 volts, but both are in white region. LTO gives very fast charging, but you need to have more number of batteries. So in people who wants public transport or small range, they can still use, or in the fast charging stations or small electric vehicles, they still want to use. So these are the technologies are evolving based on the future needs. Whether you want a safe, it can change. It is not that you cannot use NCM. You can use NCM battery for Tesla. If you want a high-speed Tesla Model S, you still have to go with that. But as long as you have a nice battery management system, it always helps. It sees the health of the cell and it cuts off the overcharging and all, and discharging, and it safeguards. But even in India, the components of battery management system, MOSFETs and all electronic, they're also imported. So you will compromise on everything. So indigenizing the technology of electronics, battery management system, materials, all these things have to evolve over the time of way forward, 10 years. Otherwise, we're not going to win. So these are the chemistries of the battery materials, what you choose to get, what kind of batteries, and it is all happening today. We're talking about electric vehicles, all the electronic gadgets, just because of this man, J.B. Goodenough, who got Nobel Prize sometime back. And then he first invented lithium cobalt oxide and showed that lithium battery is possible with petroleum coke as anode. Sony made the first cell based on his invention. Now, even lithium iron phosphate, he only invented, but lithium iron phosphate, although it is very safe and iron is very cheap, all this is fantastic, but it is an insulating, it's not electrically conducting. If it is not electrically conducting, you cannot use it as an electrode. But if you make it a particle coated with carbon, that carbon will do the job. You can see here the nanoparticles of lithium iron phosphate can be coated with graphite, and then they take the current. When the charge discharge happens, the electrons flow through the current collector, which is graphite here, cathode, and that will take away. So you also need nanotechnology plays a great role here, because if you have a big particle, when you discharge, the lithium comes back into the lithium iron phosphate or whatever it is, and it has to travel all through the bulk. So this diffusion length, if you cannot change the diffusion coefficient, but you can change the diffusion length so that for the same volume, if you have more number of particles, then you will have, just let me, So if I have hundreds of particles for the same volume, then the diffusion length of this particle is small, so it quickly gets charged or discharged. So that will make it possible. So your acceleration also, drive will be faster when you use in car. So nanotechnology has great role. Here you can see in Tarascon's paper, where if you use submicron particles, you cannot get full charge. It is only 50 milliamp per gram, while 170 is a theoretical value for LiFePO4. But if you use nano, you can go up to 150. If you use further modify with carbon, nano, all these combinations. In fact, we get more than 160 milliamp per gram at C/10 ratio rate. So we made the materials at lab scale, and then some of our students published papers, then got PhDs, and then transformed to a technology of very large scale and compared with the imported ones. And now today the technology is ready. And then very recently, 1 month back, we transferred this technology to Alox Minerals, one Indian company, Hyderabad-based company, who has the access to the sources of lithium carbonate from Bolivia. And then, in fact, they gave 50 kgs of lithium carbonate, and then we showed that carbonate-based lithium iron phosphate, what we made, is on par with the imported ones. And then they took the technology, and they're going to set up a plant for mass-scale production. And when you make any material, it is a production, it is a usage, it is user-friendly, worker-friendly, large scalability, and yield should be very high. All these play an important role, in addition to the equipment what you are using. So what we did is, we were using initially 100 lakhs, 1 crore machine to mill the raw materials to homogenize. Then the cost was a little bit up. And then what we did is, to reduce the cost, we use Indian-made treaters, and you can see that is only 3 lakhs. So for 3 lakhs, instead of 100 lakhs, we got the same properties of what we made with the imported one with the Indian one, and then we got excellent properties. And the cost is drastically coming down, which means that when you use indigenized equipment in your biryani, the cooker I was talking, here, when I use the Indian cooker, then my LFP cost will come down without compromising on the properties. So that makes the easy adoption of the technology. In fact, we did this at 20 kg level at one company. This Inomet, this man, we are signing agreement with him. They have a powder metallurgy company where in Hyderabad, they have all the facilities of attrition and then pusher furnace and all. At 10 to 20 kg level, we demonstrated on their practical facilities. We showed that the material what we make at that level is on par with what we make in the lab. And then we demonstrate. Then the Alox Minerals, the other company, took this technology. Now they are tying up with this company to make the plant because these people know how to make these treaters and all. So then the technology was transferred to this industry. These are the people who are the technology receivers. He is the principal secretary of our Hyderabad, Telangana government, and our team is here. So this was done last month, and I'm talking about another material. I told anode. In the material part, I said if you use anode instead of graphite, lithium titanate, that will give excellent, is safest material. But the thing is that it will only give around 1.9 or 1.8 volts. So you need to have more number of batteries to get equal number of voltage of 48 volts compared to LFP graphite batteries. But if you see TOSA, which is a public transport company in China, not in China, Switzerland, they use LTO batteries, not with LFP, but with lithium nickel manganese oxide, but the voltage is only 2.5, but this is for the fast charging. Lithium titanate when used, the charging is very fast and temperature sensitivity also very low. That means even it works at low and high temperatures also up to 60, 70 degrees centigrade. So what we did is initially my PhD student was doing nano lithium titanate to see its performance, because when you make nano, diffusion lengths are smaller and performance is better. So you can see here that at 10C rate, when she made this donut vada type lithium titanate, and she was getting almost 100, whereas the commercial one, which is submicron, at 10C rate only 30 milliamp hour per gram. So almost 3 times we increased by just making the shape into this. So this was published in small in 2014 itself, but then we cannot make nano vadas donuts in large quantities because it's done by electrospraying, but we started working on optimizing our parameters, and finally we made LTO at 200, 300 nanometer size, and then we got very flat charge discharge curve with very good performance, and then we made some batteries and then we again scaled it up, and now the LTO technology is also ready for transfer, and then we're going to publish in open media for the call for the licenses in maybe a month's time or so. Now, having said that, down the line, 10 years or 15 years, we have to live with lithium-ion batteries because they are the best energy storage devices. But in future, you need to see for the alternate technologies, whether it is a sodium-ion battery is one option. Already Faradion company has come up with the battery cells with sodium-ion, but still some challenges are there. But more or less in next 5 to 10 years, that technology also will take up. Then the scaling up and then mega plants and all that will take another 10 years. But there is a mature technology without lithium, that is a supercaps. And supercapacitors, Maxwell is a pioneering company, and then you also have Chinese companies. You can buy supercaps, but supercap is the one where you have anode and cathode. Where is that? You have negative and positive electrodes. Both are carbon electrodes, because why you use carbon? It should be a conducting electrode, but carbon is highly porous. So your effective surface area per a given geometric surface area is very huge. So you can have high storage of the charge because more number of ions can sit on the surfaces, which means that epsilon A by D, C is equal to the A is increasing. So my C, capacitance is increasing. You can go up to 3000 farads. In your microelectrons, you only microfarads only. There are small capacitors, what you see in your PCB boards. But here, we're talking about the thousands of farads. So when you convert to energy, half CV square. C is the capacity, V is the voltage. So you can use a electrolyte, a solvent which is organic, so that you can have more than 2.5 volts stability. If you use water, by the time you go to 1.8 volts, water starts decomposing. So you cannot charge your capacitor more than 1.5 volts. But in this case, you can go up 2.7, 2.8 volts if you have organic electrolyte like acetonitrile or propenyl carbonate, which has got wide electrochemical window, potential window, and you use some electrolyte salt, and then ions will go in the opposite direction when you charge it, and then you have a excellent. But the thing is, even with the best super cap, you still have 5 times smaller energy density because it's a surface energy storage, unlike in lithium-ion battery where you have the bulk energy storage. So you cannot ride a car of 100, 150 kilometers with super caps. If you want to run, you can still do, but you need huge number of super caps because super cap, the voltage comes drastically down. And if you have 48 volts motor, use a super cap pack, in maybe in a few minutes or few 10 minutes, the voltage comes down, and then the moment it comes 48 or 47 volts, your motor stops. Still your device is active, but your motor cannot take any more. So otherwise you have to use boost converter to keep the voltage up for some more time. That all is there. So if you use you cannot use in car, but you can use in a bus, public transport facility where it only goes few kilometers. Every 5 or 10 kilometers you have a bus stop. So you have this connector coming and then touching the cable at the bus stop and getting charged. And super cap gets charged very fast in minutes or seconds, depending on its volume. Unlike hours in the case of battery. So by the time passengers get in, get out, your vehicle is fully charged. And go to the next bus stop and do so. So this is what is the advantage of that. Or you can use it as a regenerative braking in heavy vehicles. If you have a battery or even combustion vehicle, when you want to recover the energy of when you apply brake, sudden brake, there's a huge energy loss because so big momentum you're stopping, and that energy can be restored by fast charging. You cannot use in battery, but in super cap, that's a regenerative braking vehicles, they use super caps. And super caps also can be used in some of the wherever you need a surge power delivery is required, that you can, like a flash, right? In flash, what is the capacitor charges and gives very high flash, but very quickly it dies. But in super cap, it can sustain for a longer time. So, so the difference is that it is like a battery is energy, and then high power is a super cap. It is a long range athletes and the short range racer. And then already in China it is there, and several countries, Switzerland, China, Poland, and all, they're using that. But in India, no one. Still you are playing with the battery and super cap. Some institutes are working on that, but the technology is a tabless welding is required to, if you want to go beyond 500 farad. And then nowhere in India they have the technology. We have developed that, and then we made the tabless technology, and then made that we are able to do more than 1,000 farad that is required for electric vehicle. Okay. So we made the battery bio-waste material in large quantity, carbon, and then in fact we made petroleum coke based. HPCL has given a lot of money to use their petroleum coke waste material, which has got more than 80% is the carbon. And we activated and then make a graphene like carbon, and then made big quantities and made in the form of a device of more than 1,000 farad, and then see that we're on par with the commercial one like Maxwell or something else, chain, and then we're on par with that, and then we could get a good battery. You can see in the bottom, ARCA and then commercial one were very much similar to 1,200 farad capacitor on par. That means the first time for an EV, we're able to demonstrate in India that we are capable of making super caps on par with a global product benchmark. And we have a pilot facility to make. And then here also one in-house design of this flattening machine, which is very critical for the tabless welding. That was missing because when we imported, we forgot this because we didn't know about this, because all battery people, they don't even know this. But what then we did is we started looking into some diagrams and then literature and all. Finally, we got it made in Hyderabad, and we could make it to flatten the both anode. After this, you have to flatten both sides and then make the jelly roll and then make the batteries super cap. So the 60 lakhs machine In 3 lakhs, we could make it. That motivated us that now we are going to think of making even the machines for the battery line should be made in India. We're already working with some companies to do that. I think this is our team and all, and we have a lot of encouragement from several groups, and then awards are there. This is a supercap bicycle totally driven by our supercapacitors, no lithium at all, but it doesn't go for 10 kilometers, it only goes 2.5 to 3 kilometers, but it's a good demonstration we're done. And we got awards for our technologies, and I acknowledge scientists, engineers, technical support, students, and DST, HBCL, NSTL for their money, and Inamet, who actually demonstrated in a practical company industry scale for our materials, and we also have MOU with them. And all these are required. Just with one set of people, it's impossible. So thank you so much for your listening. Bye. Stop share.
I think that's a very eye-opening presentation to us, because everybody, whoever is doing research, they should know at what TRL stage we are doing and what is our focus.
Yes.
And we are very glad to see the ERCA developments in the battery, starting from the precursors, because today, well, we are seeing under self-reliant India, the chemical industry is getting booming up, but every researcher has to realize that my contribution is directly should be, to the Indian government, Indian scientific organization. Sorry, since we are running out of time, maybe one or two few questions we request you to take.
Sure.
Well, one Akanksha, she asked, in near future, can batteries be completely replaced by supercapacitors?
No, I don't think so. Because as I told you, the supercapacitors have got lesser energy density but high power density. So you cannot use it in your long driving cars or buses, only for the public transport. But not in near future, but mid future, maybe 5 years or more. This is called lithium ion capacitor, where one electrode is lithium ion battery capacitor material, other is the high active capacitor electrode. But that will give the high power density energy, but still not competing with the lithium ion battery. I really don't see so much about that. Why? Because again, if you put lithium into lithium ion capacitor, you still depend on the lithium. So what is big about that? So supercaps should be taken as a supporting system for electric vehicles. For example, if I go to Varanasi, I see all their electric auto rickshaws are lead acid batteries, because lead acid will give enough energy, driving range of 30-40 kilometers, enough for a city, and then it will give 30-40 kilometers per hour, enough for a driving into the city to taking passengers. But whenever you have a flyover or whenever you have a speed breaker, the guy keep rising the accelerator, you are drawing so much current from the battery, and lead acid battery will get abused and it will die in no time. If you have a super cap, and whenever you need a high power for a ramping or for a speed, then your BMS will switch out to super cap for short time. It will take care of that, and again when it comes smooth, so your battery is protected long time. So some of this, and similarly, I also told that whenever you have a regenerative braking, you have a heavy truck that is stopped, but the energy can be quickly gets charged through the super cap, and then that can be used again for your lighting or something. So there are, and quick charging stations, electric stations, where you need to have quick charging station. There also you need to store the energy and then release the energy very fast. If normal batteries cannot do. So a lot of applications are there in addition to this short range electric vehicles like electric bus. Thank you.
Sir, there are many questions. Even myself, I have a couple of questions, but I am unable to ask because another speaker is waiting. Probably
sure.
If somebody is interested, they can contact you. If you
Sure.
don't mind, maybe,
They can write to me.
Okay. Thanks a lot, sir, for accepting
so
the
much.
invitation and sharing your insights into the battery research. We are very glad to see the results. Thank you very much, sir.
Thank you so much. I'm signing off.
Yes, sir. Sorry, Kiran. So I think
no worries. Anyway, for the information to the participants, SAR will be joining tomorrow evening for the valedictory function to distribute the Research Excellence Awards, Best Poster Awards, and Best Oral Awards. So at that time, if you have one or two questions, maybe he can answer there also. Thank you.
I think that's a good information. Yes.
Yeah. Okay.
So thank you. I'll probably take over from here, and we can have the final keynote talk of this session before lunch. So I am very happy to introduce Professor Narasimhan here, who will be delivering a talk. And Professor Narasimhan is a professor of mechanical engineering at the Indian Institute of Science, Bangalore. He received his BTech in mechanical engineering from IIT Madras in 1982, and then he pursued his MS and PhD from Caltech. And after that, he joined IIT Bombay as a faculty in 1987 and subsequently moved to IISc Bangalore in 1991. Since then, he has had several visiting faculty positions at Caltech, Royal Institute of Technology, Stockholm, and NUS Singapore. He is also a highly decorated professor. He is an elected fellow of the IASC, INSA, as well as INA. And he was also awarded the prestigious Shanti Swarup Bhatnagar Award by CSIR in 1999. So coming to his expertise, because his list of laurels are many, and if I keep going, I'll take the entire time. Let me talk about his research interests, and he is specifically an authority in the field of solid mechanics and mechanics of materials, in particular nonlinear and dynamic fracture, mechanics of indentation and deformation and fracture of bulk metallic glasses, shape memory alloys, and HCP. So I request Professor Narasimhan to please switch on his video, or if he prefers that, and go ahead.
Okay, thank you very much, Lakshminarayan. And thanks to you and the organizers for inviting me to give this talk. Unfortunately, my camera doesn't seem to be working this morning, so I cannot show my face, but hopefully my audio is clear. So
Yes.
let me share my screen and start my talk.
Sure.
Okay, are you able to see my screen?
Yes, it is visible. Yeah.
Yeah, okay. All right, so I'm going to talk to you about how do I actually get rid of the small panel at the top that
you can move that.
Okay,
and
yeah.
you can share your full screen.
Okay. I want to share my full screen. It's sort of interrupting in the middle.
Right.
Yeah. Okay. So, okay. All right. So I'm going to talk to you about tensile, the role of tensile twinning on the fracture behavior of magnesium. And before I begin, let me acknowledge my collaborators, my former PhD student Prasad, as well as Vaishak, who just graduated recently, and my current PhD student Arjun Sridhar, and my colleague from materials engineering, Professor Satyam Suhas, with whom I have been interacting for the last 8-9 years on this topic. In fact, I started working on this in 2013 with my master's student Kaushik, who later did his PhD at Brown, and now he's working at General Electric. The topic was introduced to me by Dr. Mishra, Raj Mishra from GM R&D, who's since then retired. But also acknowledge my collaborators from the Graduate Aeronautical Laboratories, Caltech, Professor Ravichandran and his postdoc Suraj, who helped us to do some of the dynamic fracture experiments, which I'll be showing. Okay. All right, so magnesium has been attracting a lot of attention in recent years, mainly because it's one of the lightest materials. Its density is very low, and it has got very high specific strength. And there are a couple of other good characteristics like good damping and also machinability characteristics.
Professor Narasimhan, sorry
Yeah.
to interrupt. You have not gone full screen yet.
I don't know how to remove that. That thing is,
F5,
I am in full screen,
okay.
but this small panel is coming at the top, which I'm not able to get rid of.
Oh, can you just go to that?
I think you can click resume slideshow. So there is a
where is that?
Just on the same tab.
Yeah, same tab. There is a.
Oh, it has disappeared.
I can't see that actually. I mean, it's got participants, chat, and share, but it doesn't seem to have anything else. I mean, I'm not able to get rid of this small. Maybe that is hiding the view because I'm on full screen mode.
I see, okay. But we are actually seeing your.
Okay, let me do this again. Okay, just 1 second. I know what's going on. Okay, just 1 second. Yeah. Okay, so let me again go into the projection mode. Are you able to see it now?
Oh, now, no, we are able to see the screen, but not full screen.
I don't know why the
You
top
can-
part still being hidden.
You can stop sharing and try to share again once.
Yeah,
Maybe-
okay, I'll do that. Stop share. No, it not seem to be going away. Stop share. Okay, I stopped sharing. So
Yeah,
let me
no.
try this again. I haven't used Zoom very much, so we're more used to Teams.
Now it is. Yeah,
Now it
great.
is clear. Okay, all
Yeah,
right.
we are full.
Okay.
It's perfect. Now.
Okay. Who can share something? All right. This has a lot of things coming in the middle. Sorry about this because I'm not very familiar with this and it's giving me a lot of small windows. All right. Let me tell a little bit about the slip and twin systems in magnesium. At room temperature, magnesium has got 18 slip systems and 12 twin systems, which I've shown here in the form of the slip plane and the slip direction. In the top panel, which consists of basal, prismatic, and pyramidal A slip, these actually cannot accommodate deformation along the C-axis. In order to do that, one has to activate one of the systems from the bottom panel, pyramidal C plus A or tensile or contraction twins. Now, these tensile twins, they actually cause extension along the C-axis, whereas the contraction twins lead to contraction along the C-axis. And there are also other characteristic differences between the two. The tensile twins, for example, can widen very rapidly and they can engulf full grains, as we're going to see in my talk a little bit later. On the other hand, the contraction twins are narrow and the lattice rotation is much higher in the case of the tensile twins. I have also indicated the number of such systems for each category. For example, basal is 3 and tensile twins, there are 6 variants and so on. And also the CRSS values corresponding to magnesium single crystal. So you can notice here that the basal slip and the tensile twins, they are soft deformation modes. They have low CRSS values. On the other hand, if you take a look at pyramidal C plus A and contraction twins, those are hard deformation modes. The CRSS values are much higher. In particular, note that there's a very large variation in the CRSS values, and that is one of the reasons why magnesium is highly anisotropic. Okay, let me motivate my talk by showing one important result from the literature, and this is from the work of Amin Benzerga. They did experiments with tension tests with smooth and notched round bars, which are cut from an AZ31 magnesium alloy plate. And what you see at the top are the fracture surfaces from their tests corresponding to a sharply notched RN2 specimen, which has got a triaxiality T defined as a ratio of hydrostatic stress to equivalent stress of 1.5. And you can observe basically brittle features like elongated grooves or splits. On the other hand, when they worked with a shallow notched RN10 specimen, which has a triaxiality of 0.8, it shows ductile void growth and coalescence. So there is a transition in the failure mechanism from quasi-brittle to ductile as the triaxiality reduces. And that has its implications on the failure strain as well, which is plotted on the bottom figure, bottom left figure here. And you see that the ductility is almost 35% for the triaxiality of 0.8, and it drops with increase in triaxiality. Now, let me frame the objectives of our work. So since twinning has been shown to play a very important role in affecting both the deformation as well as the failure in magnesium alloys, we wanted to understand its role vis-a-vis the fracture behavior more closely. So first, we wanted to look at magnesium single crystals and understand corresponding to different lattice orientations with respect to the notch direction, how the tensile twinning develops and influences crack initiation and crack growth. Next, we wanted to look at a polycrystalline AZ31 rolled magnesium alloy and look at here specifically the effect of notch root radius. By varying the notch root radius, we can vary the stress state or the triaxiality near the tip, and also the loading rate by conducting both quasi-static and dynamic experiments. And again, the focus is on how twinning develops and how the fracture behavior changes with respect to these parameters. Finally, time permitting, I will tell you a little bit about some crystal plasticity simulations which we have done, trying to understand wide growth and coalescence in magnesium single crystals. Now, let me first show you some results from our single crystal tests. These were conducted using 3-point bend specimens, which were tested inside an SEM stage. And these experiments were done in the Warren labs of General Motors. So we had provision for in situ SEM and EBST in these experiments. The dimensions of the specimen are shown at the bottom, are indicated at the bottom there. And we considered basically 3 orientations. In orientations A and B, the C-axis is along the normal to the flat surface of the notch, but the direction of crack propagation and the crack front direction, they are switched around. Whereas in the case of orientation C, the C-axis is along the thickness direction. And this has a very important bearing, as you will see on the results. This shows the EBST maps as a function of loading corresponding to the orientation A, where remember the C-axis is along the normal to the flat surface of the notch, as indicated in the schematic on the left side. The bottom left side picture shows an IPF corresponding to the as polished specimen, indicating basically inverse pole figure, showing basically a strain-free surface. Now, as you load up the specimen, the panel on the right shows the image quality maps, and the twins here are the tensile twins, the 101 bar 2 twins, are identified by the red lines over here. So very early in the loading process, twin nucleates, W nucleates at the notch root. And as you increase the loading, more and more twins will start nucleating further away from the notch root. They start intersecting with each other, and they start impeding the development of twins. So there's a lot of interaction between twins that happens as the loading increases. In fact, some of the early twins, their width increases and then they saturates at around typically about 140 microns or so. In the case of orientation B, where also the C-axis was perpendicular to the flat surface of the notch, the pattern of twin development was similar, starting from the notch root and then emanating out. On the other hand, when we looked at orientation C, which is shown at the bottom over here in the slide, where the C-axis is along the thickness direction, twinning actually starts at the far edge of the specimen and then it enters into the specimen towards a crack tip, towards the notch root. But there is a region near the notch root which remains independent of, which is free of twins even at later stages of deformation. Now, one of the things that we wanted to do here is, do these twins actually persist through the thickness, particularly in the single crystal specimens? So therefore, we actually chemically etched and polished the specimens down to the mid plane and the quarter plane, as well as on the free surface. And what I have shown on the top, a panel of image quality maps for orientation A from an unloaded specimen. And one notes here that in all the 3 planes, the pattern of twinning is similar, emanating out from the notch root. And some of the twins, like the one I have identified by W here, seems to persist all the way through the thickness of the specimen. On the other hand, when we look at the bottom panel for orientation C, there is more intense twinning on the mid plane as compared to the free surface. It's not very much different. It's about 10, 12, 15% higher in the mid plane as compared to the free surface. Now let's take a look at optical metallographs, trying to understand the slip and the twin traces. So this is for orientation B. And if you look at the left top figure, you basically see 2 traces. One is a basal slip trace, which I've identified as S1, and the other is a prismatic slip trace, which is identified as S2. Also, we notice that there are 2 families of twin traces which are intersecting ahead of the tip. And the zoomed in view of the extended crack is shown on the right side top picture. And you can see that the crack has initiated from the notch root. It's growing along a twin trace. And then at a twin-twin intersection, it deflects, basically resulting in a zigzag sort of crack propagation. Also, if you follow some of the slip traces, for example, a basal slip trace, which in the right top panel I've identified as KJIH, you can see that there is a deflection by about 90 degrees inside the twin. And therefore, this suggests that there is secondary slip activity inside the twins. So in all the experiments, the crack initiates before the peak load, grows stably along a twin boundary, and then it deflects at twin-twin intersections. One can see that more clearly on the bottom left figure here, which is an SEM image, and you can see the crack deflecting as two segments, MN and NO, and there is also a forking of the crack into two segments, NP and NO. The right side bottom picture shows an SEM fractograph, and we basically see some intriguing patterns of elongated stripes, which we believe are caused by intersection of twins of the other variant on the fracture surface. We also quantified the evolution of the twin area fraction with respect to load, and that is shown here as a plot corresponding to different orientations A, B, and C. And this is done within a square region about 900 microns, which is indicated on the top left image here. The right side top plot shows the energy release rate plotted against load. Actually, one sees a qualitative similarity between the evolution of twin area fraction near the notch root and the evolution of the energy release rate with respect to load. In particular, see that orientation A and B are evolving in a similar way. Only thing is, in the case of orientation B, the twin area fraction starts with a finite value, because in this case, unfortunately, all the specimens which we tested had polishing twins, and these polishing twins impeded subsequent twin development and led to early fracture of the specimens. And that's why you can see here the twin area fraction saturating early, and also the JC value, the crack initiation value, which is indicated by the open circles, is low in the case of orientation B. The main point here, which I want to emphasize, is the similarity in the twin area fraction development, the evolution history, and that of the energy release rate with respect to load, which suggests that tensile twinning is an important dissipation mechanism and can lead to enhancement in the toughness. We'll see more of it a little bit later in this talk when we look at polycrystal specimens. We also conducted complementary finite element simulations using crystal plasticity in order to gain a little bit more insights about our experimental results. So we used the classical crystal plasticity framework developed by Asaro and Rice and modified by Kalidindi and Starasolsky and Anand to incorporate twinning as a quasi-slip process. The kinematics in both the cases involves a multiplicative decomposition of the deformation gradient into an elastic and a plastic part, Fe and Fp. In the Asaro-Rice framework, the Fp part embodies plastic shearing along the crystallographic slip systems, whereas the rotation and the stretching of the lattice are vested in Fe. On the other hand, in the Kalidindi framework, Fp takes care of both slip in the untwinned region, called as primary slip, as well as twin in the untwinned region, called as primary twin, whereas Fe again takes into account the rotation and the stretching of the lattice. The flow rule is written for the plastic part of the spatial velocity gradient, F dot P, Fp inverse. And as you can see from the equation at the top, it involves contribution from slip in the untwinned region, the first term on the RHS, and twinning in the untwinned region, which is the second term in the RHS. Now, in the equations, some of these quantities are familiar quantities. S is the Schmidt tensor, gamma is the plastic slip, gamma TW represents the twinning shear, which is indicated here about 13% for both TTs and CTs, and F alpha represents the twin volume fraction. The macroscopic Cauchy stress also involves contribution from the untwinned region and the twin region, as you can see in the equation in the middle. We made use of phenomenological hardening as well as evolution laws to describe slip-slip, twin-twin, and twin-slip interactions, which were given by Zhang and Joshi. And as suggested in their work, we benchmarked the material parameters in the model by comparing against the channel die compression experiments of Kelly and Hosford long ago. And these were done corresponding to 6 different orientations. So we used that to benchmark the material parameters. Now, here is a view of the in-plane finite element mesh. The finite element modeling was done with 3D 8-noded B-bar based hexahedral elements, and half the mesh through the length and half through the thickness is modeled because of crystallographic symmetry. 7 elements are used through the half thickness, with the element layers getting increasingly thin as you approach the surface of the specimen, because there is a stress gradient as you get to the free surface. The in-plane view of the finite element mesh, a zoomed-in view, is shown on the right side bottom figure here. These are load displacement plots corresponding to the three orientations. I have compared the FEM predictions, which are indicated by the solid lines, against the experimental data, which is indicated by the broken lines. In all the cases, we see that the behavior is like bilinear sort of response. And we found that this is true even in the polycrystal specimens, which we tested. There also the response seems to be like sort of a bilinear sort of response. And we noticed that there is a good agreement between the experiments and the simulations, except that the experiments show a lot of serrations. And these serrations from the in situ observations, our ICAMMC observations, we could make out that whenever there is a serration here, it coincides with the nucleation of a twin. So, and that means that there's a sudden increase in the tensile strain, which leads to an abrupt drop in the load. But this is not captured in the simulation, because the simulation does not model discrete twinning, and therefore the curves are smooth. The load displacement curves are smooth. These are contours of twin area fraction corresponding to two orientations. Orientation A, where remember the C-axis is along the normal to the flat surface of the notch, and orientation C, the bottom panel, which corresponds to the C-axis coinciding with the thickness direction. Now, the top image, left image, is taken on the surface of the specimen. The notch you can see on the left side, bottom, and the right one is on the midplane of the specimen, whereas the extreme right image shows the twin area fraction contour, twin volume fraction contours taken on a section through the thickness. You take a section ahead of the crack tip, ahead of the notch tip, and it's plotted on that, going from the midplane on the left side to the free surface on the right side. One can observe here that twinning is developing out from the notch root in the form of a rectangular region, and there is not that much thickness dependence in the case of orientation A. In the case of orientation C, the bottom panel, we see the twin area fraction developing at the far edge of the specimen and propagating inwards, leaving behind a region near the notch root, which is free of twins. On the other hand, as opposed to orientation A, we see a little bit more thickness dependence in the twin area fraction development, with higher twin area fraction in the midplane compared to the free surface. And all these features are in good agreement with what we saw in the experiments. We in fact went a step further and we quantified the twin area fraction by considering a rectangular region around the notch root. And that is plotted here corresponding to all the three orientations. And the experimental data is also superimposed. And we see actually a fairly good comparison for orientation A and C between the experimental data points, which are the symbols, and the continuous lines, which are the simulation data. But in the case of orientation B, on the other hand, as I indicated earlier, there were some polishing twins in the specimens that we tested, which sort of impeded twin growth and led to saturation in the twin area fraction in the experiments, which was not captured in the simulation. So the simulation shows further evolution of twinning. Now, an important issue which we wanted to understand in the experiments was, why do these twins grow along the twin boundaries and why do they get deflected? Why not go along the twin boundaries continuously? It's been seen that this sort of intersection takes place in all our experiments. Now, in order to understand that, we decided to take two of the twin variants, which I am going to call as twin variant 1 and 2, as seen in the experiments corresponding to one of the orientations, orientation A, incorporate that in the finite element model, and then do crystal plasticity finite element simulations. Basic idea here is to look at how the plastic slip develops, as well as, more importantly, how the energy release rate evolves, corresponding to two different crack propagation scenarios. In the crack propagation scenario 1, we take the crack to propagate. So the initial crack is along the twin boundary 1, indicated as OA, with the crack tip at A, indicated by the vertical arrow here. In case 1, we take the crack to extend along that boundary without deflection, whereas in case 2, we allow the crack to deflect and then the tip is located at point C. So we do detailed energy release rate calculations by taking the rate of decrease of strain energy with respect to crack advance. So here I show contours of equivalent plastic slip corresponding to the initial configuration where the crack tip is located at the intersection point between the two twins. And the right panel is for the right picture is for case 1, where the crack tip is now extended along the twin boundary without deflection. Now, in both cases, one can see a lot of plastic slip accumulation at twin-twin intersection. In fact, an interesting point, if you look at the right side picture, is you see more intense strain concentration at the twin-twin intersection as compared to the crack tip. And that's very interesting. And also we see that there is more plastic slip inside the twin. So this actually correlates with, and most of this is actually basal slip. And this correlates with the slip traces, which we saw inside the secondary slip traces, which we saw inside the twins in the optical micrograph I showed earlier. These are plots of computed energy release rate versus load corresponding to the two cases which we considered. Remember, case 1 corresponds to the crack extending along the twin boundary without deflecting, and case 2 is where the crack deflects. So the energy release rate clearly shows that it's much higher for case 2 as compared to case 1. In fact, if you go up to a load point displacement of about 0.25 millimeters, it's almost double for case 2 as compared to case 1. So this suggests from an energy standpoint, deflection of the cracks at the twin-twin intersection is going to be favored. Now, let me summarize the key takeaways from this part of my talk on magnesium single crystal. We noticed that there is profuse twinning occurring ahead of the crack tip in all the geometries. The crack grows stably along the twin boundary and deflects at twin-twin intersections. And the tensile twinning is profuse in all the cases, and it correlates with the evolution of the twin with the energy release rate, which suggests that twinning is an important dissipation mechanism. Now, let me show you some results from our polycrystal experiments. And these are conducted with AZ31 magnesium, rolled magnesium alloy, having basically a basal texture, as you can see here. And experiments were conducted with compact tension specimen and 4-point bend specimens, about 10 mm thick. And the 4-point bend, we also used both fatigue pre-cracked and EDM cut notches, different notch root radii, in order to understand the effect of the notch root, notch size. So the pole figure shows a nearly basal texture, except that we found that in the midplane, there was a little bit more closer adherence to basal texture as compared to the free surface. The average grain size about 14 microns in this alloy. Now, here I show the twin pattern development. The right side schematic at the top is stitched together by considering several optical metallographs, and it shows profuse twinning all over the specimen. For example, very near the tip, indicated at A, and point B at the far edge of the ligament, as well as above and below the notch root. The left side pictures are the inverse pole figure maps. The top panel is at the point A in the midplane of the specimen, and on the surface is in the middle. So you see a lot of twinning here, and in fact, in the surface, you see more twinning as compared to the midplane. And in fact, in the midplane, it seems to be present only in very large grains. Also, we see a lot of interesting features like twin-twin intersections, twin coalescence, and twins, multiple twins of the same variant. And in fact, in some of the pictures, you can see twins forming as chains cutting across twin boundaries. The bottom figure shows the on the free surface on the point B, and you see profuse twinning. So all these suggest significant dissipation due to twinning over the entire ligament. These are optical metallographs corresponding to the notched specimen, corresponding to different notch root radii, and the fatigue pre-cracked specimen, FPC, at the bottom right side. And all the images, we see the grains around the tip carrying twins, multiple twins in some cases. I'm going to call these as anomalous twins because from the standpoint of the stress state, these twins shouldn't be there. Why exactly they are there, we will try to understand that a little bit in the subsequent slides. But an important observation is that as you decrease the twin, as you decrease the notch root radius and go from 175 microns to the fatigue pre-crack, we found that the average twin area fraction increases from about 4% to 14%. So we did metallography quantitative metallography by considering different 100 micron square regions, and then evaluated the twin area fraction in these regions and found that there is a increase in the twin area fraction as you go from notch to the highly notched specimen to the fatigue pre-crack. Also, if you observe these images, for example, the top left panel, you can see oblate voids which have labeled as P and Q, which have nucleated in front of the crack tip, and they are about to coalesce with it. These can also be seen in some of the other images, but an interesting point in the fatigue pre-crack specimen on the bottom right is you see a slit-like void, W. And if you observe carefully, this seems to be parallel to some of the twins. So these are possibly twin-induced cracks. And let me briefly tell you about this anomalous twinning. Why do these twins actually form? This was investigated in detail by Koike's group, and they actually conducted experiments with the AZ31 alloy tension test. And their important observation was that in grains which have their lattice slightly tilted from the ideal basal orientation, the C-axis slightly tilted, as you can see on the IPF on the left side, those grains actually carry tensile twins. And that one can make out from the right side quantification of the fraction of twinned grains against the Schmidt factor for basal slip. So in fact, there seems to be a correlation between the two. So the higher the Schmidt factor for basal slip, you see higher tensile twins. So the model which they proposed was shown at the bottom here. So there is excessive basal slip in the tilted grain, and that leads to pileup of basal dislocations at the grain boundaries of these twins. And that creates a sort of a stress concentration at this boundary, and it can nucleate twins. That stress concentration nucleates twin, and it leads to stress fluctuations, and it nucleates twins inside the tilted grain. So this we actually investigated by doing CPFE simulations, and I have shown here some results from this crystal plasticity simulation corresponding to tension. And the central grain is tilted from the C-axis. It has a tilt of about 30 degrees. C-axis tilted from ND by about 30 degrees. All other grains are in the ideal basal orientation. So you can see basal slip developing very early in this grain, and lot of stress concentration adjacent to it. In fact, if you track the stress concentration factor, you see a stress concentration factor of 2 in the adjacent grain. And that leads to a pronounced drop in stress inside the tilted grain. And in fact, you get sigma 11, which is negative, and that leads to CRSS, RSS for twinning, which overcomes the CRSS. These are the fractographs which we got from our experiments corresponding to different notch root radius and the fatigue pre-crack specimen. The right side is an X-ray tomograph image of one of the fatigue notch specimens. So there is a clear change in the fracture mechanism. In the fatigue pre-crack specimen on the bottom right side, you see elongated grooves or slits. These are possibly caused by twin-induced cracks. In fact, Gandhi and Ashby, who did fracture mechanism maps, called this sort of features as cleavage 3 regime. And these are actually brittle with some amount of plastic deformation. It's actually quasi-brittle. On the other hand, all the notch specimens show ductile white growth and coalescence. You can make that out clearly from the X-ray tomograph images. And there are inclusions sitting in many of the voids. These white, gray dots here on the X-ray tomograph, those are all second phase particles. And we did an EDS spectrogram and found that these are actually manganese-rich particles. One of the important observations which we found out by doing quantification of these void sizes is that the average dimple size increases with notch root radius from about 30 to about 40 microns. And in fact, that can be nicely correlated with the evolution, with the variation of the fracture toughness, notch fracture toughness with the notch root radius, which is plotted here. And one sees a very strong enhancement. I've also affixed the SEM fractographs in order to correlate the failure mechanism against the toughness. So the fatigue pre-crack specimen breaks by cleavage 3 and low toughness, lower shelf, and then it transitions to, as the notch size increases above 50 microns, it transitions to ductile white growth and coalescence, and larger void size are noticed, and there's a stronger enhancement. In fact, one can predict this entire trend by using the classical Rice and Tracy formulation combined with the Rice and Johnson theory. In fact, we did that in our EFM paper, and you can see that's a very nice agreement between the model prediction, the Rice-Johnson, Rice-Tracy model prediction, and our experimental data. Now, let me show you a few results from our recent work just published in ACTA this year, where we looked at dynamic fracture of AZ31, rolled AZ31. And these experiments were conducted in Professor Ravichandran's lab, Guggenheim Aeronautical Laboratories. And we did these experiments using Hopkinson bar setup, which is shown on the right side here. So you can see the gas gun on the left bottom, and then you have the striker bar, the incident bar, the striker bar, and the specimen at the far end of the specimen. Can make that out more clearly in the image at the bottom, the photograph at the bottom. You can see the specimen fixed to an anvil, and the incident bar just about touching the specimen. And a high-speed camera, Shimazdu camera, which can take more than 1 million frames per second, is used to image this specimen. And we use in all our analysis, we use DIC in order to figure out the strains and the displacements on the specimen. We also did quasi-static tests using our own servo-hydraulic machine at IISc. 4 impact speeds were considered, ranging from 9 to about 20 meters per second. The image on the left side here shows the strain development in the specimen corresponding to a test conducted at 20 meters per second. These are the vertical strain or the bending strain. So very early on the loading history, we see strains developing, normal strain developing at the far edge of the specimen. And then as your time progresses, we see strain developing at the notch root, becomes very intense at the crack initiation stage. And we have a typical bending strain distribution developing on the specimen, going from tensile at the notch root to compression at the far edge of the specimen. The hinge point, plastic hinge point, located at about 40% of the ligament width from the notch root. The right side images are DIC images, strain image, vertical strain contours, epsilon YY, corresponding to the crack initiation stage for the static specimen and different velocities of impact from 9 to 20 meters per second. The key observation here is that with increase in loading rate, with increase in the loading rate, one finds more intense strain accumulation both at the far edge of the specimen as well as near the crack tip. So this suggests higher plastic dissipation with loading rate. Now, a very intriguing thing which we observed in our experiments is the way in which twinning develops in these tests, both in the static test and in the dynamic test. In all these cases, the far edge of the specimen, twins start developing initially in the form of fingers. In fact, we did some interrupted static tests, and you see these white finger-like patterns in the optical metalograph on the left. These are actually twin packets. And as your load increases, these twin packets widen and they also lengthen, and ultimately they merge with each other, resulting in a very large semicircular region which has completely twinned. In fact, in the bottom left picture, I show a schematic of the whole scenario. You see a large semicircular region with claw-like things like birds' claws, which are actually like twin packets. Now, are these really twin packets? We can actually do a detailed optical metalograph that's shown on the bottom here. We focused on one of these fingers, and you can see that within the red region here, you can see a chain of twins cutting across twin boundaries inside these packets. Now, if you go slightly outside this band, go to the top of it or go below it, you see a twin-free region. Okay, so it's a very intriguing pattern of twin development that happens in this specimen. We also did some EBSD maps, both near the crack tip and in the far edge of the specimen. And I've shown it here for 2 impact speeds, 9 meters per second and 17 meters per second. So near the crack tip, you see more twinning for the low impact speed as compared to the high impact speed. In fact, the twin area fraction drops from about 12% for the static to about 4% for 20 meters per second. The scenario is exactly the opposite when you look at the far edge of the specimen. In fact, near the loading edge, as you can see from the bottom panel, as you increase the impact speed, there is much more profuse twinning taking place at the far edge of the specimen. In fact, if you look at the bottom right panel, many of the grains have completely reoriented. Look at the pole figure. The basal poles, the basal poles have completely shifted out from the ND towards the TD and the RD. Okay, there's a 90-degree rotation of the lattice, about 90-degree rotation of the lattice taking place inside the twins. Okay, now this is an important plot which shows how the fracture toughness varies with respect to the loading rate. Again, we want to correlate the failure mechanism against the toughness. So I have superimposed the SEM fractographs corresponding to various specimens and tagged it with the corresponding toughness data so that we can make out what is going on here. So in the bottom left, I have for the static test, we see elongated grooves or splits, which are the cleavage 3 regime of Gandhi and Ashby taking place for the static specimen. And then as you impact it at higher speeds, you get ductile wide growth and coalescence. And in fact, the wide size increases as we saw in the effect of the notch size, then increase in the wide size with increase in the impact speed. There is a concomitant increase in the toughness almost by a factor of 3 as the loading rate changes from static to a J dot of about 10 power 6 Newton per millimeter second. Let's try to understand physically what is going on over here. So I have shown on the left side a cartoon which depicts the scenario both near the crack tip as in the far region. So if you take the fracture process zone near the crack tip, there's a lot of twinning that is taking place at low loading rates, and the intensity of twins diminishes as the loading rate increases, and the twinning is replaced by wides, and wide growth and coalescence takes over as the loading rate increases. And at the far edge of the specimen, there is more profuse twinning. So the combination of the brittle to ductile transition near the crack tip combined with more plastic dissipation at the far edge of the specimen results in this factor of 3 increase in the toughness as you go from the static to the dynamic. A more detailed model of this is shown on the right side. I don't have much time to describe this, but this is a plot of the JQ locus and a superimposition of that on the possible J versus Q trajectories corresponding to different loading rates in order to predict this sort of trend. Now, let me summarize this part of my talk by noting that the twin volume fraction near the notch root decreases with increase in notch root radius or with increase in loading rate, and this is attributed to drop in the stresses near the crack tip. And there is a concomitant brittle to ductile transition that takes place. On the other hand, the microvoid size near the tip enhances with increase in notch root radius or with the loading rate. And the twinning-induced dissipation at the far edge of the specimen is sensitive to the loading rate. It enhances with increase in loading rate. And JC, the toughness, enhances with notch root radius strongly as well as with increase in loading rate. Now, Lakshminarayan, have I run out of time? Then I will just stop it here. Or if you give me 5 minutes, I'll show you some wide growth simulations.
Please go ahead. Please go ahead, Professor
Okay. All right. So I'm going to switch gears and show you some crystal plasticity simulations, trying to understand wide growth and coalescence. As we saw from our notched experiments as well as high impact velocity experiments, there's a lot of wide growth and coalescence that takes place in magnesium. It's not completely brittle all the time. And this is I would say this is a misconception in the literature. Many people dismiss magnesium alloys as brittle. Now we beg to differ. We say that, oh, that depends on the stress state. It depends on, in fact, it also depends on mode mixity. We have done a lot of experiments on mixed mode, which I don't have time to show here. And again, it is sensitive to that. So don't dismiss magnesium alloys as just brittle. It depends on the state of stress. So it's important to understand how wide growth and coalescence takes place in these alloys. So we have done some crystal plasticity simulations. These are plane strain simulations, unit cell simulations done with cylindrical voids inside square unit cells with periodic boundary conditions. Crystal plasticity is used, and these are single crystal configurations. And we considered 2 lattice orientations. In orientation A, the C-axis is along the thickness direction. Orientation B, the C-axis is along the major principal stress direction. All right, so these are the equivalent plastic slip contours corresponding to orientation A, where note from the schematic on the top, the C-axis along the thickness direction. So for low lambda, lambda here represents the stress ratio, the ratio of the major to the minor principal stress, a minor to the major principal stress. So lambda 0.8 high triaxiality, you see that essentially prismatic slip is active in this case. It forms around the wide surface, and as the strain increases, it grows develops along the transverse ligament and the transverse ligament next. And note also the wide shape becomes highly oblate in this case. This is actually similar to what you see in isotropic solids. On the other hand, when you go for low lambda, low stress ratios, at a small strain, plastic slip develops in the form of an inclined band, like a shear band cutting across the cell. But when it goes to higher strain, again, the strain localizes in the transverse ligament, leading to coalescence by internal ligament necking. When you look at orientation B, we see a different picture. So in this case, the C-axis along the major principal direction. So here, unlike in orientation A, basal slip is initially active along with tensile twinning. So at low strain, this is for lambda 0.8, basal slip emanates out from the wide surface, and tensile twinning develops at the bottom of the cell, and then it spreads upward, as you can see in the bottom right panel, engulfing the entire right half of the cell as the strain increases from 5% to 15%. Once the lattice reorients, we trigger additional slip systems. Pyramidal C plus A and prismatic are triggered in addition to basal slip. And these are hard slip systems, and they can impart texture hardening due to their higher CRSS values. This is the scenario for orientation B, the plastic slip and tensile twin volume fraction corresponding to lambda 0.2 low stress ratio. So at low strain here, again, basal slip is initially active from the wide surface, and TT, tensile twins, start from the lower left corner, and then it goes up, develops over the entire right half, as you can see in the bottom right side. An interesting thing that happens here is, as your strain increases and as the lattice reorients over a major portion of the cell, pyramidal C plus A gets triggered, and that leads to shear bands, which you can see on the bottom left panel in the plastic strain plot, which actually cut across the diagonally across the unit cell. So the mode of coalescence, wide coalescence, actually transitions from internal ligament necking for high stress ratios to shear band induced coalescence for low stress ratios. And in fact, this is characteristic of plastically anisotropic solids. So people have worked with, for example, Amin Benzarga's group. They have done simulations with anisotropic plastic solids, and they have seen this similar sort of transition. But to my knowledge, first time we have predicted it for magnesium. These are plots of macroscopic mean stress and wide volume fraction corresponding to orientations A and B. So in the orientation A, the behavior is very similar to isotropic solids. So the mean stress, macroscopic mean stress increases, reaches a peak when the expansion of the void can no longer, when the hardening in the solid material can no longer compensate for the void expansion, and then it begins to drop. The peak stress diminishes with the drop in the stress ratio, which is similar to what we see in isotropic solids. And if you look at the wide volume fraction on the bottom, okay, so there's a retardation in the wide evolution rate as the lambda decreases. On the other hand, when you look at orientation B, where a lot of twinning takes place, initially the macroscopic stress evolves slowly, and as the part of the lattice reorients to harder slip systems, you see an abrupt increase in the mean stress. And again, it reaches a peak and then it begins to drop. An interesting observation which you can make out from the bottom right side image, bottom right side picture, is that if you look at the wide volume fraction evolution for orientation B, I have identified the pre-twinning regime and the post-twinning regime. In the pre-twinning regime, there is a distinct retardation in the wide growth rate. And this is associated with the hardening associated with twinning, because twinning can impart several hardening mechanisms, like, for example, twin-twin intersections, twin slip. It can act as barriers to dislocation motion, and it could impart twinning, and it could impart hardening. And that causes a retardation in the wide growth. And once it reorients, you see a rapid evolution in the wide growth rate. So let me summarize here the crystal plasticity simulations of wide growth. So in the case of orientation A, where the C-axis is along the thickness direction, predominantly prismatic slip, whereas in the other orientation, the C-axis is along the X2 direction, the major principal direction, basal slip and tensile twinning are initially active. Once tensile twinning develops over a large part of the cell, pyramidal C plus A and prismatic slip, hard slip systems get triggered, and hardening imparted by twinning can play a secondary role by retarding wide growth, as we saw in the case of orientation B, till the lattice reorients. And there's also an interesting observation from the simulations of wide coalescence transitioning from the traditional internal ligament necking to shear band induced coalescence when twinning is operative, as in the case of orientation be? So let me stop here, and I once again thank Lakshminarayan and Kiran and the other organizers for inviting me to give this talk. Thank you very much, and I would be happy to answer any questions you have on this talk. Thank you very much.
Thank you, Professor Narasimhan. This was a very nice talk, and I think the coverage as well as the mechanisms that you talked about are really interesting. I think I was also not aware of some of the latest work. I have seen the previous magnesium work when I was a student in IISc, but some of this is very fascinating. So I'll just kick off with a couple of questions, and then we can cut for the lunch break. So there is a question by Professor Long from Shenyang, and he says that so he's talking about high loading rates and low temperature in metallic alloys that generally promotes twinning.
Right.
So he's wondering, how can you incorporate temperature in your simulations or your calculations that you have done?
I think this is a very interesting observation. The traditional belief is that, let's talk about loading rates. I haven't shown the temperature results. These also we have done recently, so I will not get into it today because we're still analyzing the results. Now, the loading rate effect is perfectly, Professor Long, is it? Yeah, Professor Long is perfectly right. If you look at the far edge of the specimen in our Hopkinson bar test, you can see more profuse twinning taking place at high loading rates. And that is in tune with what people believe. And that can impart a lot of dissipation, because twinning leads to twinning shear, and it also causes additional dislocation activity inside the twins. And that can result in a lot of dissipation. On the other hand, what is happening near the crack tip is something very intriguing, and it's counterintuitive. In fact, here we see that with increase in loading rate, there's a decrease in the twinning volume fraction. And that also results in the transition in the fracture mode from quasi-brittle to ductile. Now, why that happens is because of the transition in this, because of the stress state. Now, what is happening near the tip, as I said, is not classical twinning. I call it anomalous twinning. And that anomalous twinning is unique to basal textured magnesium. Okay, and that is because of triggered by basal slip, which actually acts like a catalytic agent in order to trigger tensile twins. And that behavior is very, very different from the conventional stress, what we know about twinning, the effect of the loading rate. The temperature effect also, we find something very similar, but I don't have time to discuss that here. It's just about going to send it for publication.
Yeah, I think, when it comes out, we'll all look at that. Another question by Nataraj. So he wants to understand, you have done fracture tests. So can you predict something from these about fatigue?
Fatigue is a different ball game, because what happens in fatigue is that, the twinning is a very complicated phenomenon. It's very interesting, and both for a materials as well as a mechanics person.
Yes.
But when you do fatigue, you get detwinning. Okay, and this has been shown in many of the experimental studies. So detwinning, how that manifests in terms of the crack growth rate, okay, needs to be understood. So we haven't done any experiments on fatigue crack growth in magnesium alloys. But I believe that twinning will again play an important role, and during the unloading cycles, you could possibly have detwinning. In fact, in some of our crack, when we look at near the crack growth, near the extended crack, we see some evidence of detwinning, even in our monotonic experiments. And that I think happens because of some amount of elastic unloading. And that leads to detwinning. So detwinning will play a major role, and how that affects this. But I'm sure there is experimental results available in the literature. I am not aware of this.
So, but fatigue, I think modeling that would be, you have to use a fully reverse cycle and look at it, right?
Yeah, fatigue, FEM modeling is always tricky,
Tricky,
how do we actually do that? So people model it just by few cycles, and they actually don't model the crack growth. They only model blunting and sharpening.
I see.
So,
So
I haven't worked in fatigue modeling, so can't comment on that.
That's very nice of you. There is, I think, some more questions that have been asked by several people. You can probably take a look at those in the chat if you have time.
Yeah, sure.
Otherwise, we will close the session because we have to cut for lunch and join in the next session that will be chaired by Professor Ishwar Prasad. I thank all the invited speakers as well as keynote speakers for today's session and for making this very nice, interactive as well as informative session of a lot of very nice talks on mechanical behavior as well as advanced materials and characterization. So thank you very much, and I will close with this and cut for lunch. Thank you.
Thank you, Lakshmi Narayan. Thank you.
Yeah, thank you, sir. Thank you.
Good afternoon, Professor Rabe.
Good afternoon, Professor Rabe.
Hello.
Good afternoon.
Good afternoon.
Namaste.
Good afternoon. Yes.
Can you hear me and see me
Am I
okay?
still playing the video?
Absolutely, Professor Rabe. We are able to hear you. We are able to see you.
Yeah, thank you very much for the kind invitation.
It's our pleasure.
Thank you very much, Professor. It's our pleasure.
Yes, thank you very much.
You want to share your screen, Professor Rabe? Just check the.
Yes, thank you. I will try that.
Share screen.
Yeah. Can you see it?
Yes, yes.
I used very big letters, so it should be easy to see.
Thank you.
Thank you also. So I understood we have like 45 minutes, right? For the.
Yes, Professor Rabe. We have 45 minutes.
Yeah, the topic as I wrote is a little bit not in the main direction of the workshop maybe, but there's a lot of micromechanics involved in the direct reduction part. When you think about the future of maybe fluidized bed reactors or standard direct reduction reactors with different gases, then the question is also, how is the fracture response? So when you have inadequate mechanics of a pellet or fine ores or something, or lump ores, then material might stick together and reactors might not work anymore and so on. So I was surprised actually as to how much mechanics is involved, how much micromechanics is involved in direct reduction techniques. And in the process metallurgy, there has not been much done in this direction. So it might be an inspiration maybe also to mechanically interested metallurgists to look into this. So, but I will show a couple of pictures, I think, where this hopefully becomes a bit more clear then.
Sure, Professor Rabe. So shall we get started? Yeah. Hello. Good afternoon, everybody. So it's 2 p.m. Let's get started. Kiran? Kiran? Yeah. So good afternoon. Welcome back to the day 2, session 2, afternoon session. And we have very distinguished speaker with us today, Professor Rabe. Professor Rabe is well known to the materials and mechanics community. He is currently a director, Department of Microstructure, Physics and Alloy Design, Sustainable Synthesis of Materials. Professor Rabe has an interesting combination of degrees. He has a music from Conservatorium Wuppertal and metallurgy and metal physics from RWH Aachen. And after his doctorate at 1992 and habilitation at 1997 at RWH Aachen, he worked at Carnegie Mellon and also at the National High Magnet Field Lab, Tallahassee, and joined at Max Planck Society as a director since 1999. So his interests are in the area of phase transformation, alloy and segregation, design, sustainable metallurgy, computational materials, and atom probe tomography. Professor Rabe has more than 600 peer-reviewed publications with an impressive H-index of 136 as per the Google Scholar, and he has won several laurels and awards for his contributions to the Metallurgical and Mechanical Society, some of which are the notable are Leibniz Award, which is the highest German science award anybody can get, and also ERC Advanced Grant, which is also highest European research grant. And also, he's also won the Acta Materia Gold Medal Award for the year 2022. Without further ado, Professor Rabe, I'm handing over the session to you and looking forward for the great talk.
Yes, thank you very much for the very nice introduction and for the opportunity that I can participate here. And yeah, I picked a somewhat maybe unexpected topic for the presentation, namely the quest for green steel, for sustainable steel. But I think I can convince you that there's a lot in also for mechanically interested scientists. So it's essentially about how to reduce iron oxide by the use of hydrogen. And the assignment is, of course, targeting the removal of carbon dioxide from that process chain and instead produce as a redox product water from this type of hydrogen-based direct reduction. So the work is done, of course, with a couple of good friends and colleagues, and I will highlight their contributions as we walk through the different topics. and you will see their respective contributions then. So that is just only an overview from a recent compilation we made where we compared steel to aluminum, nickel, and titanium to have the biggest metallic alloy groups, so to say, on the market considered. And as we essentially all know, is that you have this gigantic footprint from steel. So you have about 7% of the global energy consumption from steels and about a third of all the industrial greenhouse gas emissions. And there are, of course, several acceleration factors which propel that. Of course, not just population growth, but particularly GDP scaling, which has the highest leverage, but also the fact that realizing green energy carriers like windmills and so on requires huge amounts of metal, as we all know, and of course, a massive further growth of the infrastructure. And at some point also coastal protection, when the waters are rising, we would need huge quantities of concrete and steel also. So, and that is something that will remain as we see in this forecast of the global steel demand. We see that the lower estimate for 2050 talks about 2.3 billion tons of steel compared to the current value of about 1.85. But the upper estimate is even 3 billion tons of steel. So when you see this little compilation here, when you place such a steel block close to Pittsburgh, you get a feeling for the quantities. And the underlying redox reaction, as we essentially all know from textbooks, is that you reduce hematite, Fe2O3, by carbon monoxide to the blast furnace or in direct reduction. And that is producing these huge amounts of CO2. And that produces, as I've already stated, this gigantic leadership of iron steel making when it comes to the global CO2 emissions. Currently, most of the big international companies start beyond CO2 trading, start pumping carbon dioxide underground. So there are big projects already ongoing, but this is of course not a sustainable engineering solution. And even if you take a look at the Bill Gates notes, the blog of Bill Gates, he also emphasizes when you talk about global warming, you must address the question of steel, of how to make steel. So let's take a look at thermodynamics. So when you reduce hematite, then the embodied energy of the oxide requires about 6 megajoule per kilogram. The actual balance in the steel industry averaged over the global steel companies is about 20 to 35%, which is already, by the way, for the metallurgical sector, a very good efficiency. Others are below 10%. But when you translate this now a bit into science, that opens very interesting research opportunities. So we have different feedstocks for iron, not just the fine ores, but also the pellets, which are essentially agglomerates of the fine ores. You have lump ores, just coarser blocks of ores, and not to forget, you have a drastically increasing scrap market. So that will later also be considered during this talk, how these things come together. And now the question is, when you want to expose these feedstocks to reductants, you can do that in different physical and chemical forms. You can use electrons directly, like in electrolysis. You can use, of course, molecular forms of reductants, but also protons and ions. And that you can do in different aggregate states. So we can expose these feedstocks to liquid, solid, plasma state. That will be the second part of this talk. And of course, to gas state, like in direct reduction. And these gas vectors, these different hydrogen carriers, can be of different nature, be like hydrogen, ammonia, methane, methanol, and so on. And also we work with LOHCs, which stands for liquid organic hydrogen carriers. So these are efficient oils that bond huge amounts of hydrogen. And that gives, then rise to identifying a relatively wide variety of possible reactors. And today I will only talk about two of them, namely direct reduction and plasma reduction. Now here, this is a very busy overview slide, which however, I think everybody knows from textbooks and classes. So we all grew up with classical blast furnace metallurgy, where you produce the iron towards the eutectic point. So you produce an iron-carbon mixture due to the use of coal and hot air, which produces carbon monoxide, and then you go towards the reduction and get this redox reaction that I explained before. And then you have this very high carbon containing near eutectic so-called pig iron, containing also all the impurities, by the way, from the coal, which you then bring into an LD converter to remove that amount of carbon, and then you go further towards secondary metallurgy. And the alternative would be that we go towards the established direct reduction processes, like for instance, Midrex processes and so on, that are currently, of course, running globally with natural gas, and use instead hydrogen. And I will talk later about those. An alternative is, as you will later see, to directly go with the iron ore into an electric arc furnace, but equip it with a reducing atmosphere. And of course, we have electrolysis also, but this is not part of the talk today. So there are so many things that we can do. So this is again just a repetition of the very classical blast furnace setup, and you see the different ingredients in the feedstock. As I've already mentioned, you go then towards the converter, but you produce about twice the amount of carbon dioxide compared to the amount of iron you produce. So that is really a staggering number. And when we talk direct reduction, now the classical Midrex process would make use of so-called solid oxide pellets, which are agglomerates, polycrystalline agglomerates of fine ores. And you can now play with not just only feeding different carbon carriers in, be it a natural gas or coal form, but also hydrogen or other gases, and combine this with iron ores and pellets and bring all this together in a shaft furnace or in different other types of furnace setups. And then you produce that sponge iron that you charge into an electric arc furnace, and there you can charge also scrap and melt it down. And that has, a footprint between 0.3 and 0.6 tons CO2 produced per ton of iron, just to give you the ballpark of what we talk about. Now, when we look into this now from a physical metallurgy standpoint, we do here, just show you here a curve for 700 degrees centigrade with pure hydrogen atmosphere. And what's very interesting already upon first view, when you're not so accustomed to discussing these aspects, then I personally find it very exciting that you already go through a number of pretty complicated phase transformations. I mean, when you work with iron or with high entropy alloys or with titanium, then you are accustomed to work with complex phase transformations. That makes our profession also so interesting. But in the oxide states, that is very much the same. So it's really interesting. You go from the original hematite, which is a standard ore, towards the cubic magnetite, further from the cubic magnetite to the likewise cubic wüstite, so where the oxygen lattice is essentially the same. And then you go at 700 towards body-centered cubic iron. At higher temperatures, you end up with austenitic iron and so on. So that depends, of course, always where you are in the phase diagram. But you see what is really important, when I go back for a second, what you really see here in this slide is that the last reduction stage, the wüstite to iron transformation, is extremely sluggish, very, very, very slow. And that is a problem for the mass production of about 2 billion or more tons of iron that we need per year also in the future. Now, this is a very nice environmental microscopy experiment from my colleague, Professor Mark Willinger at the ETH in Switzerland. And here he exposes a single crystal wüstite directly to a hydrogen-containing atmosphere. And you can very nicely see how this rough wüstite surface here is overgrown by a thin layer of iron, because naturally at the surface you nucleate, you form the iron. We already started in the last part with wüstite, so the last oxidation stage. And you can see how it's covering really the surface entirely. And here you see that in a slightly higher resolution. So this smoother surface that you see building up is actually the iron as it forms on the wüstite. And that tells you already that you build up a barrier, a diffusion barrier for the transport of oxygen and for the transport of hydrogen, of course. So that is translated here into this schematical picture. You see the wüstite, the cubic wüstite on the left-hand side. And the oxygen experiences a gradient in chemical potential between that wüstheit and the surface beyond that iron layer that had been formed, where it would react with the water. So the exact location where the water is really formed at internal interface and so on is still a pending scientific issue also. So we also tackle this by reactive force field molecular dynamic simulations that is done in collaboration with my colleague R. Gürcan in Turkey and with a couple of other friends. And you see that is, of course, a rare event problem. Here you see how a water molecule was formed at the surface and how the first oxygen is reduced. That's just to give you a feeling. One of the elementary scientific questions here, before even the first iron layer can be formed, is a question: how do you remove the first oxygen atom from the wüstheit, which is a very, very strong bond. And the question is, when the first one has been removed, where exactly do you remove the second one? Maybe from the already weakened area, but that is all not so well known. So it is generally interesting to better understand nucleation phenomena in redox systems during phase transformation. These are things I think that are not yet so well understood. Here you see another rare event. Yeah, you see also how a water molecule forms. So that is at very early stage. It's all unpublished material, just to show you how rich this field is. Now we jump into a piece of hematite here. That is one of these commercial pellets. You see that is a complex polycrystalline aggregate with a lot of inherited sinter porosity. And you see from these EBSD pictures where the grain boundaries are, you see also a bit of magnesium oxide debris, although these hematite ores are relatively clean nowadays. And here what is interesting, when you jump towards 1 minute reduction state at 700, you see that here the bright blue areas, which are the hematite, are already overgrown by the newly formed magnetite. So that is a transformation between a hexagonal oxygen lattice and a cubic oxygen lattice. And the nucleation is obviously starting at these internal interfaces where the hydrogen can arrive easily and the oxygen can be removed easily. And that gives a classical Avami problem with nucleation growth and massive grain refinement, which for later transport properties, by the way, is quite important. When we jump towards 10 minutes at 700 degree centigrade, then you see why I alluded to the fact that mechanics is becoming important. When we take a look here at the different snapshots, then you can see indeed that you have not only the inherited porosity, but massive further porosity is growing up because you remove a lot of mass, you remove many oxygen atoms. And here you can see that unlike we saw in the electron microscope, you see here in that little picture that the inner wüstheit is not entirely surrounded by a dense ferrite layer, but you have also delamination and fracture at these interfaces, which, by the way, for the process is extremely important regarding nucleation and mass transport. Here's a ferrite wüstheit interface highlighted with electron channel contrast imaging illuminated, where you see the buildup of high populations of geometrically necessary dislocations because of the very high volume mismatch between these highly stressed phase contrasts. And of course, you see here this massive porosity that is building up when the point defects collapse into nanopores and micropores. So the porosity, therefore, is also growing, as you see in this diagram, as a function of reduction time. And you start with a certain inherited porosity for a commercial pellet, and you arrive between 40 and 50% porosity at the end of a reduction sequence, as you can see here. We also screen that with direct synchrotron in situ reduction experiments. Here you see also the gradients between the surface and the center. This is now a wüstheit single crystal, so without any grain boundaries or so. And you see that it looks like a Swiss cheese. In the center, the oxygen cannot escape, and you have, due to the mass loss, the point defects forming pores where the water can be formed and stored. Let me go back. And towards the surface, however, the oxygen can rather easily diffuse out. So some of the oxygen is lost through the surface where it forms water. So you have massive gradients. If you now scrutinize that also for a commercial pellet, then you see indeed that at the center of the pellet, you have a much higher presence of wüstheit, while at the surface you already have, nearly 90% alpha iron formed. So the take-home message from this synchrotron experiment that you see here is that also through the commercial pellets and due to their size, you have a massive gradient in the properties, in the phase transformation rate, in the metallization, and so on. And so when you take this into this overview picture, then you have here a typical Vidrex type shaft reactor, and these pellets, which typically have a centimeter diameter, experience high gradients in this phase transformation kinetics, and hence also in the distribution of the metallization. So we are, of course, very much interested of casting this into now in the moment a relatively simple model. We just have placed the paper on archive if you are interested, where we just take a classical core shell type of problem, where we formulate the chemical free energy in a Landau form, so in a classical Kahn-Hilliard form for the corresponding phase transformations, and that can be fitted to existing free energy data. But as I said, you have a large volume change, large volume shrinkage up to 40% between the wüstite and the alpha iron due to the oxygen loss. And we translate this here into a corresponding coupled elastic stress strain response. So it's a coupled chemical elastic problem. And further here, we also introduce an inelastic yield criterion. That means we also render this phase field calculation capable of dealing inelastic effects with as simple as you see a J2 plasticity, equivalent plastic strain, and so on. So it's still relatively simplistic. Just the take-home message is here that we cast these redox reactions into an advanced phase field model under full consideration of elasticity and plasticity. Now, just to give you a simple core shell type of problem example, as you saw in the electron microscope before, maybe you look here at the 40% volume change, that is the last row. The omega 40 stands for 40% volume difference between ferrite and wüstite, which is about realistic. And that is now the elastic case. So this is a purely elastic redox phase field calculation with hook coupling. And you see after 15 minutes exposure that there's a very fast shrinkage. So very fast reduction rate of the remaining wüstite that you see in the center. But on the right-hand side, where the corresponding J2 von Mises stresses are shown, you can realize that this builds up artificially high stresses. So we talk here 21 gigapascal, which is of course nonsense, because we know in reality you would undergo delamination, fracture, and particularly massive plasticity. That's also what we see in the electron microscope. You saw that in the SEM pictures before. So this is just to give us a feeling that when the elastic stresses build up a lot, then you really also start altering the double well potential into a single well potential. So the thermodynamics are then really highly mechanically dependent. But as I said, realistically, you have a plastic capping of this effect. And when you now compare the elastic and plastic calculations that you see here on the left-hand side, then you can realize that, again, when we go to the more realistic scenario of 40% volume mismatch between ferrite and wüstite, that indeed, when you have a plastic relaxation, no artificially high elastic energy densities can build up, and you have a more realistic metallization rate, which is also in better accord with the corresponding experiments. And the von Mises stresses do typically not exceed the yield stresses, of course, which are around 800 megapascal or something like that, then producing, of course, dislocations in both phases. We, of course, also work on considering fracture mechanics in these calculations, but this is all ongoing work. And when you then look at the resulting kinetics for this last reduction stage from wüstite into alpha iron, then you can indeed see here that the purely elastic case, which is that blue solid line on the left-hand and right-hand side, gives slightly exaggerated reduction degree, which is understandable because you build up artificial elastic energy densities. And the more realistic case of the plastic deformation gives very realistic reduction rates. So that is just a test that you can run against analytic examples for such a simple core shell scenario. Now we take a more realistic case of say, a commercial pellet, as you see it here. And you can see when we cut that open with about 1 centimeter size, you have, again, this very complex microstructure and phase analysis that we wisdomed before already. And you now want to know how such a reduction proceeds locally in such a complex microstructure. And that's where now the phase field formulation that we have chosen can play out its strength. Here you see a first simple example. where you can follow not only the intrusion of the hydrogen, because all these diffusion equations are of course also solved in this phase field formulation, but particularly you want to see how the formation of the iron is progressing and where the hydrogen is formed, because it's very important in all of these direct reduction means that the hydrogen that forms is removed from the process. When you store too much hydrogen in the material, you will later see you reduce the metallization degree. And you see with that nicely that the nucleation would occur naturally close to the free surfaces where the gas transport is very fast, of course, reduction rates are fast, and then it grows towards the inside. And indeed, you have these remaining little Leucite islands that are also shown here in this micrograph, where when you zoom in a little bit, you see this gray area in the center with these many pores. That is a remaining Leucite, which now indeed is more and more overgrown by a solid, rim of iron, which slows down particularly the transport of the oxygen. And now we look at some of these local scenarios from such a real pellet configuration in a corresponding phase field simulation. Here, this is just again the elastic case. And you can indeed see that, as we saw before, that the alpha iron is formed close to the existing interface areas. But you see again that the elastic stresses are artificially high. They produce in part here something beyond 10 gigapascal, which is of course nonsense. And in the plastic case, you can again see that these stresses are kept and produce plasticity when you reach that yield surface. And then you can see where the hotspots are created. And that is very important to later understand what does it mean for possible fracture mechanics of these particles and so on. Because when they fracture too easily, then your reactor is also kept. Now we do also, together with Malte Erik Beck at the ETH in Zurich, in situ experiment of two-dimensional, low-dimensional oxide films. So as you see here, you have layers of oxide films that we expose again to hydrogen in the electron microscope. And we do that under low-dimensional conditions to better study and understand how the iron is really nucleated. And from that, we really see, as you see here nicely in this plot, that they really essentially originally form at the triple points where the mass transport, the removal of oxygen, particularly through these adjacent grain boundaries, is the fastest. And that's where the iron crystals are then freely growing in this low-dimensional experiment. Here you see now, jumping to a high resolution, the work of my colleague Brad Zoe here. He is an Alexander von Humboldt fellow in our group and does wonderful high-angle annular dark field imaging, where we look closer at the topology and connectivity of some of these pores. And here you see a high resolution where we look at some of these smaller pores in 3 dimensions. And we want to study its connectivity to the grain boundaries and its storage actually of the water. Because, like I said before, when the water is not removed from these pellets during reduction, you have a problem of reoxidation and sluggish kinetics. So what he did now is that he studies such micro and nanopores at different distances away from the next free surface because of the insufficient transport. And indeed, you see for those pores that are far away from the next inner surface, there's very high water pressure building up inside of these pores at these high temperatures. That is something that we can nicely calculate with the phase field calculation I showed you before. And then you produce reoxidation at these rims, at the inner rims of the surface. That means when you have a very fine calculation of the porosity through your material, as you saw before also in the single crystal experiments, then you have interconnection of reoxidation phenomena in this pellet, which makes the reaction rate potentially very sluggish. Now here we jump now just a few results. There's a lot of ongoing work into the APT analysis, where we look at the atomic scale phenomena of these processes, where we study at the moment particularly the interface reactions and the role of the residual oxides that you find throughout the material. Here, that is now again a little bit switching gears. When you now forget for the moment about this, direct reduction and the other aspect that I told you before, but you jump directly from the iron oxide to the electric arc furnace. and don't go through this classical, blast furnace or direct reduction operation, but you directly bring your iron ore into an electric arc furnace. Why? Because even from any direct reduction, you must, at the end of the day, with your sponge, go through a melting process in electric arc furnaces. So it's classical process metallurgy, nothing new. What is new, however, is that you can equip such an electric arc furnace with a reducing atmosphere, in this case with hydrogen. And that is what we do. And then you can, in part, achieve a very, very small carbon footprint of such a process. That depends then essentially on the electrodes and on the remaining fuel that you must put in the reactor to get the reaction running. And this is, of course, as most of you know, existing technology. So plasma furnaces are used around the globe already for melting scrap, essentially, particularly in the stainless steel industry, but also in the nickel industry. So it's an existing technology, of course, with graphite electrodes. So we also work on the electrodes a lot. So the idea is that you have something like one big blender, one big mixer, where you can throw everything in. So lump ore, fine ore, scrap, and you can directly operate it with electrons, of course. No? You can operate this with electrical power. And then you have all the phenomena that you need for iron making in one reactor. The mixing, melting, alloying, the reduction, most importantly, of course, the evaporation, some of the oxygen you lose from the vapor pressure, because you must recall that the hematite melting point is only 50 Kelvin above that of iron. That means you can, melt all of this in one reactor down. And this is now something which we study in high detail, because we arrive maybe then at a much, much higher efficiency than currently in hydrogen-based direct reduction. And you see that how we do that here in a reactor, a little electric arc reactor in our laboratory. And you see the metallurgist, Mr. Kulse, doing this experiment. And here we work with a mixture of argon and only 10% of hydrogen. And we do, of course, experiments with different hydrogen partial pressures and so on. And we partially can interrupt these processes, quench the chips down and analyze them step by step to study how the reduction works and proceeds over time. This is shown schematically here for an experiment with 10% hydrogen plasma, the rest is argon. And then you see here, when we took out specimens and then recharged them back into the reactor, of course, with a refueled gas atmosphere after 1 minute, 2 minutes, and so on, how essentially the reduction very efficiently proceeds. And already after 15, 20, 30 minutes, you have pure iron in your hand, just with one single reactor. And just to make this clear, you have it directly from the ore in one furnace, replace an entire steel factory. And this is what you see here also from a couple of quenched microstructures. You beautifully can see how these iron nuclei are forming in the adjacent wüstite melt, and how the silicon is rejected from that interface into the wüstite. So you will have to do some slag metallurgy also to understand the partitioning. And you do that here also at the atomic scale in the atom probe measurement, often quenched in interface between wüstite and alpha iron. That was, of course, in the liquid state, now quenched down. And you can study the partition of silicon and, of course, of many other elements in this process. And we were surprised ourselves how efficient that works in terms of the energy consumption and hydrogen consumption. One little sidestep here is copper. Now you might ask, why is this guy talking about copper? Copper is one of the biggest challenges for future steel making, because it enters massively through the scrap. This is just a little explosion diagram where you see how much copper is in a current SUV. And when you go towards, electrification of the transport, which is globally, of course, going on, you can, from this little overview, nicely realize how the amount of copper is drastically growing when you go to a high electrification degree of the future vehicles, and that is already going on. This is a Bloomberg analysis of the copper demand, and the amount of copper that translates to the amount of copper that will end up and is ending up in steel scraps. And that is, as you know, the only element that you can practically not remove from iron, and that has many implications. And therefore, this little sidestep where we now study, of course, the removal of all of the behavior of all of these scrap-related or ore-related elements as a function of time, not just the production of iron, of course, but it's very important, as you see here in this diagram, also to better understand how really the copper can be removed in the plasma reactor from the material. That is, I think, very, very important, because that means that you can indeed mix your different iron oxides in a slightly reducing atmosphere together with scraps that can be polluted by copper and still be capable of producing very, very clean iron. That is, by the way, much, much cleaner compared to what you get from the blast furnace. So that is, I think, the reason, just to show you that there's also nice chemistry effects when doing this plasma direct reduction of materials. So I come now towards the end to a couple of conclusions. So in the direct reduction business, I thought I could show you the role of micro and nanostructure, also of mechanics, and of course of the chemistry associated. You could realize the immense importance of all the inner surfaces, of the physics of the pores and the role of the pores for transport and mechanics. The nucleation and the role of the fast transformation at the beginning was very important, understanding these phase transformation phenomena, but also the very sluggish last part of the sequence, namely the Wüstheit reduction to iron. And we are very much interested in the role of the nucleation, of the transport and the pore conditions on these nucleation and phase transformation conditions, where also, as I showed you, the volume mismatch plays a really, really big role between the different phases, because you remove so much oxygen, you have a permanently shrinking volume. And this mechanics also enters the understanding of these phase transformations. And of course, we studied the total energy balance, the Gang elements, the chemistry of all of that. And the second part, a little bit briefer, was the plasma reduction as a totally different process. However, with very exciting chemistry and physics effect associated with it, very high efficiency. It's also an exothermic process. And we study the kinetics. We have very fast reduction rates that are comparable to high temperature direct reduction with only 10% of hydrogen. So it's really efficient. And of course, we have not so many rate limiting barriers as in the solid state. So we study now the liquid nucleation and slag metallurgy partitioning and so on from a physical metallurgy. But we think of that aggregate like a thermomix where you can replace an entire steel company by just one simple reactor. And of course, there are many, many fundamental questions are open. So the entire plasma state, the excitation states of the free radicals, the plasma chemistry is something that we simply don't know. It's entirely new. We probe this by in situ in operando studies in the microscope, where we also create a plasma in the microscope. The nature of the phase transformation is, of course, what is for us very interesting. The entire theory of the first reduction stages. So we have both binodal and classical nucleation phenomena. So the entire thermodynamics is very interesting. But also we look into things like what is really kinetics of the dihydrogen molecular splitting. So because the reduction goes through atomic hydrogen, not through molecular one. And so catalysis plays a big role also. And of course, at the end of the day, you want to translate this into disruptive reactor ideas. And what I sometimes find worth mentioning is that we talk a lot about the global warming, which is totally correct, of course. And we have more than 40,000 papers nowadays on the market on the origin of climate change, global warming and the role of carbon dioxide for it. But I think we have too little research and too little attention on avoiding the carbon dioxide in the first place. I think it's not enough describing what carbon dioxide is doing. I mean, you must do research on avoiding the production of carbon dioxide. And that's why I think metallurgy, like science on concrete and so on, plays a huge role in that. And you see there's a big mismatch. This community is still incredibly slow. And I think the somewhat artificial separation of process metallurgy and physical metallurgy is not always helping. So I think there's a lot of things that we can do together with process metallurgists to really, get this off the ground. So thank you very much for your kind patience. Thank you.
Thank you, Professor Rave, for the very insightful lecture. We have a few questions in the chat box, if you permit, I'll ask. Dr. Long John, he writes, thank you, Professor Rave, for the inspiring talk. So his question is, we know hydrogen generally causes severe embrittlement of iron and steel. and the concentration of hydrogen, iron, and iron-based alloys should be kept very low. So I'm curious how to control the concentration of hydrogen in the final hydrogen-induced iron.
Yeah, that's a very good question that is brought up quite often. And in all of these different hydrogen-based reduction methods, you get different degrees of hydrogen implementation. So it depends very much on your process route. And we indeed monitor and measure this in very high detail with TDS and even with atom probe and so on. And indeed, it turns out that you are left typically in most of these processes with a very, very low residual hydrogen content. In the direct reduction based on hydrogen, the problem is even smaller because, as I said before, when you produce iron sponge, then you must at the end of the day melt it anyway in an electric arc furnace, and you melt it then again or keep it liquid for the secondary metallurgy where you adjust your alloy. And in these processes, you lose a lot of the hydrogen also. So the message is that these are very low in hydrogen content. But it's a very good question, must be probed for every process.
Thank you, Mr. Ravi. We have another question from Professor Jaya, MIT Bombay. So what is the diffusion rate of hydrogen inside the Fe layer that forms on the oocyte? Does it not get accelerated due to plasticity because of dislocations produced due to the stress buildup during the reduction? Why is this particular low in ferrite? Is it because of the density or why oocyte is taking up zero stress in the simulations?
Yeah, no, these are a couple of very good elementary questions indeed on the physics of the transport in these different, say, layered structures. No? And so first of all, one must say the hydrogen transport, which is here atomic transport, through both iron and wüstite is not the bottleneck. So we have in the literature very good data about the diffusion coefficients, about mobilities and so on. So the hydrogen motion through all of these different phases is very fast. And secondly, so you are totally correct that as I showed, we build up a wide cosmos of defects, grain boundaries, fracture, many dislocations. These are, of course, all defects that would accelerate the transport of hydrogen further, particularly, of course, the grain boundaries. And particularly when you remember, you go from the hexagonal hematite to the cubic magnetite, inverse spinel magnetite, then this is particularly breaking up the grain structure substantially. So there's no big limit to this. What really is the transport bottleneck is the transport of oxygen outbound. So it means you always kind of swim in a lake of hydrogen at these high temperatures. That's not the problem, but you must get the oxygen out. And that is really, really very slow. And for the oxygen transport, therefore, it is much more important to understand, when you have across a centimeter big commercial pellet, a gradient of between 90% and 5% iron production, you must consider this, of course, in the future design of these pellets to have faster diffusion pathways for oxygen particularly. Or you want to design a pellet that is softer, has more defects, or breaks up, or has more fractures. So for these processes, indeed, the defect landscape and the oxygen transport, and of course, not to forget the water transport outbound. These are the real bottlenecks. Hydrogen is not the transport bottleneck. A very good question. Thank you.
Thank you, Professor Ravi. And there is another question, like how do you get rid of sulfur in this process? What specifically is that? I mean, probably if you look at the variation in different iron ores, so how do you treat them? That's a gist of the question.
Yeah, that's also a very good question that addresses the entire question of all the impurities. Now, everything we learned so far in process metallurgy and teach our students is, of course, addressing the gangue elements and the impurities that enter for conventional processes in either MIDREX or blast furnaces. And they are very different from those that we enter now, that we have now in these processes. First of all, most of the sulfur and phosphorus problem in classical steelmaking comes from the coke, does not come from the ore. They come from the coke. That means suddenly you are in a positive situation where many of these classical very harmful, low eutectic melting elements like sulfur and phosphorus and so on are simply no longer there in these huge quantities. That means your secondary metallurgy does not take so much, has not to take care of them. But what is much more important is what the natural ingredients of these different ores are. And they're the biggest problems when you go particularly more to low price ores and open the market on the ore side also. Now we don't have to stick to those that we use for blast furnaces, but we should open the market and take cheaper ores in. Then the main problems are aluminum and silicon content, and also titanium, magnesium, and others who form very, very stable oxides. And I think for the metallization degree, this will be the main challenge to tackle. And here it's again very different whether you go through direct reduction or plasma reduction. So, and then you must do like in other steel making processes also a very dedicated slag metallurgy that must work out to fit these processes.
Thank you, Professor Rabe. One last question, Sachin Kumar. He would like to ask, what is the source of hydrogen and what is its implication on the greenhouse gases?
Yeah, so that's of course a very, very good question, a systems question, because we totally changed the way how we make steels, and we made it with carbon since about 3,500 years, since the Hittite Empire in Anatolia started doing this. And you are totally correct. So currently pretending that all this comes from classical green water splitting hydrogen is of course nonsense. This market does not exist. And so that is more a guess for people who know that, gas business better. My best pick is that we look intensely into other hydrogen vectors, like for instance, ammonia is for us very interesting. So we do many experiments with ammonia. And secondly, I think that much of the hydrogen that we need in the industry will come more from pyrolysis. Currently is coming from gas reforming, which is of course not a very clean technology and will remain so. But I would put my money more on pyrolysis technologies, where you produce, in plasma pyrolysis, you produce solid carbon. And I think that is a much more viable and sustainable technique to satisfy that market.
Thank you, Professor Rabe. In the interest of the time, I will not be able to take up any further questions. Professor Rabe, if it is possible, you can actually go through the chat box, and there are a couple of questions which are people interested to ask. So, but nevertheless, I think thank you very much for the insightful lecture. And then it's a wonderful testing the physical metallurgy, process metallurgy, and mechanics. Thanks a lot.
Thanks a lot. Bye-bye. And thanks again for having me. Bye-bye.
Thanks a lot.
Thank you.
Okay. Yeah. So now we will switch to the link 1, link 2, link 3, the 3 parallel sessions comprising of advanced material characterization, mechanical wear of materials, and crystal engineering. So link 1 is for the same link is for material characterization, and the link 2 will be for mechanical wear of materials. We'll see you in 5 minutes there. Thanks a lot.
Yeah, a very good afternoon to all. I am Dr. Chandramohan from Physics and Nanotechnology Department, SRM IST. So I request the participants, those who are interested in continuing this session, please stay in this link, and those who are interested to listen to other talks on other themes, you can join session 2 and session 3. So we'll start the session. So in this session, we have 3 invited talks by Dr. Siva Katuri and Professor Viswanath Balakrishnan and Professor Koteshwar Rao, followed by we have 1 contributory talk in this session. I welcome all the delegates to this session. So the first talk will be by Dr. Siva Katturi. Yeah, so before inviting inviting him, let me introduce him briefly. Dr. Siva Katturi is a senior research fellow in the College of Engineering and Computer Science at Australian National University. He is currently leading a research program on the development of catalytic materials and systems for green hydrogen production. He received his master's degree in chemical engineering from IIT Madras and a PhD degree from NTU, Singapore, in material science and engineering in the year 2013. He basically works on he basically works on like areas like material synthesis, device fabrication, with extensive experience in photoelectrodes, catalyst synthesis, solar cells, and integrated systems for direct solar hydrogen generation. He was a Discovery Early Career Researcher Award Fellow during 2015 to 2018. He was also a recipient of Australia-China Young Scientist Exchange Program Award from the Australian Academy of Technology and Engineering and Australia-India Strategic Research Fund Early and Mid-Career Fellowship from the Australian Academy of Science. He has been awarded a total grant funding of over $4 million Australian dollar as a chief investigator from the Australian Research Council and Australian Renewable Energy Agency. With this brief introduction, I welcome Dr. Siva Katturi and I request him to start his presentation.
Thank you, Professor Chandramohan. Thanks for your nice introduction. First of all, I would like to thank the organizers of this conference, in particular, my friend and ex-colleague at ANU, the convener of this conference, Dr. Kiran Mangalampalli. Today, I'm going to talk about our work on designing semiconductors and catalytic materials for sustainable hydrogen production. So I'll focus on two topics, one on semiconductors for direct water splitting to produce hydrogen and on low-cost catalysts. And sorry, you can see that the date mentioned on this slide is a bit old, so that shows that, yeah, you put a lot of effort on your actual slides and you don't look at your title slide much. So the introduction, coming to the introduction, why we need sustainable or clean hydrogen. If you look at the plot on the left, this is the data, scientific data from IPCC. IPCC stands for Intergovernmental Panel for Climate Change. So the data shows climate change is real. You can observe that surface temperature is increasing. This is the data for the last 150 years or so. And the average sea level is increasing and snow cover is dropping. And in particular, if you focus on the last 50 years, it's more rapid. That coincides with our industrial activity, increase in industrial activity. And you can see that most of these greenhouse gas emissions, mainly carbon dioxide, comes from automobiles and power plants. Indeed, 2/3 of the emissions come from these emission sources. So it's true that the climate changes are permanent, changes are happening, and that's resulting in catastrophic events. And it's not all gloomy. We are making some progress, particularly if you look at solar cells, solar panels. You can see that the orange shaded area shows the cost of electricity produced using solar cells. It dropped almost 100-fold in the last 40 years. That's the economy of scale. So we are able to now produce solar cells at large scale, and that also impacted the price. I understand from my colleagues that the price of solar electricity is now even like less than 10 cents in some parts of the world. And that means the price of solar electricity is almost half to that created by burning fossil fuels. But renewable sources doesn't solve all the problem. Some of the renewable sources are intermittent. If you take, for example, solar, you get 4 to 6 hours of sunlight. Then you have to rely on other type of energy sources. And another issue is you can't use electricity for everything. There are sectors which are hard to electrify. So we need to find ways to store and then transport, because there are regions like some of the Asian countries like Korea, Japan, they feel they won't be able to produce enough renewable sources themselves that they require. So we need to be able to transport renewables. So we need the ways to store and transport. If we look at methods, different methods available to store energy, the x-axis here is mass energy density, y-axis volumetric energy density. And if you look at hydrogen, it's sitting very high on the mass energy density. And in comparison to fossil fuels like gasoline, it has 3 times more energy. That means if you use 1 kilogram of hydrogen, you can produce as much energy as burning 3 kilograms of gasoline. And if we are able to compress, if we can compress hydrogen, you can also increase the volumetric density, because it's a gas. It's at standard conditions, its volumetric density is low. And other technology that we often talk about, batteries, you can see that it's almost 2 orders of magnitude lower. So that indicates that batteries, it will be tricky to store large amounts of energy, in particular to transport energy across different regions. And so hydrogen can fit in very well to solve this issue of energy storage and transportation for renewables. And another advantage of hydrogen is if you burn hydrogen, it produces just water as the emission, so which is completely clean with 0 carbon. And now we need to accelerate our transition to 0 carbon energy sources. Hydrogen can accelerate that transition. Hydrogen can, first of all, integrate different sources of power generation, for example, wind, solar, and you can integrate, convert them into hydrogen, and then produce electricity when needed. And hydrogen can be used to transport ship energy across different regions. And hydrogen can act as a buffer to improve system resilience. And some of the sectors like transportation, industry energy usage, building energy usage, also, for example, hydrogen can be used as a feedstock in industry. So hydrogen can help to decarbonize all these sectors, provided we produce hydrogen sustainably. So now coming to the first topic of my presentation, direct solar to hydrogen production. I would like to first start with some basics about photocatalysis. A lot of you might have studied or read about this. If you have a semiconductor material with a suitable band gap, when it is exposed to sunlight, it produces electron and hole pairs. And electrons from the conduction band, they participate in water reduction to produce hydrogen, whereas holes from the valence band, they participate in water oxidation to produce oxygen. So there are several requirements for a material to be a good photocatalyst. For example, a suitable band gap to absorb sunlight efficiently, and good optical absorptions, and good electronic properties like electron mobility and carrier lifetime. And in the end, it's a catalytic reaction, so the material should have good catalytic efficiency. And if you have to use it in a practical system, you need to have very good long-term stability. And this field grew rapidly in the last 20-30 years time, and people worked on a number of materials. I can quote hundreds of materials as this chart shows, but we don't have one material that satisfies all the requirements to take it to practical application. And also in the last 20-30 years, we have seen the progress in solar photovoltaics. We were looking at them as very expensive technology to produce electricity, and now we look at them as cheap technology to produce electricity. So in our research at ANU, we are focusing on how we can use these photovoltaic materials to turn them and use them in producing hydrogen cheaply. So why direct solar hydrogen production? If you look at the current existing method to produce green hydrogen, you can have a solar PV plant which produces electricity, and then you have grid infrastructure, produce electricity, and then transmit electricity and power centralized electrolyzers such as this. So this approach has a lot of issues. First of all, it's complex with low flexibility. You need grid infrastructure. For example, solar cells produce DC electricity. You need to turn that into AC and then transmit, and then again turn that back into DC electricity and power the giant electrolyzers to go produce sufficient hydrogen. And there are also various efficiency losses in this process. As I mentioned, power inversion losses, there can be thermalization losses, solar mismatch losses. And effectively, like if you start with 20% solar efficient solar cells, it ends up in less than 10% overall efficiency. And the other approach that we've been investigating is all integrated direct solar hydrogen cells. For example, an example here, how a solar hydrogen panel can look like. Here, it's a simple device that can directly produce hydrogen when exposed to sunlight. This can be when the technology is mature, and we should be able to integrate them just like solar cells and construct large plants. And we should be able to achieve higher overall efficiency and reduce the cost of levelized cost of hydrogen. So the target for levelized cost of hydrogen to make it practical is less than $2 US dollar per kilogram. So we believe this technology has the potential to reduce the cost of hydrogen. So in our work, we looked at how we can use the material used in rooftop solar cells, silicon, and turn that into photoelectrodes. So conventional photoelectrode design consists of a semiconductor and coated with a layer to Hello. Can you hear me, guys?
Yes.
Looks like there was a problem.
Yes.
Yep. Yep. So I just stopped here. I was explaining about making photoelectrodes. So in our lab, we looked at decoupling light harvesting with catalysis. In the conventional approach, you have light harvesting happening at the front surface and catalysis also at the front surface. So we looked at creating structures where we can move the catalysis to the rear. So the light harvesting and catalysis, there is no trade-off. And the catalyst sometimes can block the light. So in this case, there is no light blocking effect. So we created silicon photocathodes with very good performance. As you can see here, the currents around 40 milliamp per centimeter square are comparable to solar cell currents. And that resulted in applied bias efficiencies close to 14%, which was one of the highest reported. And this approach also enabled very high long-term stability. You can see that we looked at 3 hours running this photoelectrode, and the current remained stable with a good Faraday efficiencies. But one problem with using just silicon itself, it doesn't produce enough voltage to power water splitting. So in our work, we looked at integrating with perovskite solar cells to turn them into tandem. When you have a tandem semiconductors, you have two semiconductors, so they can produce together enough voltage to split water. So if you look at this graph, when we have this silicon photocathode combined with the perovskite solar cell and a counter electrode, this whole integrated cell achieved 17.6% solar to hydrogen, which was one of the highest reported efficiencies. And this work was also recognized as global top 10 most notable recent innovations in energy and climate change by innovation for Cool Earth Forum set up by Japanese government. So in collaboration with the University of New South Wales, we went on to further improve these systems. We looked at optimizing the catalyst materials, the morphologies of the materials, in this case, nickel iron, nickel molybdenum. And we also looked at a different way of integrating these. So we used silicon and perovskite as solar cells, and the voltage produced by them wired, powered to power catalyst through a wired combination. So this produced a solar to hydrogen efficiency close to 20%, which is the record efficiency for under one sun. And the most importantly here, the materials that we used in this combination, they're all low cost materials, no expensive materials involved. And we were also able to achieve good long-term stability. And you can see this comparison plot that the efficiency is the highest, as well as it's based on all low cost materials. So now we are trying to expand this research and build larger prototypes to produce hydrogen. And in another work, we looked at a method of making photoelectrodes out of these photovoltaic materials using catalyst foils. So you can, as you can see in this figure, the photoabsorber like a typical solar cell, and with front side optimized for light harvesting, and the rear side, a lot of times when you coat catalyst, then when you put that photoelectrode in electrolyte environment, it can corrode. So we looked at pre-synthesizing catalyst and a foil, very thin foil, and then bonding this foil to the photoabsorbers. So in this way, the metal foil, typically, for example, nickel-based foil, is very stable in electrolyte environments. And it also allows you to pre-synthesize catalysts, so you can use solution-based methods, which can be otherwise corrosive to photoabsorber. And so we looked at solving both stability and low efficiency issues. So we fabricated two different types of photoelectrodes, one based on silicon and another based on gallium arsenide. As you can see here, the long-term stability of these photoelectrodes. Gallium arsenide, we looked at 5 days. It's the current remained very stable, highly stable. The silicon photocathode, the same. And if we compare with the existing data for these different photocathode, photoanode materials, you can see that our photoelectrodes achieved one of the best stabilities, one of the best efficiencies. And in comparison, we built an artificial leaf that can produce hydrogen on its own using these catalyst foils. You can see that the stability, represented by the circle sizes, the largest circle greater than 7 days, we managed to achieve 10 days of stability, which wasn't shown before with the other approaches to make photoelectrodes. And this approach also allows to turn various types of solar cells into photoelectrodes. So we looked at calculating the efficiencies that we can achieve based on various other solar cells. So you can see that we can exceed, using this approach, we can quickly improve the efficiencies of a range of systems. This work was carried by my PhD student, Joshua Butson. And the second topic of my presentation, low-cost catalytic electrodes. So when you look at electrolyzers, catalysts are an important component, catalyst electrodes. So in a typical electrolyzer, you have a positive anode and negative cathode separated by a membrane and some flow channels. And then you repeat this stack hundreds of times to produce gigantic electrolyzers such as this. So in order to reduce the cost of electrolyzer, so reducing the cost of the stacks is a crucial aspect. You can see the stacks can be like 50% of the cost of the electrolyzers. So we looked at how we can make low-cost nickel-based electrodes. So in terms of preparing membrane electrode assemblies, there are various approaches, synthesis approaches For example, wafer phase deposition, including sputtering, CVD, and evaporation, and electrode-assisted methods, and also solution-based methods such as aerosol spray, ink printing, roll-to-roll spreading, and also solid spraying methods. At ANU, we looked at developing scalable methods using solution-based. Solution-based can be, developed into a large-scale, rapid manufacturing method, and also physical deposition methods, which are popular with the semiconductor device fabrications. So we looked at how to make electrodes out of any material, any substrate, because in electrolyzers, we typically use titanium as the electrode material because titanium is stable and highly conductive. So we looked at replacing those expensive titanium electrode material with low-cost materials. So in this method, we coat any substrate that can be chemically unstable, thermally unstable, but we coat it at low temperature with a metal like nickel. And then we use a solution process. We developed a solution process where a thin layer of the metal turns into the catalyst. So in the end, your substrate is fully covered with the nickel layer that protects the substrate. And nickel layer itself acts as a conductive layer to turn that into an electrode substrate. And you also have a catalyst that can make it catalytic electrode. So we looked at silicon because silicon is highly unstable in alkaline solutions. So you can see that we coated with nickel, turned that into a catalyst at the top layer. And you can see for oxygen evolution, good performances are obtained. So this method can be adopted on a range of materials. We looked at semiconductors like silicon gallium arsenide, metals like copper, which is unstable in electrolytes, and plastic like PET, stainless steel, copper mesh. All of them produced consistent performances, as you can see here, and also good stability. So our method is kind of adaptable for a range of substrates, and so we can also replace some expensive substrates in making catalytic electrodes. And another advantage of this method, we can regenerate because this is solution-based transformation, surface transformation. So we intentionally etched the surface. You can see that after solution-based catalyst deposition, and then etching, we can see the ore potential increase by a significant amount. That shows catalyst is lost. And then we simply dip it in the solution and able to regenerate. So we tried it 5 times, so which can be very useful when you consider industrial circumstances, because it takes a lot of effort in terms of maintaining those electrolyzers. So we also looked at physical deposition methods, sputter deposition in particular, and we looked at developing nickel-based catalysts. So the postdoctoral fellow in our group, Dr. Dodal Zhang, she developed this nickel nitride catalyst with sputter. And the sputtering technique is a facile technique, which is used in electronic industry. You have a metal target and you use plasma source to excite, sputter the material onto the target substrate. So in order to produce nickel nitride, we have nickel as a target and nitrogen in the nitrogen environment. And you can see that sputter can produce very controlled films, compact films, and also with nice, beautiful surface structures, pyramidal structures at the surface. And when we looked at its catalytic performance, as you can see here, the nickel nitride performance is comparable to that of platinum. Platinum is the standard for as a cathode material, so which is a very good result. And the stability also looked quite stable. You can see over three days of stability. And we further investigated the impact of different process parameters. So for example, here we try to tune the gas ambient, changing the concentration of nitrogen in the sputter chamber. And it impacted the performance, as you can see here. As you change nitrogen to different concentrations, the performance impacted. So we looked at further analyzing why this is happening. So we did some XPS analysis, and we found that when you change amount of nitrogen, it's introducing nitrogen vacancies. So by conducting further theoretical analysis, we were able to obtain the understanding that these nitrogen vacancies actually contribute to increased catalytic activity when they are present at an optimum level. So we went on to build laboratory electrolyzer prototype with these electrodes and able to test these electrolyzer performance of this catalyst at currents that are of industrial standards. For example, like 0.5 amps per centimeter square. So these catalysts remain stable with good performance. And then we looked at this work was carried by our PhD student Asta Sharma. This is also again using sputter-based system, and in this case we looked at developing hydrogen evolution catalysts. So the literature showed that having molybdenum and nickel combination can help to increase the performance for hydrogen evolution. So by looking at the sputter-based system using the same method, we were able to produce compact nickel molybdenum films. And the performance of these nickel molybdenum films, as you can see here, especially with the nickel underlayer, the dark ones curve is a platinum. So the nickel molybdenum is closely comparable to platinum. So that's a very good result. And again, nickel molybdenum at a proper optimized composition, we were able to obtain this good performance. So to conclude my talk, we so far relied heavily on traditional energy sources, fossil fuels, which using the process called combustion that produces heat, and then we turn that into useful work. But that also emits a lot of pollutants, which are causing the climate change. And the approach that we need to take, we need to transition to, is to go for sustainable energy sources, such as sunlight, wind, water, geothermal, and biomass. And we need to develop technologies for direct conversion of these renewable sources directly into electricity and fuels and into useful work. So this requires high-tech materials and high-tech technologies such as photovoltaics, water splitting cells, electrolyzers, batteries, and fuel cells. And I would like to acknowledge all my mentors, collaborators, and co-workers who contributed to these results, and the university, the Australian National University, for providing facilities, and Australian Research Council, Australian Renewable Energy Agency for providing funding support, and Australian National Fabrication Facility for providing facility access. Thank you, everyone. I'm happy to take your questions now.
Yeah, thank you, Dr. Sivakaturi, for the excellent presentation. And of course, you have covered starting from this hydrogen production and then the different ways to produce catalysts. So I'm not seeing any questions. Participants, do you have any questions? Yeah, there is one question from Sachin Kumar. What would be the source of what would be the source of hydrogen, and what is its implication on the greenhouse gases?
Yes, I think it's an important question. There is a lot of debate as well. If we use hydrogen, because the most common method to produce hydrogen, cheapest method, is using steam methane reforming. So that's again using fossil fuel sources. So that produces greenhouse gases. So that's where we need to, also transition hydrogen technologies to more sustainable approaches. So our research looks at these, sustainable approaches like electrolyzers, solar to hydrogen. Yes.
Yes.
So, yep, I hope that answered that question.
Okay, so there is one more question from Yan Jiang. What is your principle of choice of materials?
Sorry, what?
So I think his question is what is the basis in selecting materials for I don't know, he has not specifically given whether it is for hydrogen production or catalyst, but his question is in general.
I can answer more as a more general answer.
Yeah.
So there are two aspects. One is light absorption. So you need a semiconductor for that. And there are already proven semiconductors to absorb light efficiently. For example, silicon, which we use to produce electricity as rooftop solar cells. And the research is going on to produce more cheaper materials. Perovskites is one potential candidate. And yeah, that's one area of research. And other area is catalyst, because you need catalyst to convert electricity into hydrogen. And a lot of systems, existing commercial electrolyzers, they use like PEM, they use noble metals such as platinum, iridium, but they are very expensive. So there is now a focus on developing low-cost nickel-based catalysts. Nickel is very abundant and shown to perform very well. So in terms of catalysts, yep, there's also focus on moving away from noble metal-based catalysts to earth-abundant catalysts.
Yeah, thank you. Yes. Yes. So if there are no other questions from the participants, I would like to ask you one question. So you talked about this volumetric density of hydrogen. So could you please tell me what is the maximum volumetric density one can reach? Means when we talk about the storage of hydrogen, I mean the safest limit I'm talking about.
Yeah, I think it's a challenge to achieve high volumetric density. So the reason is hydrogen is the lightest gas, and yeah, compressing it takes a lot of energy. So one of the research is because compressing at high pressures requires materials that can withstand high pressures. So there are, based on the known materials, known technologies, there is only so much that you can achieve currently. But that's a research and active area of research in terms of finding materials that can withstand higher pressures and, where we can compress more. I can give like an example, a simple example that gives you a bit of, feel. There are now hydrogen cars. So those hydrogen cars can typically, when you fill the tanks, those hydrogen car tanks, that you can do like 6 kilograms of hydrogen. So whereas now, gasoline, diesel, petrol, you can do 50, 60 liters. So that's how much of a difference. But the good thing is that 6 kilograms of hydrogen can almost power similar range. To my knowledge, like Toyota, Hyundai, they have their versions, hydrogen fuel cell based cars. They can power almost 600 kilometers, because the efficiency through this process, hydrogen to fuel cells, and the losses are much lower. Whereas IC engines that uses the gasoline, for example, petrol and diesel, yeah, their efficiency is 20% or so. So yeah, I hope that answered your question.
Yeah, thank you. Thank you very much. Yes, if there are no questions, let's thank the speaker for his wonderful lecture. Thank you, Dr. Sivakarthuri, for sharing your time and for your wonderful presentation. Next, we will move on to the next talk. The next talk will be by Professor Vishwanath Balakrishnan.
Thank you, Chandramohan.
Yes, yeah, Dr. Chandramohan.
Yes, yeah. Good afternoon, Dr. Vishwanath. Let me Yeah, let me introduce the speaker. Professor Vishwanath received his PhD from Materials Research Center, Indian Institute of Science, Bangalore, and he gained a couple of research experience as postdoctoral fellow at School of Engineering and Applied Sciences at Harvard University, followed by second postdoctoral associateship at Department of Mechanical Engineering, MIT. He is currently associated with the Indian Institute of Technology, Modi, in the Department of, in the School of Engineering as associate professor. And his research interests revolve around vapor phase growth of one-dimensional and two-dimensional materials, phase transition, and nanomechanical behavior of functional materials. He has many awards and many high-quality publications to his credit. In the interest of time, I will skip the introduction, and with this, I invite Professor Vishwanath Balakrishnan to proceed with his presentation.
Yeah, thank you very much, Dr. Chandramohan, for the kind words. Let me also take this opportunity to thank the organizer, in particular Dr. Kiran, for inviting me to deliver a talk. I've been attending some of the talks. It's really very engaging, and a lot of talks in terms of advanced materials as well as mechanical behavior. So I, in fact, work in the junction between developing some of the advanced materials and also looking at both mechanical as well as some optoelectronic and energy applications. But for today's talk, I'll be try to focus more about the mechanics, the strain engineering aspects, without going to the other applications and so on. So this is our campus. We are in IIT Mandi. Typically, whenever I go, people always ask where it is located. We are located around 2 hours from the Kullu Manali. It takes about 6 hours from the Chandigarh. Before I start, I essentially thank all my students. The students are listed here. They are the one essentially produce this data, whatever I'm going to present today. There are 2 questions I would like to post, or I would like to probably discuss. When I say strain engineering across phase transformation or phase change, strain engineering as a tool, it is used for almost many different materials. How do we manipulate the properties and so on? So it become a nice platform or a tool. On the other hand, phase transformation is one of the fundamental concepts in material science. It's a century-old subject. We have a fair understanding of the basic thermodynamics and so on. So how do we connect these two things together? For example, can we measure the some of the mechanical properties across the phase transformation? That is what I have shown here in this particular plot. I'm taking vanadium dioxide as a model system. It is a well-established oxide, functional oxide, that shows the first order phase transformation. Around the phase transformation temperature, the structural phase transformation temperature, there are many exciting properties like electrical properties, optical properties, and so on. But we want to see, can we reliably measure the mechanical properties like elastic modulus, hardness, and also fracture toughness across the phase transformation. And many times it is also possible we can actually stabilize both metallic and insulating phases. Otherwise, I can also say rutile and monoclinic phases. So having this kind of coexisting phases, can we systematically measure the properties without having any artifacts? So that is one part of the presentation. Second part, I will also try to at least spend 10 minutes about looking at the 2D materials. There are many interesting aspects have been explored in the recent past, but at the same time looking at the defects and more importantly strain engineering aspects across the phase transformation in 2D materials, a relatively new topic. So we do grow this kind of a 2D materials like WS2, MOS2 by chemical vapor deposition. Then we again try to manipulate the properties. One is by using the strain. In this case, you can see here, nanoindentation has been used to kind of selectively introduce strain and also to kind of do a lithography or a nano sculpting to tune the properties. And also inbuilt heterostructures. You can see this particular fluorescence image. there are two different phases nicely self-organized in an external format. Again, there is a competition in terms of the lattice mismatch and growth stress. How do we stabilize this kind of metastable phases? And more importantly, how does the mechanical behavior changes when we have this kind of coexisting phases? So just let me start with the first one. How do we measure the mechanical properties? I already told you. In addition to that, whenever we have a phase transformation, there is also transformation stress involved. For example, nickel titanium shape memory alloy, we all know the shape memory effect. There is also transformation stress involved across the phase transformation. So can we also try to detect the actual strain or the actuation associated with the phase transformation, in addition to measuring the mechanical properties? And the last point is the combination of the defects and strain, how they are also to some extent help in stabilizing the metastable phases. That is something I would like to emphasize on the 2D materials. Let me just give a very brief introduction about the phase transformation. The first point is, why do we care about phase transformation? Because during the phase transformation, there are several properties can be reversibly tuned. So in this case, this cartoon, I plotted resistance and optical properties in the y-axis. In the x-axis, I plotted as a function of stimuli. The stimuli can be a temperature or electrical pulse or an optical pulse or even applying a strain. So the question is, can we use this kind of external stimuli to tune the properties reversibly? For example, the resistance can be tuned from high resistance state to low resistance state, because there is a phase transformation. In this case, the phase transformation in vanadium dioxide can be nicely tuned by heating and cooling around 68 degrees Celsius. There is also structural phase transformation accompanied by the metal insulator transition. It goes from monoclinic to tetragonal. Again, not only resistance changes, optical properties changes. So it's very interesting to see with the external stimuli just warming up around 68 degrees Celsius, or by electrical pulse, or shining a light, or simple bending, it is possible to tune the properties. So these kind of instabilities that essentially makes material more interesting. For example, structural steel and so on would be very useful for a mechanical and structural application. Of course, steel iron itself has many phases. We know about iron carbon phase diagram. But the question here is, if you have a instability, it is not necessarily bad. The instability can be exploited, especially for tuning the properties and achieving many functionalities. As long as the phase transformation is reversible, it is going to be very useful. And this phase transformation also found to be very fast. I think the inaugural lecture, Professor Sood was saying about vanadium dioxide, recent paper in Science, how they're able to do in situ electron microscopy and capture high speed, the diffraction pattern with the pulse of electric field and so on. So in this case, the phase transformation is found to be happening in a 50 nanosecond time scale. So the question I'm asking is, the phase transformation is interesting. A lot of properties can be tuned. Functionalities can be definitely introduced. The question is, how stable in terms of mechanical behavior? Do we really know the mechanical properties so that we can use them reliably for many robust applications? So again, just one quick slide, show the variety of different application, mainly for vanadium dioxide. It is already proposed to be a good material for actuators like nickel titanium shape memory alloy and piezoelectric material. The vanadium dioxide shows very high displacement to length ratio. So we can make a beautiful cantilevers. The cantilevers not necessarily in a millimeter length scale, even micron scale, even hundreds of nanometer scales, we will be able to produce good actuation. Similarly, this can be used as a gripper. Reversibly, we can change the shape and we can actually exploit the mechanical function. On the other hand, we can also use this for strain sensor. As I said earlier, because there is also electrical property variation across the phase transformation. When you try to impose some bending, accordingly, you can exploit the change in the resistance for detecting extremely small amount of strains. So the question is like the transformation stress I mentioned, that is what going to be very useful for actuators application, cantilever application, and so on. So the question is, how do you measure the transformation stress? Again, we have a Stoney's equation. It's more than 100 years old. In the form of thin films, by using the laser curvature method, it's an in situ laser curvature. By laser scanning, we can get the change in the wafer curvature. If you know the thickness and radius of curvature, something we can measure with the biaxial modulus, it is possible to find out the thin film stress. So what we have done, in fact, I have done this during my postdoc a long time before. I just try to develop a background and move on to the recent work. So the vanadium dioxide can be deposited onto a substrate. In this case, we are deposited on a silicon substrate. The moment we deposit thin film, the thin film is going to have a stress due to many variety of reasons, thermal mismatch, lattice mismatch, residual stress, and so on. After that, if you do a heating, during heating cooling, the thin film vanadium dioxide wanted to expand and contract because of the phase transformation. Because there is a volume change involved between the monoclinic phase and tetragonal phase. So this volume change would essentially impose a stress on the thin film. So that thin film stress can be measured as a function of temperature. So what I'm showing here is an exaggerated picture. The curvatures will not be that big, but it is a measurable quantity. From there, we can back calculate the actual stress in situ as a function of temperature. In vanadium dioxide, it shows around typically close to 400 megapascals of tensile stress. When I go from monoclinic to tetragonal, you can see the red color, the triangles. During heating, there is a tensile stress development. During cooling, again, it comes back. So we have a clear reversible stress change as a function of phase transformation. As I said earlier, the phase transformation is completely reversible at 68 degrees Celsius. Again, the stress can be very easily controlled. Not necessarily always we have to start from low temperature to high temperature. In between some temperature, like 77 or 81, we can arrest the temperature, we can come back. So the total transformation stress can be systematically controlled to achieve a required disparate actuations. Again, this particular phase transformation shows a very stable stress switching. At 50 degrees Celsius, it is compressive stress. At 90 degrees Celsius, it shows tensile stress. So by going from 50 to 90, again 90 to 50, any number of time we are able to reversibly tune the stress. We have done this experiment only for 100 cycles, whereas the electrical measurements already shown the phase transformation is stable for around 10 power 6 to 10 power 8 cycles. As I said earlier, we have a now transformation stress because the thin film is developed on the substrate. If you make the substrate very, very thin, like otherwise if you can make a cantilever kind of a substrate or electron transparent substrate, of course we'll be able to see there will be an actuation right, essentially happening on the cantilever of the thin film structures. So the question is, how do we visualize and measure the actuation using in situ transmission electron microscope? We have prepared the cantilever of silicon using the focused ion beam and deposited vanadium dioxide thin film. And the same TEM holder, only thing is we are going to have a heating holder. Instead of having a static specimen, we are going to have a dynamic specimen. Dynamic in the sense, during the heating, the cantilever is going to go up and down. So when the cantilever is going up and down, accordingly, there will be a change in your focus. Inside the TEM, the defocus can be very precisely controlled with the precision of few nanometers. So without worrying about the regular optical limitation, if you are using an optical microscope and so on, what we can measure is very small. In TEM, the defocus can be very precisely measured down to nanometers. So I have measured the defocus as a function of temperature as the cantilever goes up and down during the heating experiment, heating as well as cooling experiment. Then I do the same experiment, one from the tip, one from the base. So if I just take the difference between the cantilever deflection at the tip and the base, I can get the actual cantilever deflection, which can be plotted as a function of temperature. So again, you can see it is not a stress now. The actual visualization enabling the measurement of deflection in terms of hundreds of nanometers. Again, the phase transformation going from insulating to metallic, we know from the electrical properties. By looking at the electron diffraction pattern, we can also confirm the phase transformation happening from monoclinic to tetragonal. So TEM is great. We can of course get down to the very small numbers for measuring and detecting the actuation across the phase transformation. But there is also a penalty, right? We need to make an electron transparent sample. Many times sample preparation become a difficult task. So the question I would like to ask here is, can we measure these kind of actuations in a bulk single crystalline samples during the phase transformation? In that case, instead of using a TEM, can we use conventional nanoindentation, not for measuring the mechanical property, but actually measuring the actuation during the phase transformation? So this is what we have done. We have a same isotron nanoindentation we have. Just a small trick we have done to do a kind of experiment. So typically in a nanoindentation, we have a very sharp tip, diamond tip, that will be essentially like approaching your sample, and with whatever load we apply, maybe hundreds of say micronewton, it will essentially like do a penetration. We'll have a load displacement curve from where we'll get the elastic modulus and hardness. So in this case, what we are interested to measure the actual expansion and contraction of the crystal during the phase transformation. So what we have done during the actual loading cycle, so we have a loading cycle. After that, there will be a holding, right, a holding segment, then again unloading segment. So we essentially wanted to bring the tip with a very, very small load. We applied our only like a 25 micronewton of load, and essentially keep the contact on the sample, just approaching the sample and making a gentle contact. Then keep there for a long time. The loading segment, just keep it for a long time at a hold. During the hold duration, we heat the sample. So in this case, we heated the sample from 64 degrees Celsius to around 65 to 75 degrees Celsius, because we know phase transformation is going to take place around 68. So what is going to happen? The tip is in contact during the phase transformation. Because we are heating, of course, if the crystal is expanding, the tip will be pushed up. If the crystal is essentially contracting, the tip is going to or allowed to go down. So it is possible to capture the actual tip displacement during the phase transformation because of the expansion and contraction taking place in the vanadium dioxide single crystals. So what you see here as a red color curve, this is a tip displacement. Like you can see around 600 nanometer of tip displacement during the heating. And again, during the cooling, you can see it is reversibly going back. Compared to the cooling, the heating is more reliable, because during the heating, whatever like the crystal is slightly expanding, so the tip will be always in touch. Whereas during the contraction, sometimes it is difficult to make the contact. But we are able to clearly see there is a small difference between expansion and contraction due to the measurement limitation. Otherwise, we are able to probe the actual displacement. From there, we are also able to quantify what is the actual spontaneous strain across the phase transformation in vanadium dioxide. We already know the orientation of the crystal by EBSD. It is a 0-1-1 orientation. In that orientation, we see around 0.5% of change in the strain, and which is also reversible in this case. The other point is, like we looked at the literature, though the vanadium dioxide is a well-established, well-studied system in terms of physics for 4 or 5 decades, The actual mechanical behavior is not very much studied. There are few papers reporting the mechanical behavior at room temperature, but during the phase transformation, how the mechanical behavior changes, there are not much reports. There are some scattered in the values of elastic modulus and hardness. So what we have done, we have systematically done the indentation as a function of temperature. You can see here at 69.2, like 0.4, 0.8 and so on, there is a gray color region. It is a metallic domain, whereas the white color region is the insulating domain. So at the phase transformation temperature, it is possible to stabilize both metallic and insulating phases. So we can do indentation both from the metallic domain and insulating domain and see what is the actual change in the elastic modulus, hardness, and also fracture toughness. How do I know it is metallic and insulating? So we can actually do the IV measurement. We can clearly confirm it is metallic and insulating. We also do a Raman measurement to make sure there is a phase transformation. One is essentially metallic, another one is insulating, because in metallic, Raman modes would essentially disappear, whereas insulating monoclinic phase, you will see all the possible Raman modes. So I'll probably, like, for a benefit of time, I will avoid the Raman spectroscopy. It is just to confirm there is an in situ phase transformation. And more importantly, we are clearly able to see abrupt change in the elastic modulus, around 15 to 17 gigapascal of abrupt change when I go from metallic to insulating phase. In this case, the temperature is fixed. Only we are doing systematically indentation across the phase boundary from rutile to monoclinic. Clearly you can see the abrupt change in the properties. Same with the hardness. The hardness we found only like a 1 gigapascal of change. So the hardness and elastic modulus, both we are able to explain, taking the actual changes in the crystal structure, in the bond length between vanadium and oxygen and so on. At least we are able to reliably measure the mechanical properties across the phase transformation. I will come back to the fracture toughness measurement as well. But before fracture toughness, I also want to show you quickly the same vanadium dioxide. We also studied the mechanical behavior during the Split-Hopkinson ice strain rate. The Split-Hopkinson is typically used. There is a striker bar and incident bomb. The bar, the pulse, stress pulse essentially will be transmitted in the velocity of sound. Because of our sample, how much is transmitted, how much is reflected. From there, we can find out the properties, especially the stiffness, and also the stress strain curve can be also computed or calculated from the measurement. Only thing is, this measurement, we have done one at room temperature, one at high temperature. We want to see how the properties at high strain rate changes, monoclinic phase as well as at insulating phase. So you can again clearly see the variation. In this case, we have not done on only a vanadium dioxide single crystal. We reinforce this kind of single crystal into a polymer matrix. We use the high molecular weight polyethylene as a matrix. So when we tried this measurement, we could clearly see the actual stress, right? If it is only polymer at high temperature, you will see the stress strain curve. It will essentially, like, the compressive strength will be smaller, because polymer, right, being thermoplastic, it will essentially there will be compromise. But when you introduce the vanadium dioxide, you can see the trend is reversed. At high temperature, the vanadium dioxide shows better compressive strength. That is because of the phase transformation. We have a higher modulus as well as hardness contributing for the higher mechanical behavior at the high temperatures. We also looked at the X-ray computed tomography during the Split-Hopkinson high impact test, whether any damage happened to the crystals. Indeed, we see there are some crystals came off from the matrix, and some of the crystals also shows the fracture. Then we thought maybe we should also look at the fracture more closely. The fracture toughness of vanadium dioxide, in my understanding, there are not even a single report that reports the fracture toughness across the phase transformation. We did the indentation at both room temperature as well as above the phase transformation temperature for monoclinic and tetragonal phase. Of course, we are able to see the crack lengths and so on. Taking the crack lengths, we try to calculate the fracture toughness. there is a difference in fracture toughness, but the fracture toughness values are extremely small, right? Almost like appear to be erroneous in values. We are initially like puzzled what essentially makes this vanadium dioxide to break at such a very, very small loads, having such a poor a fracture toughness or very high brittleness. Then later on, we found that the vanadium dioxide in this case grown on quartz substrate. During the growth itself, you can see there are many crack patterns, which essentially tells the vanadium dioxide are already pre-stressed condition. Then we try to calculate what is the actual stress present in the vanadium dioxide, taking the thermal mismatch between the substrate and the actual vanadium dioxide. It turns out that around 0.95 gigapascal of thermal mismatch stress, tensile stress is imposed on vanadium dioxide. Since the vanadium dioxides are already in the high tensile stress behavior, even a small amount of load is sufficient to crack this particular crystals. So again, we use this particular formula, accommodating the residual stress and also the phase transformation stress into the conventional fracture toughness measurement expression. And we found that there is a 32% of enhancement in the fracture toughness. First thing, we are able to get the correct fracture toughness after putting the residual stress. For monoclinic phase, it is around 2 megapascal out of n, whereas for tetragonal phase, it is 2.67, having around 30% of enhancement across the phase transformation in vanadium dioxide. I do not know how much time I have. Maybe like quickly, I'd like to cover how the.
Yes, you have another 3 minutes.
Okay, maybe quickly, like I'll show you where the 2D materials and the strain is important. The 2D material, it is possible to have this kind of beautiful metastable phases. The dark one is essentially a 1T phase, and the bright one is a 1H phase, and the crystallography and those are still kind of poorly understood. But the question I'm going to ask is how the fracture of the 2D material will change instead of having only homogeneous 1H phase if you have two different phases together. So I call this as a heterostructure, and how the mechanical behavior will change. What we found is when we have only the 1H phase, again due to the same thermal mismatch stress, they are extremely brittle in nature. You can see there are many small voids are present. The voids essentially nucleate the cracks, the crack initiates, and completely the material become fractured. Whereas when we have a heterostructure of 1H and 1T, what we found is the defect creation is also relatively small because the structure is already stable. There is a inbuilt stress because of the maybe mismatch, lattice mismatch between 1H and 1T. There is an inbuilt compressive stress that seems to compensate your actual thermal mismatch stress. Thermal mismatch stress is tensile in both the cases, but when we have a heterostructure, the heterostructure from the Raman, we are able to see there is an inbuilt compressive strain. So that indeed helps to avoid this kind of fracture in the heterostructure. Whereas in a only 1H phase, they are very quickly getting fractured because of this kind of voids introduced due to the defects. I'll also probably quickly go through the defects and voids. We also looked at very carefully because these are the voids essentially responsible for initiating the crack. But at the same time, these kind of voids also have interesting properties because of the tungsten and sulfur termination. We are able to get different optical properties. So we know exact termination. And finally, we thought, can we also use nano indentation to desperately put this kind of voids? So that is what's shown here. Probably this will be my last slide. So the nano indentation in this case used for selectively inducing the strain. We can make any patterns we want, like this kind of square pattern, or we can also write like IIT. In this case, it's almost used as a tool to do a nano sculpting. The material is removed, but interestingly, we are able to manipulate the optical properties, right? Wherever we have done the indentation, there in this case, we are able to introduce a dark state. So the nano indentation can be used for introducing defects as well as this kind of nano sculpting. And also, I already told you, can be also useful for measuring the actual thermal expansion, not exactly thermal expansion, at least the the spontaneous strain across the phase transformation and so on. So there are several things still we are exploring, we do not know. But one thing is for sure, the strain as well as the phase engineering aspects that required more than one technique, several allied techniques, and also possibly simulations tools to develop clear mechanisms. I feel there are a lot of scopes in the area of strain and also the phase transformation applied to conventional materials, including the latest 2D materials for a variety of applications and so on. I'll stop here by thanking the funding agencies. I'll be happy to answer any questions you have. Thank you.
Yeah, thank you, Professor Vishnath, for the wonderful talk on the mechanical behavior of these systems. So you started with the model system vanadium pentoxide and explained nicely to the basic how one can perform this measurement. I mean, how one can measure the mechanical behavior in the phase transformation regime. And of course, I was looking for more from the 2D materials aspect, but anyway, so nice to see all those stuff. So we have a question in the chat box. There is a question. Could you please comment on strain measurement during transformation of retained austenite to martensite in high strength steels?
Yeah, we have not done that, but definitely, like, of course, if we can take a simple iron carbon diagram, we have all possible phase transformation. I think there are a lot of already studies on steel looking at the austenite, martensite, and also the bainite and so on. But I'm not very sure in situ. I think I'm sure like people also looked at the properties across the interface, systematically doing indentation and so on. But at high temperature, reversibly, I'm not very sure. But I think there are lots of work already on steel, looking at the phase coexistence and also the mechanical behavior. At least dynamic modulus mapping already have been done. Only thing is from there, getting the expansion and contraction, that I am not very sure, like that is done or not. That way, it is a very good question. We can actually take a steel, focus on a particular phase, and try to see, during the phase transformation, is there any expansion, contraction, whether that can be captured using the nano indentation. That seems to be an interesting question. We have not looked at. Maybe a definitely interesting problem to look at.
Thank you. Yes, actually, I have a question. So, in the case of vanadium pentoxide, I think you mentioned you measured a displacement of approximately 60 nanometer during the phase transformation at that particular temperature. So, my question is whether the displacement of 60 nanometer is mainly due to the phase transformation, or it is due to the initial stress or strain which comes in during the deposition of the flame.
Yeah, I think if you are referring to TEM measurement or a nano indentation measurement.
Nano indentation, yes. Yeah, this one. Yeah. This next one. Yeah.
Right. Yeah. So these are like a big crystals. I think I have a movie to show. I did not show the movie. These are like typically like a millimeter size crystals. After, of course, many times we grow on quartz, but it easily can detach. Almost like many measurements also can be done like a freestanding. So the thermal mismatch stress from the substrate may not be a problem here. Whereas for the vanadium dioxide grown on silicon substrate, there of course there will be an initial residual stress. In that case, we have to calibrate. So whatever initial at room temperature, the deposition stress will be there. Once we know how much is the stress, then during the heating, we should only look at the actual stress or the strain happening across the phase transformation. So this particular portion will be free from your residual stresses at the junction where, at the proximity to the phase transformation temperature.
Okay, yeah, now I got the point. And my question is, for example, if it is a thin film on a substrate, so then can we say that this is only because of the phase transformation?
Yes, yeah. So what we do is for even the wafer curvature method. So after the deposition, like before the deposition, we do a wafer curvature measurement for the bare substrate. Then after the thin film deposition, again we repeat the same measurement. That difference will actually tell you what is the actual residual stress imposed during the growth. Once that we know, after that again we have to do the wafer curvature measurement as a function of temperature. Then again we can capture only the stress change happening due to the phase transformation. So if you look at this particular picture, like initially I'm showing monoclinic around 250 compressive stress. So this stress is essentially coming from the residual stress. But during the heating, whatever we are probing, that is going to be coming from your phase transformation. So to answer your question, Dr. Chandramohan, we can easily decouple the residual stress from the phase transformation stress by doing the careful measurement, taking the initial bare wafer, then subtracting the values, then we will be able to split this two.
Okay, thank you very much for clarifying my doubt. And one last quick question. So when like you talked about this heterostructure, I mean 1T and I mean that WS2 case.
Yes.
Yes, and is that because the coexistence of 1T and 1H phase is because of the growth, or I mean how to control the coexistence of these two phases in the same material?
Yeah, so this is like again a very interesting topic. So typically, like what I understand is the phase difference, the allotropic phases. If I take the 1H phase, WS2, we have a tungsten sandwiched between two sulfur layer. Typically, like gliding, there will be a shearing of the sharing of the sulfur layers. So typically, like people are using lithium ion intercalation, right? We need to essentially introduce some shear and 1T to 1T prime, some bond distortion. There are several approaches reported in the literature, starting from lithiation, some cases doping. In our case, what we are doing is there is a small amount of sodium doping. In XPS, we are able to clearly see that. So we need to have some distortion. There is also another possible mechanism by the doping of electron. With respect to the electronic band structure, if you put a donor dopant, which essentially provides the electron, again your 1T phase can be stabilized. So otherwise, the 1T phase is thermodynamically not stable. By imposing this kind of doping or lattice strain or electron donation, it is possible to stabilize. So in our case, answer to your question, we are able to stabilize because there is a small amount of impurity that is kind of stabilizing the 1T phase.
Okay, very interesting. Thanks a lot. Yeah, so if there are no questions, let's thank the speaker for his excellent presentation. Thank you, Professor Vishnath, once again. So we will move on. Yeah. So now we will move on to the last talk. The talk is by Professor Koteshwar Rao. Professor Koteshwar Rao had his academic training in metallurgical and materials engineering, and he obtained his PhD, MTech and BTech degrees from the North Carolina State University, Raleigh, USA, IIT Kharagpur, and JNTU Hyderabad, respectively. He did his postdoctoral work in the University of Michigan in the year 2007, and subsequently he moved to University of Southern California, Los Angeles, USA for his second postdoctoral. And he has been with the School of Engineering Sciences and Technology of University of Hyderabad from 2009 onwards, and he is currently a full professor. His research interests include nanomechanics, high entropy materials, friction stir welding and processing, additive manufacturing, advanced high strength steels and superalloys, and so on. He has several awards to his credit. I'm not going to read all. Few I'm going to read it. His academic and research efforts were basically recognized by several national and international distinctions, such as Fellow of Chulicana Academy of Sciences in the year 2018, Weld Specialty Award of Indian Institute of Welding in the year 2018, Chancellor Award of UOH in 2015, the James Clerk Maxwell Writers' Prize of Philosophical Magazine Letters for highly commended article in the year 2014, and INAE Young Associate Young Engineer Award and Alpha Sigma MU Award in 2004, and so on. So with this brief introduction, I welcome Professor Koteshwar Rao. I request him to start his presentation.
Yeah, thank you, Dr. Chandra Mohan, for the generous introduction. And first and foremost, I would like to thank all the organizers for giving us a chance to present our recent efforts in this conference. The work that I'm going to present here is the outcome of the two of my PhD students, and most of it is unpublished. The work is on the refractory high entropy alloys. So coming to the basic definition of the high entropy alloys, normally the conventional engineering materials are single element based. For example, in aluminum alloys, aluminum is the major element. In copper alloys, copper is the major element. In steels, iron is the major element. In nickel based superalloys, nickel is the major element. But this is something new. The concept itself is new, that that has emerged in the last 15 years or so, where you give equal importance to all the elements present in your composition. That way, when you have 5 or 6 elements that you want to target to make an alloy out of, then all the 5 or 6 elements should be equal in proportion with respect to the composition. That's how this concept has emerged. And by doing so, we have seen a lot of unprecedented mechanical properties, at least in the last 15 years, out of various alloy systems. And the basic definition so far has been like this, that if you have a system, an alloy system, where the concentration of the alloying elements varies from 5 to 35%, you can call it as a high entropy alloy. And also based on that, if you can look at the configurational entropy based on the Boltzmann equation, S equal to KL and omega, then it turns out to be about 1.5 R and so on. And based on the delta S configuration, these were classified into low entropy alloys, medium entropy alloys, and high entropy alloys. Of course, the definition itself is debatable as of now. And based on the basic nature of the development of these alloys, people have predicted that the high entropy that comes out of the presence of the various number of elements that in equal and high proportion in a concentrated manner could bring in some kind of disorder in the form of entropy, and that would itself give you some kind of new properties, be it mechanical properties or functional properties. And also, since you have the presence of wide variety of elements with variation in their atomic sizes and the melting points, there could be a sluggish nature with respect to the diffusion of any diffusing element in the given lattice. That would itself bring in some kind of a novelty to the properties that you would look at. And also the atomic radii of the various participating elements could be different. And that in turn brings distortion to the overall final lattice. And that again creates some kind of, again brings in some kind of novelty to the properties that you observe. And the majority of the new properties that people have seen in the last 15 years or so were successfully explained using this last discussion by considering various models. And moreover, here, and before I say this, I want to also bring in a topic here that majority of the cases have resulted in a solid solution, unlike the formation of an amorphous solution, amorphous material, or any other composite kind of structure. People have observed that you see a simple solid solution in majority of the alloys that people have targeted. And since you have the mixture at atomic scale, the properties that you observe could be coming from the presence of all these elements and the mixture thereof at the atomic scale. These are all only proposals in the beginning, like 10 to 15 years ago, but slowly there was a refined wisdom in the properties that people have seen. And as I mentioned before, in various LI systems, people have seen that you get some kind of unprecedented mechanical properties that you have not seen before in these new LI systems. The basic thing that I want to bring your attention to here is that the small e, niobium, tantalum, tungsten, and the LIs thereof. This is what most of the presentation is going to be. And this LI is targeted for very high temperature applications in order to push the limits that are imposed by the nickel-based superalloys, which are being used for the gas turbine engine applications. But again, this LI system, which comprises of very high melting elements and also high dense elements, which are of BCC structure, pose a lot of problems with respect to development, processing, and then subsequent applications. And most of these efforts were carried out by Dan Miracle and Oleg Senko. As I mentioned just now, that the nickel-based superalloys, their operating temperature is around 800 degrees centigrade as of now, and they are reaching the theoretical limits. If you want to have the performance of these gas turbine engines increased beyond the limit that are currently in place, then you need to operate these engines at high temperature and high pressures. That again demands the adoption of the new set of materials compared to the already existing materials. And then the only way is that you have to look for the a material which is very strong at very high temperature compared to the present temperatures of operation. And these nickel-based superalloys normally melt at 1200 to 1300 degrees centigrade based on the various alloying elements, because nickel melting temperature is around 1400 degrees centigrade. And as I mentioned before, our target has been towards the applications, gas turbine applications. So the moly, niobium, tantalum, tungsten system in equal proportion, people have seen, they have prepared several LIs using different processing routes, be it by traditional melting and casting route, or the powder metallurgy route, where you start with powders and then compact and see what sort of microstructures you have obtained, and that resulted in the properties that are seen. The efforts that we do at our lab are like this. We are looking at the concentrated alloys and also varied length scales with respect to the microstructural length scales, starting from where the grain size, the average grain size is about tens of microns, tens of nanometers. And our efforts till now has only been the experimental part. And soon we are also trying to understand the properties that we have seen using some kind of simulations. And we develop our own materials in our lab and test them. Here the schematic in between is just to show that this is a pseudo ternary diagram where our interest is in the middle of the phase diagram, where all the elements are equally represented, or at least near equally represented. The LI systems that we have studied and also that I'm going to show it to you today are like this: moly, niobium, tantalum, and titanium, tungsten, and also moly, niobium, titanium, and also aluminum, copper, tantalum, barium, tungsten. If you see, the literature till now was mostly concentrated on the presence of the moly, niobium, tantalum, and tungsten. But then we purposefully added titanium to it and see what sort of microstructures would develop that would lead to the properties that are of interest. And then subsequently, based on our understanding of the microstructure and the properties that we have realized, we have developed moly, niobium, and moly, niobium, titanium, and also various other LI systems that I'm not going to show here. So our efforts have resulted in the realization of either single or multi-phase structures in these concentrated systems with varied microstructural length scales. Initially, this moly, niobium, tantalum, titanium, and tungsten system with equal proportion of all the alloying elements, we started to do the ball milling. We wanted to see that the mixing would happen really well. Otherwise, if you see moly, niobium, tantalum, and tungsten, their density is above 9 and 10 grams per cc, whereas titanium's density is about only 4.5. So if you adapt traditional melting and casting route, there is each and every possibility that there could be a segregation. Then it would not serve our purpose. We wanted to see where the titanium really goes. So for that purpose, we did this, we processed the cell using ball milling at room temperature. And initially, if you see this diffraction pattern in the beginning, you see that the presence of all the alloying elements that we started with. And then 30 hours of ball milling, you see that we have only a single phase BCC structure. And I just want to bring your attention here that moly, niobium, tantalum, and tungsten are of BCC structure, whereas titanium is HCP structure. Nevertheless, finally, even the titanium also has become a part of a new BCC lattice. And then to study the mechanical properties in either reasonable or a meaningful way, we need to compact these powders to at least near theoretical density. Then we adapted the spark plasma sintering in collaboration with ARCI, and that resulted in the formation of three different phases. And here, these three different phases are totally different from the as-milled phase that we have seen. So we have seen one BCC phase and two FCC phases. And this is the BSE imaging contrast that you see that the dark one is the FCC phase, and the gray one is the BCC phase, and again the bright one is the FCC2 phase. And you see that the particle size, if you observe it here, they're about submicron range. And this is just the color coding to show the presence of the three different phases and their relative proportions. BCC accounts for about 47% of the whole proportion, and FCC1 accounts for 16%, and FCC2 accounts for 36%. And the compositional variations are like this. The initial composition is here, it's nominal, all equal in proportion with 20% contributing each. And the gray phase, which is BCC in crystal structure, has some presence of all the elements. And again, the dark one, which is FCC, has the major proportion as titanium, and the other one, FCC2, is also similar as BCC. But the only problem here is that iron has come in, which we never added in the beginning. But this has come from the milling media as a contaminant. And when we try to understand the hardness variation in these relatively bulk samples using micro hardness at various loads, we see that we got a hardness as high as about 18 gigapascals at a low load, and also it got saturated, and then it leveled out around 13.89 gigapascals. And this is really exceptional compared to all the literature that is published on the cell life system, be the microstructure at a coarser length scale or the finer length scale. This is the highest reported so far on this in the cell life system. And then you also see that there is a pronounced indentation size effect where your hardness is very high at low loads and then kind of low at high loads. And you also see that at low loads, there is a precipitous decrease in the hardness, which shows that you have a pronounced indentation size effect. And our main intention to add titanium in the cell life system was to decrease its overall density. And then when we try to understand the mechanical properties normalized with the density in these different alloy systems that are reported so far, we see that the data that we got here is the highest reported with respect to the hardness versus density, density normalized hardness. In this here itself, you see that you have a remarkably high hardness, which is absolute in nature. And here, even if you look at the density normalized hardness, that's also remarkable. And here, the squares are rectangles. I think it is a rectangle. They are all from the melting and casting route, where you see we have the microstructure in the coarser length scale, and these dots are having some kind of finer microstructure length scales in various alloying systems. And irrespective of all that, the one that we have has got a best properties so far. And most of these details are we have mentioned in this MSCA paper. And then when we try to understand the different contributions of various microstructural features in the cell life system to the overall hardness that we have seen, we have observed that both the solid solution strengthening and Hall-Phase strengthening are the dominating factors here. Because in the solid solution strengthening, you have the presence of all the alloying elements in all the three phases. It's not that one phase is devoid of any of the alloying elements, including iron, that which has come into the system unwantedly. So while evaluating these different contributions, we also considered the presence of iron. We have not neglected that, because after some time we have accepted that that is an alloying element as well. So essentially, it has become a 6 element system, although we started with a 5 element system. And the contributions from the frictional stress and also strain hardening that comes from the intersection of dislocations and the grain size strengthening, soil strengthening are all the various factors that we have considered. And to try to understand the indentation size effect, we looked at the Myers analysis, which shows that we have a strain hardening index of about 1.82. That shows that we have a indentation size effect. And we have explained the indentation size effect using the generation as well as the intersection of the geometrically unique dislocations in all the three phases, which come in contact with the indent during the indentation in the Vickers indentation. And this is the analysis that we have adapted after the Nix and Gav. And these are the different indents that we have done at various loads. And it shows that our depth independent hardness is about 11.8 gigapascals. And the characteristic length scale over which the indentation size effect would prevail is about slightly more than 1 micrometers. And this is, in a nutshell, you have a chemically homogeneous system because all the three phases have got all the presence of all the elements, but you have a plastically non-homogeneous region owing to their different crystal structures and also different microstructure length scales. And then we try to, because it's kind of a well understood microstructural features in case of moly, niobium, tantalum, and tungsten, but we added titanium and iron came in unwantedly. So the new effects that we have seen, we wanted to see where exactly this is coming from. Is it because of the iron or the titanium? And then I also want to bring it to your attention that iron is BCC in crystal structure and titanium is HCP. And also both are relatively low melting compared to the rest of the aligning units. And then we melted because the powder processing route has brought us the iron in a proportion that we never anticipated. And here in the traditional melting and casting route, we melted the moly, niobium, tantalum, tungsten, and also one with iron, and also one with titanium, and also one with titanium and iron. So we see that the basic BCC structure will be retained with the presence of some minor other phases based on the alloying elements that we have added. And also, if you see the hardness variation, one with titanium and one with the titanium and iron, sorry, titanium and iron, you see that the one with titanium and iron will have a higher hardness value compared to the one without iron. And this predominantly is coming from the solid solution effect. And again, these are some of the analysis to show that again the strain hardening occurs and all that. Now, since in a 5-element system, we know that titanium has done some magic to bring out some kind of a novelty to the overall mechanical properties. Then when we try to understand what exactly happens to the phase formation and also the phase stability with the addition of titanium to these two relatively high melting elements, we started with the binaries that we need to proportion. So the one alloy that we developed is moly niobium 50-50, and the other is moly niobium titanium with all equal proportion of 33, 33, and 33. So this is the sample that we prepared using our traditional melting and casting route. And to our pleasant surprise, what we have seen is that it's a single BCC structure, irrespective of whether there is a titanium or there is no titanium. And when we homogenize the structure at 1200 degrees centigrade for 24 hours, even then, no phase changes happened, but only microstructural changes happened. And titanium did not alter the phase structure. A single and stable BCC structure is obtained. And when we try to understand the grain structure and their size, we see that here in the moly niobium, the as prepared condition, the average grain size is about 115 micrometers. And then when we added titanium to it, the as-cast condition, the grain size is refined to 34 micrometers, a remarkable grain refinement by the presence of titanium. And also the one with the after the molybdenum niobium material, when we homogenized it at high temperature of 1200 degrees centigrade for 24 hours, we didn't see any considerable change in the average grain size. And also here in this case, also it's moly niobium titanium, also there is no change in the average grain size with respect to the as-cast condition. So the titanium has stabilized the grain structure in the as-cast condition itself, but further changes have not happened even exposing this material to very high temperatures. And when we try to understand the hardness variation in these alloys with titanium and without titanium, and also with heat treatment and without heat treatment, we see that the hardness has kind of remained in the same ballpark at about 4.6 to 4.8 gigapascals. And then when we try to understand the density normalized hardness the way we have done before, we see that these are all the data points that came from the systems that have got at least 4 elements in equal proportion. You have moly, niobium, tantalum, titanium, vanadium, and so on. But our 2 systems have got 2 elements in one case and 3 elements in the other case. In each case, you see that we have got a really remarkable density normalized hardness. Then again, it poses a question that do we need to look for the development of LIS by adding so many elements in equal proportion? I think we can again refine our thought process here by resorting to by adding the allying elements in the either 2 element or 3 element as principal elements, and then look for minor allying additions to see that you get the desired properties. And then when we try to understand the mechanical behavior at even the finer length scales using high-speed nano notation, we see that here these are the details about the mapping that we have done on these 2 LI systems, one with titanium, one without titanium, and also as cast and heat treated conditions. The applied load is about 1.8 millinewtons and number of indents are about 1600 in each map. And we see that there is a slight segregation of niobium in molybdenum case, and also the this is the SEM image. The same was converted into this kind of a map using EDS data that we have obtained, and also the MATLAB code. And this is the nano indentation hardness data that shows that you have a higher hardness wherever the niobium segregation is there, and that is again prevalent with respect to the modulus as well. And you see that wherever you have a this is coming from the line scan here, and that shows that you have a higher hardness wherever you have a niobium presence, and then later on it gets saturated over the rest of the sand. And same thing here. This is with the under the heat treated condition, but you have we could capture the data from 2 different neighboring grains, and then that shows that there is a orientation difference which got reflected in the modulus data, and then hardness data and then EDS data are going hand in hand, and then wherever the niobium presence is there, we have the higher hardness. But with the addition of titanium, the best part that we have seen is that niobium presence is not seen as a segregation, but instead we see some kind of needle-like structure, which is dominant with respect to titanium presence. And then this titanium presence also has given us both high hardness and then high modulus. You see here, wherever hardness is high, the titanium is also high, and at the same location, the niobium content is kind of depleted. And then the same sample, when you try to homogenize, you see that the titanium presence has got more pronounced, and that again got reflected in the both EDS mapping and nano hardness mapping, and also the line scan that we see here, that wherever the niobium presence is low, or alternately titanium presence is high, we have got the higher hardness. So we see a good correlation between the EDS and the local mechanical properties, and the higher hardness regions are coming from either niobium rich region in molybdenum sample or titanium rich regions in molybdenum and titanium samples. And we don't see much change in the modulus either with respect to the heat treatments or with presence of titanium or without titanium. But the only difference we have seen is that whenever there is a orientation, the modulus difference was seen. Orientation difference between the 2 neighboring grains. In the other case, rather than keeping moly, niobium, tantalum, vanadium, and tungsten, we wanted to replace this moly, niobium with the relatively softer metals, which are aluminum and copper, to see what happens in these systems. Then, when we subjected these systems to ball milling, then after 25 hours of ball milling, we see that we got a single phase BCC structure. And then when we tried to compact this powder in SPS at high temperatures, we saw that there is a multi-phase structure that has evolved. And then this is the microstructure of this multi-phase structure, and the corresponding EDS analysis is shown below. We have a mixture of bright phase and also 2 FCC phases. One is out of that, one is ordered. And then when we are trying to measure the hardness using Vickers indentation, we saw the cracks everywhere. Then we try to measure, rather estimate the fracture toughness from the cracked sample by measuring the crack lengths using SEM. That shows that the fracture toughness is about 8.3 MPa root meter, and also the micro hardness is 13 gigapascals. And this is a reasonably good combination of hardness and the fracture toughness. If you see here, we have compiled a lot of data from the literature that includes carbides, nitrides, bulk metallic glasses, ceramics, ceramides, and several other brittle materials. And then you see that we have a right combination of high hardness as well as reasonably good fracture toughness in this new system. That would be coming from a relatively harder phase, which is obstructing the crack propagation through a softer phase. And these are the crack paths, which is a tortuous, and you see that the crack taking some kind of zigzag path, and also crack diversion here when it faces the hard particle. And that could be the reason for the high, relatively high fracture toughness that we have seen. So in these concentrated systems, our efforts have shown that we could make near infinitesimal composition, near infinitesimal compositions can be made, but the only thing is that we should judiciously select the alloying elements which would offer the properties that we are envisaging. And also not only just the experimental effort, but the combined and integrated effort with simulations also would offer us better insights before doing too many experiments. And since we are adding so many elements in a larger proportion, even recycling of the samples which are done should be the need of the hour, even at laboratory scale in future. That is our opinion at this moment. And I would like to acknowledge my PhD student Dikshit and former PhD student Dr. Ramya for the because they both have executed work that I have presented here. And Dr. Sudarshan Fania of ARCI, Anjali, Harita, and Sai Karthik, who are also at ARCI, and they are part of the work that I have presented here. And my sincere thanks to them. And my collaborator and senior colleague here at UH, Professor K. Bhanshankar Rao, for many useful discussions on high temperature materials and nickel-based superalloys, and also these systems. My gratefulness to him. And the funding bodies, our Institute of Eminence and DSTPAS and DSTPs, which have offered financial support either directly or in the form of equipment while executing this work. And with that, I thank you all. And if there are any questions, I would be happy to take. And once again, my sincere thanks to the all the organizers which for the invitation, which allowed us to present some of our recent efforts here. Thank you. Thank you all.
Yeah. Thank you, Professor Koteshwar Rao, for the insightful presentation on superalloys. There is a question in the chat box. The question is about cell type microstructure in optical, I think OIM and SCM. Will it relate any dislocation? Cell type microstructure in OIM and SCM, will it relate any dislocation?
Let me go to chat. No, it's not. OIM is not the dislocation structure. It's not. It's only a grain structure.
Okay, so Nadraj, hope you got the answer for your question. Yeah. So meanwhile, I have one question. So of course, so I would like to ask you about that grain refinement. You talked about grain refinement when you add titanium to the that binary system, right? Alloy. So this grain refinement, how it affects the mechanical behavior of the material?
It increases the strength in one line by using the classic Hall-Page strengthening mechanism.
I see. And this grain refinement, is there any, like, for example, in your case, you said grain size was something around 30 or 40 nanometer, right?
Micrometers.
Micrometer. Okay. So can that be changed by changing the amount of titanium or
maybe
the temperature?
Maybe, because we have not done anything on that. Maybe we should be able to change. And before that, if you see, by the addition of titanium also, we see the grain refinement, but the hardness remains the same. So when there is a grain refinement, you should expect more hardness. But the other problem is that titanium, which also went into solid solution, might be decreasing the strength because titanium is relatively softer compared to the other alloying elements. So the strength decrement that was was given by titanium is being compensated by the strength increment that is coming from the grain.
Okay, thank you.
Thank you. Thank you.
Yes, so there are no questions. Yes, okay, so if there are no questions, let's thank Professor Koteshwar Rao for his insightful talk. Thank you, Professor. Now we will move on to the last talk. Last talk is a contributory talk. Yeah, last talk is a contributory talk by Mrs. Jalluri Pushpavalli. Mrs. Jalluri Pushpavalli, can you
Good
hear
evening,
us?
sir. Yeah,
Yes.
yeah. Good evening, sir.
Yes.
Can you see the screen, sir?
Yes. You can put it in presentation mode and you can continue.
Now, could you see the slides?
Yes, yes.
Okay, sir. This is Pushpavalli. Good evening to all. This is Pushpavalli. I'm working in Rio's ISRO as a scientist. First of all, I want to thank organizing committee to give this opportunity to present my work in this esteemed conference and conducting in virtual mode in this pandemic situation. Today, I would like to talk about challenges in clad layer development and qualification for sintered silicon carbide materials for space optical applications. And I have organized my talk like this.
Yeah, sorry to interrupt. Can you put the slide in presentation mode?
One second. Is it okay now?
No.
Now, screen is changing. Screen is changing, sir?
Screen is changing, but I am telling you put the presentation in full screen mode.
1 second, sir.
It is not in full screen mode, presentation mode.
But I could see in presentation mode. So
okay, it's fine then. Yeah, go ahead.
Can I maximize the things and present?
No, it's fine. It's fine. Go ahead.
1 second, sir. Is it okay? Is it visible to you, sir?
Yes, yes. Your slide is visible, but anyway, so it's fine. You can go ahead. Yeah.
Yeah. And today I have organized my talk like this: introduction about telescope mirror materials, merits and demerits of existing materials, new evolution in silicon carbide mirror technology, clad layers developments, methods and materials used for these clad layers, and microstructural characterization using scanning electron microscope, EDAX, micro-Raman and nano indentation, functional properties, surface figure, surface micro roughness and spectral properties, space qualification test carried out on silicon carbide mirrors to use in space, and summary. So low thermal expansion materials we are using for telescope optics fabrication and development. Those are ultra low expansion glass ceramics, that is clear serum, porofloat glass, and supermax, zero there, beryllium, aluminum, and silicon carbide. These materials will have their own merits and demerits. Coming to the glasses, it is already reaching lightweighting limit, and it's a very fragile material. Low strength, it is having low strength, brittle in nature. Coming to the beryllium, it is very costly material and toxic, brittle in nature, and it will take so much of time to machining. Coming to the aluminum, it's very reactive material and chemically unstable and having high CTE. So silicon carbide is an appropriate choice for space optical applications because it is having good characteristics like extremely low coefficient of thermal expansion and high thermal conductivity, large operating, it can withstand in large operating temperature range, and extremely hard and high fracture toughness, excellent in chemical stability. And this is a radiation hardened material and it exhibits a high affinity for coatings. There are 4 varieties of silicon carbide materials based on fabrication route. One is reaction bonded silicon carbide, second one is sintered silicon carbide, second one is hot pressed silicon carbide, fourth one is chemical vapor deposition. So we have fabricated these mirrors using sintered silicon carbide, and it is in alpha phase exhibiting HCP structure, and it has porous in nature. It is in porous in nature and microstructural defects and grain boundary damages. So one cannot achieve optical surface using this material because of inherent limitations of this phase. That is, whatever we require for optical applications, it is around surface figure is around lambda by 6 to lambda by 8 PTV and lambda by 50 RMS, and micro roughness around 1 to 2 nanometers. For optical application, surface modification is must by incorporating of cap layer or CAD layer to the SiC substrate for better polishability and smoothness. People are already done silicon carbide coatings by chemical vapor deposition method at ARCA, and these are the limitations it is having this process. Like substrate should be heated at a high temperature, that is greater than 1000 degrees centigrade, and it may surface may contaminate due to this process, and it's very complex and time consuming process. Moreover, yield rate is very less. We have encountered certain problems like white patches, depletion layers, cracks, blowholes during grinding and polishing process. So we have developed alternative coatings for clad layers using new approaches and methods, and these coatings are available for space optical applications. Those are silicon coatings by thermal spray method, and second one is silicon dioxide by physical vapor deposition. First of all, sintered
Excuse
silicon
me.
substrates.
I think your slide is not changing. So we are still seeing slide number 3.
4 you could not see?
Yeah, now for slide 4 is visible.
Okay, sir. 5?
Yeah.
Yeah.
No, but what I am telling is, I think your slide is, we are not seeing the change in slide numbers. I mean, we are seeing only slide 2, 3, like that. Okay, please go ahead. So you are in slide 5 or 4?
5,
no.
Sir.
Okay. I think we missed out slide number 4, I guess. But for
this
me,
is
it
the
is not.
slide. This is the slide number 4, and these are the defects.
No, fine. You already explained. Please go ahead.
Okay, sir. So silicon carbide substrates we have taken, and these are fabricated using sintering process. Once it is done, we have conducted non-destructive testing on these substrates. Those are X-ray radiography, dye penetrant test, and micro Raman tests for inspection of void surface, cracks, delaminations, pits, inclusions, and residual stresses. Once it is passed this screening test, we have taken these samples for grinding and polishing process. And this we have done by conventional method using Speed's FAM machine. We have taken the samples of size 50 mm by 50 square samples and 50 mm diameter circular samples, and we have done ductile mode polishing using diamond and silica abrasives. And we have taken this substrates 50 mm diameter also with the thickness 6 mm. Silicon powder we have taken for this plasma spray coatings. So particle size distribution influences the microstructure of the coating. So we have measured particle size of this using scanning electron microscope. This is around 15 to 50 microns spherical in shape. Once it is done, these substrates is sandblasted to get roughness less than 1 mm, and subsequently these substrates and mirrors has cleaned with IPA. Silicon coatings has been done carried out using this atmospheric plasma technique, and the thickness is around 400 to 500 microns with a low plasmatron power 54 to 55 kilowatts. Once it is done, these substrates have been taken for grinding and polishing and achieved optical surface. Once it is achieved, we have done all optical characterization and microstructural characterization and nano indentation characterization we have done. This is the XRD spectrum we got. Using this, we can tell that we have seen silicon predominant peak at 2 theta is equal to 28 degrees, and there is no other peak, and it is in cubic structure having the D space 5.4 angstroms and as per ICDD standards, and there is no other peak. So that, and moreover carbon peak we could not see. Because of this way one can tell that it is free from substrate, and we have since we have deposited silicon of the thickness 200 to 300 microns, and silicon carbide. This is the micrograph of sintered silicon carbide, and this is the IDAX spectrum. After deposition with the silicon, this is the micrograph. This is in porous structure. These pores are filled by silicon, and this is polished. These samples has been polished, and after polishing, this is the micrograph we got using scanning electron microscope. Corresponding IDAX spectrum I have given here. And micro-Raman is also conducted on these samples in the range of wavelength range 0 to 3000 nanometers, and we could see this Raman peak of silicon at 521.4 nanometers, and there is no other peaks, so there is no contamination in these coatings. Once it is done, we have measured micro roughness on this polished silicon clad layer sintered silicon carbide mirrors, and we have using white light interferometry technique, and it is a proven method for optical applications. Using this, we could get roughness around 2.25 nanometers and RMS around 2.48 nanometers. These values are cross-checked with atomic force microscope, and those are well matching within the measurement of uncertainty. Coming to the surface figure, this is the heart of the experiment. We have done this surface figure measurements using phase shift interferometry, and whatever it is shown, this is the photograph of test setup for surface figure measurement. We have used Zygo interferometer, and this is the interferogram. And surface figure, we have achieved lambda by 4 to lambda by 8 PTV and lambda by 40 to lambda by 60 RMS, and 2D, 3D profiles, corresponding profiles for these samples. Spectral measurements also have been carried out using Perkin-Elmer UV visible spectrometer in the wavelength 200 to 2500 nanometers, and the average reflection we got 30.97%. And in the IR region 1000 to 27,000 nanometers, we have conducted this experiment and we have achieved the average reflection values 27.85%. And these results are published in Surface Engineering, and nano indentation also studies are also carried out on polished silicon surface using Berkovic indenter under controlled loading of 5 millinewtons to 50 millinewtons on polished surface, polished silicon surface. Nano hardness is around 10.43 plus or minus 0.8, and elastic modulus is 146.0. 16 plus or minus 3.5 GPa. And these are the pH plots, load versus depth plots. Coming to the silicon dioxide coatings on sintered silicon carbide, these coatings we have done by E-beam evaporation techniques, and substrate is heated at 200 degrees centigrade with the rate of deposition 4 angstrom per second at vacuum 5 into 10 to the power of minus 6 millibar, and we have coated around the thickness of 5000 angstrom using this E-beam evaporation. These are the optimal parameters for this technique, and these are the sample photographs. Substrate after coating, after polishing, and after high reflective coating. Once it is polished with colloidal silicon, we have achieved optical surface. So full level characterization we have done. Same the way we have evaluated surface figure and roughness using interferometry technique. Here also we have evaluated PTV and RMS at a different stage of fabrication and development of silicon dioxide clad layer coating on sintered silicon carbide mirrors, and these are drastically improved from 128 to PTV to 74.8. In case of roughness, RMS, if I'm taking RQ values, 212 angstroms to 9.11 angstroms, it's much improved after polishing these substrates. And this is the high reflective spectrum we have taken at different stage of fabrication, and after high reflective coatings we have achieved 92% average reflection in the visible region and 90% in the IR region. These are the plots we have got at a different stage of fabrication. And SEM analysis we have done. These are the micrographs of silicon dioxide coatings. So many pits are there on substrate before coating. These pits are filled with the silicon dioxide. Once it is polished, we got uniform structure. And after reflective coating, this is the microstructure we got. And the corresponding IDAX spectra I have given here. We have used aluminum coatings as a reflective coatings with the protective layers SaO2 and Nb2O5. The same elements we got in IDAX without any other peaks, so that it gives there is no contamination during this process. And nano indentation we have carried out using by applying 20 millinewtons. And we have measured and we got hardness around 3.5 to 5 GPa, and Young's modulus area is around 40 to 60 GPa. And this is the XRD spectra we have measured on polished silicon dioxide on sintered silicon carbide. So there is no other peak, only silicon carbide peak only it is there, peaks are there. And it is second, whatever it is showing in red, that is silicon dioxide. After polishing we have indicated with blue color, and greenish blue whatever we have given after a high reflective coatings we have represented with this dot and squares, whatever the elements we have got in this XRD experiment. Last but not the least, here I am showing flowchart for qualification tests. So once we fabricated the silicon carbide mirrors, we need to subject for a qualification tests to use in space. So we have taken 20 number samples of diameter 50 mm with the thickness around 5 to 6 mm. So for each and the environmental test we have conducted like thermal vacuum cycling, thermal shock cycling, humidity tests, thermal storage test we have carried out. For each test we have taken 5 samples, and we have done visual inspection and performance parameters before and after the test. Functional parameters like surface figure, surface roughness, reflection measurements we have carried out before and after the environmental test. And thermal vacuum test we have done at minus 55 to plus 60 degrees temperature during 2 hours duration, 10 to the minus 5 millibar pressure and we have done 10 cycles. Coming to the thermal shock cycling, same temperature it is applicable, that is minus 55 to 60 degrees temperature, but the dwell time is 5 minutes. We have conducted 1,500 cycles, that is equivalent to 5 to 6 years spacecraft lifetime. So we have simulated that kind of rigorous test and it is passed. Coming to the humidity test.
Pushpavalli, you have 2 minutes left.
Yeah, okay, thank you. I wanted to wind up. So humidity test, 95% RS and 50 degrees temperature we have subjected, and before and after we have seen functional parameters. It is passing all the tests. And just I wanted to summarize my talk like this. Silicon carbide is a promising material for space applications because of its excellent properties. 3 different clad layers are deposited on sintered silicon carbide with the different techniques and approaches. That is silicon carbide with chemical vapor deposition for aspheric mirror applications, and silicon coatings with thermal spray for spherical mirrors application, and silicon dioxide coatings with the PVD technique for flat mirror application. Optical studies, microstructural characterization, mechanical properties, and space worthiness tests have been studies extensively carried out on these coatings at different stage of fabrication. The proof of these concepts of these technologies are demonstrated on 200 diameter silicon carbide mirror successfully for space optical applications. And just I'm giving the references. These works have been published in certain reputed journals, that is Surface Engineering, Journal of Surface Engineering, and Journal of Ceramic International, and so many conferences. And just I want to thank Sri Venkateshwaran, Dr. Sriram, KV, and Rudraswamy and organizing committee.
Yeah,
thank you.
Thank you, Mrs. Pushpavalli. There are no questions in the chat box. Yeah, participants, do you have any questions? Well, okay, so since there are no questions, yeah, let's thank Mrs. Pushpavalli. So the next session will commence in few minutes.
Thank you for giving this opportunity, sir.
Yeah, you are welcome. So the next session will begin in another couple of minutes. We have keynote talk by Professor Nitin P. Patur from Brown University. So with this talk, so I'm concluding this session. I would like to thank all the speakers for their excellent presentation, and I thank everyone. I request all the participants to stay tuned for the next keynote talk in the same link.
Hi, Jaya.
Hi, Nitin. You can hear me, I hope. I'm actually at a place where the audio may not be very clear, but I hope you can.
Okay. So maybe I should just, let me just share my screen to make sure everything is working. Okay, can you see my screen?
Yes, yes.
It's advancing okay?
Things are moving, yes. All right, everything is good.
Good, all right.
Yeah, I'll start at 5 sharp, so a few minutes to go, I guess.
Yep.
Okay, so we are restarting the session for the keynote. Very good evening or morning to all of you, depending on which part of the world you're joining us from, for the International Conference on Advances in Materials and Manufacturing, ICAMM 2021. I'm very honored to welcome you all to the talk by the very distinguished scientist and professor, Nitin Paduture, as the last keynote lecture today. Nitin Paduture is the Otis C. Randall University professor in the School of Engineering at Brown University, where he leads the Advanced Ceramics and Nanomaterials Laboratory with research impacting energy, transportation, and information sectors that includes advanced structural ceramics and their coatings and composites, functional nanomaterials, and novel photovoltaics. His research and teaching interests are in the broad areas of synthesis or processing, characterization, and properties and performance of these materials. Previously, he was the College of Engineering Distinguished Professor at The Ohio State University. He has around 300 publications to his credit, which have been cited about 26,000 times, and he has presented over 250 invited keynote or plenary talks. Paduture is the editor of the journals Acta Materialia and Scripta Materialia. A fellow of the American Ceramic Society, Paduture has received his Roland B. Snow, Robert L. Kugel, and Richard M. Fulrath Awards, and he's also a fellow of the American Association for the Advancement of Science. And some of his other recognitions include the Young Investigator Award from the Office of Naval Research, the Presidential Faculty Award from Brown University, and the Distinguished Alumnus Award from his undergraduate alma mater, IIT Bombay. I was very fortunate to meet him at IIT Bombay a few years ago. My first introduction to his work was upon reading the phenomenal science paper on thermal barrier coatings, which is also his most cited work till date, during the beginning of my own PhD. So I discovered the great ability of his to connect to even a student audience with ease, both in his publications and talks, and have followed his work ever since. So without wasting further time, I request Professor Pallature to take the stage and deliver his keynote address. And I request the audience to type their questions in the chat box or question and answer Q&A, and we will take it up at the end of the presentation. Over to you, Professor Pallature.
Okay, okay, let me get my laser pointer. Okay, thank you so much, Jaya, for the kind introduction, and also thank you to the organizers for inviting me to give this talk. So I'm going to talk about photovoltaics, but also touch upon optoelectronic behavior and also mechanical behavior of photovoltaics, which is maybe of interest to this audience. So why we are working on photovoltaics is the global crisis of climate change, and this shows a plot of CO2 emission as a function of year, and this is where we are at. And if we continue doing what we're doing, then we will end up with a global warming of 3 to 5 degrees Celsius, which is really unacceptable. And this RCP is basically the greenhouse gas effect or representative concentration pathways. And if we were to follow the recommendations of COP26, we just concluded in Glasgow, then we have to aim for 1.5 degrees Celsius pre-industrial global warming, which will basically require the CO2 to be net zero or net negative in order to achieve this by 2100. And that is a huge challenge. And renewable energy is going to play a major role, or CO2-free renewable energy is going to play a major role in making this happen. So this is what the Earth's power capacity looks like. So on the left-hand side is, of course, finite. It will run out of eventually, but coal, petroleum, natural gas all produce CO2. Whereas this on the right-hand side are renewable resources, which do not produce CO2. And compared to the other sources, you can see that solar, which is this big circle, is somewhat limitless in terms of power capacity. So photovoltaics or solar cells have really taken off in the last few years, and this plots the cumulative installed PV capacity, power capacity in gigawatts for the world. And this is really going exponentially, and we'll hopefully exceed 1 terawatt by early next year, which is really a mind-boggling achievement over the short period of time of about 10 years. And if you look at the costs, and this is levelized cost of energy with new power plants, and you can see this is actually world average, and you can see coal has basically remained the same. Nuclear has gone up from 2009 to 2019. The combined gas cycle, natural gas is somewhat lower. This is onshore wind, this is solar PV. And you can see solar PV the cost of solar PV has plummeted to about $40 per megawatt hour. And the United States, so we basically say it's achieved grid parity, and the United States goal is to 2030 is $20 per megawatt hour. That is achievable. So, but also, we'd also need to keep in mind that this is the current mix of renewable and non-renewable, and also the energy use is also going up by 2050, let's say. And in order to achieve this, we have to reduce the overall consumption of energy and change the mix from renewable to non-renewable in order to achieve the COP26 goal of 1.5 degrees Celsius. And in order to do this, this report came out recently, basically says that we need to increase the current 1.8 terawatt to 14 terawatt solar power, and wind needs to increase by also order of magnitude from 0.8 terawatt to 8 terawatt installations. It's really a daunting task. So for all of this to happen, the cost of solar has to come down. And this is sort of a historical chart from 2010 from the Department of Energy. And it basically shows that in the beginning, it started out at about $70 per watt, but the costs have been plummeting. This is a log scale, and that was the goal in 2020, but this goal actually has been beaten. And the average cost of solar panels is about 0.3 or 30 cents per watt in 2020. But this is where we want to be. We want to be in next generation photovoltaic, which are going to be pennies per watt. And in order to do this, it has to satisfy certain conditions, and that is earth abundant, cheap materials. You have to have a small amount of materials, use thin films rather than wafers. Then also need to be cheap to make, room temperature solution processing. And also you cannot compromise on efficiency because a lot of the because solar cells take up a lot of real estate, and therefore high efficiency is very important. So this is the efficiency of solar photovoltaics. So silicon has been sort of steady over the years. And this is gallium arsenide, which is of course the most efficient, but also quite expensive. And these are thin film solar cells, cadmium telluride, 5 micron thin. And then you have SIGs. And these are all what are called emerging photovoltaics. This is dye-sensitized solar cells, organic. And this is where halide perovskites are. And you can see the rapid increase in the efficiency of halide perovskite solar cells, starting from 4% to about 25.5% record that is reported today. And so these halide perovskites actually satisfy all these new photo generation requirements. And that's what I just said. The earth abundant materials, they're cheap, so a small amount of material cheap, and also high efficiency now, right? And recently, all the pioneers in the perovskite solar photovoltaics have been honored with this prize. All right. Also, the new photovoltaics add some new functionality. So, for example, perovskite solar cells can be tuned, and therefore they can be used in what is called tandem. And so silicon absorbs certain part of the photovoltaic, so sun spectrum, but perovskite solar cells can be tuned to absorb the complementary part of the solar spectrum, and therefore you can actually increase the efficiency of silicon photovoltaics rather than competing with them. Also, these are thin film, lightweight materials, and therefore they can be made flexible. For example, and I'll speak to that later on in terms of their mechanical properties. Then they can also be made colorful and so on, and they are also damage tolerant, and they can be used in space applications. So many of you maybe come from the metallurgy background. So what is a perovskite? It's a family of crystal structures, and the general formula of 3D perovskites is AMX3. So A here is this central cation, and then you have M cation, and then you have the X anion. And so in halide perovskite semiconductors, the A cation can actually be a molecule, and that is a formamidinium, for example, or methylammonium, or cesium. So this hole here in this halide perovskite actually quite large, and therefore you need a large molecule in order to keep this, to make this material or this crystal structure stable. Then this M cation can be lead or tin, and the anion can be a halogen, can be iodine, bromine, or chlorine. So a prototypical perovskite that we study is called MaPbI3, and that is Ma is methylammonium, lead, triiodide, or we call it MaPi. Of course, there's hundreds of compositions if you make alloys, because there can be substitutional solid solutions. Also, so we have to consider the stability of this, and stability is really governed by, I don't want to go into the details here, but this is all controlled by what is called the Goldschmidt tolerance factor. And for example, for ideal cubic structure, T needs to be equal to 1. And then we have this octahedral factor. And these are some octahedral and Goldschmidt tolerance factor of some of the popular halide perovskites. But this is what I talked about, is this 3-dimensional. We can also have what are called low-dimensional perovskites. So we can have these layers, and we can have these ligands that are connecting these layers, and these are called low-dimensional perovskites, and there's different kinds. So there's literally thousands of different compounds and structures in this family of materials. So what is the most attractive part of this is that they have actually very good light absorbers. So this is the solar spectrum, and this is light absorption. This is log scale. So you can see silicon, which is the most popular solar cell material, actually is not a very good light absorber. Gallium arsenide was thought to be one of the best light absorbers, but this MaPbI3 or MaPi has been shown to be absorbing even better than gallium arsenide. So light absorption is very important for a solar cell material. And this is primarily controlled by the band structure. Again, I don't have time to go into the details of this. But for example, MaPbI3 has a direct band gap, but you can actually tailor this, tune this by alloying has a low exciton binding energy, and then has strong absorption and also very benign defects. All right, so how does a solar cell work? The solar cell works. So this is a cross-sectional TM image of the solar cell made in our labs. So light will get in, and we will promote electrons from the valence band to the conduction band, create a hole up and electron pair, and then the hole will go this way and electrons will go this way. Same thing happens in the interior of the material. And we have these what are called hole and electron and hole selective layers. So for example, this is called ETL or electron transport layer, and this is called HTL or hole transport layer. So what basically it does is it doesn't prevent holes from going this way, and this electrons cannot go this way. So it's like a one-way channel for holes and electrons, and that's why you can collect the charge. Otherwise, these will recombine and the charge will be lost. And there are several PBA architectures. Again, the mechanism is still being understood. So now what about processing? Now the processing is the most interesting part, and which is why these are very attractive, because they're potentially low cost processing at low melting point. They dissolve in organic solvents at room temperature to form solutions and on substrates. And then you can basically use what we call benches and beakers approach. And you can have continuous, uniform, smooth, thin films over large area, and therefore the cost can be potentially low. Typically, we use spin coating in the laboratory to make these solar cells, and you can see this have very nice polycrystalline structures. You have grains and grain boundaries, and so on. And these are typically about 500 nanometers thick, so it's enough thickness to absorb a lot of the solar radiation. But they have to be scaled up, because spin coating can work in the lab, but they have to be scaled up. And there's a lot of labs and also companies involved in manufacturing of these solar cells. And you can use different kinds of methods in order to make this scalably with all these different layers and so on. And it shows an example of what's called a roll-to-roll, right? So if you look at this history of the solar cells for the last 10 years or so, everybody was interested in increasing the efficiency, then the scalability. But now the focus has been on stability, because these materials are easy to make, but they're also easy to degrade. It sort of goes hand in hand. And so stability and reliability are really the two important hurdles. And this is where my research group is primarily focused on. So let's look at the grains. So for example, let's look at the microstructures. So as I said, these are polycrystalline materials with grains and grain boundaries quite well defined. And there's some recent work with the high resolution TM showing clean grain boundaries and nice microstructures. And the grain, actually, if you look at the triple junctions, they're near ideal dihedral angles. So they look like almost equilibrium structures. And if you look at these organic photovoltaics and dye-sensitized photovoltaics and others, they really don't care about grain boundaries and grains or microstructures. But in the perovskite solar cells, they become highly relevant, and that's why we're studying them. It also relates to my previous background in ceramics. So let's look at the microstructure and grain boundary. So here's a cartoon of a thin film. Grain size about less than the thickness about, as I said, is about 500 nanometers. So grain boundaries can lead to photocarrier recombination. They can also have scattering of photocarriers, blocking of photocarriers. And you can also get facile ion migration along these grain boundaries, and it can be not very desirable. And you can also get ingression of oxygen and moisture through the grain boundaries. And as I'll show, the mechanical properties of these grain boundaries are actually quite poor, because fractures are relatively easy along these brittle grain boundaries. But the grain boundaries can also play some positive roles. So for example, you can use them to passivate defects on the surfaces of the grains, which is quite advantageous. And you can also use the grain boundaries to functionalize them and create some functions that are normally not possible. And therefore, Wolfgang Pauli once said that God made the bulb, surfaces were invented by the devil. So something he did not say is that grain boundaries were created by Dr. Jekyll and Mr. Hyde. It's sort of a double-edged sword. You can have positive and negative aspects of grain boundaries. So why are grain boundaries so important? So this is actually done in a special TEM where you can actually allow moisture to go into the column. And what you will see is the degradation. So it's the degradation actually preferentially occurs along grain boundaries and less so along the surface. And that basically tells us that grain boundaries are more potent pathways for moisture and other environmental species to get in and degrade the material. And this is the work of my former postdoc, Hadas. So why don't we just grow the grains? And that's a good question. And if you coarsen these materials by simply heating them, then you can get larger grains. And this is really driven by topology and solid state diffusion, as a lot of you from material science know. But the problem is in these materials, the grain boundaries are grooved. These are natural grooves, as I showed you when the films form. And these grooves basically put a drag on the motion of grain boundaries, and you get what is called stagnation. So when the grain size becomes the same as for the thickness of the film, then you get stagnation. And you can, of course, heat it for a very long time, and you can get film degradation. And you can get film degradation. So that's why you cannot really grow these grains too big. And so in order to overcome the stagnation, you have to invent some new approaches in order to get around this problem. And one of the problems we have studied is what is called FAPBI3. So we talked about MAPBI3, but FAPBI3 is this structure here. This is the molecule that goes into this A site. And it is actually more stable than MA, and it shows degradation is actually less compared to MA. But the problem is also, by the way, it has a more ideal, more desirable band gap. But the problem is also exists on a different polymorph. It's a layered structure polymorph, which is called delta phase or yellow phase, which is not desirable because it's not a perovskite. And so but also the undesirable phase of the delta phase actually is relatively easy to make. And so we can actually make these films about 175 nanometer grain size, and the thickness is about 500 nanometers. But now when you anneal this in nitrogen, then you see that there is no phase transformation and the grain size hardly changes even after several hours. But we're going to take advantage of this polymorphism in order to increase the grain size. And in order to do this, you have to use the help of a vapor. And this is DMSO is a polar solvent, organic solvent. It's a very simple experiment. So here's the film on something like this. You put a droplet of DMSO and have a petri dish, cover it upside down and heat treat at about 100 degrees Celsius. And within 3 minutes, you actually start to nucleate this black phase. And this is actually single crystal. It looks like a mottled surface here, but single crystal. The EBSD pattern shows that they're actually single crystal. And within 15 minutes or so, the black phase has grown and it has eaten up the yellow phase and give rise to very large grains. And this shows the increase in the grain size here. And what's basically happening is that this vapor phase is actually facilitating the reconstructive phase transformation from delta to alpha. And this is something that would happen. So it would nucleate, the alpha phase would nucleate, it would grow at the expense of the yellow phase, which is not desirable, to give you very large grains. And therefore, controlling the nucleation rate is very important. And this is, by the way, the work of my former PhD student, Srinivas Yadavalli. So the control of nucleation rate is very important. So for example, at 95 degrees Celsius, you can see the nucleation rate is very low, and therefore you can get very large grains. Whereas at 115 degrees, you can get high nucleation rate and the grain size is very low, very high. Sorry, the grain size is very small. So there's an inverse correlation between nuclei density and grain size, and this is something we want here, right? And so that was the hypothesis. But to check this hypothesis, we use different solvents. So for example, DMF and NMP are also different solvents, but they have lower polarity index than DMSO, and they're less effective, as shown here using the Johnson-Malabrami analysis. And so we can draw this free energy diagram saying that at 100 degrees or so, the delta alpha phase is more stable, but there's activation barriers. So this activation barrier in nitrogen is unsurmountable. Whereas when you add this vapor, then the activation barrier decreases in the order of the polarity index, right? And that's what basically we can do. Now let's look at the stability of these. And so for example, if you have very large grain size, 7.6 micron in a 500 nanometer thin film, so it's really large grain size, the efficiency is actually quite high of the solar cells made from this. and they don't degrade as much after this relative humidity of 70%, 40 hours. But if you have fine grained material, the efficiency is lower and also degrades quite rapidly. And you can see the effect of grain size here, or the grain boundary density on the degradation. I should also say that these materials are processed at very low temperatures, and therefore you can actually functionalize the grain boundaries with molecules and polymers. So you cannot really do this in metals and ceramics. When we're processing something at 1,000, 1,500, 2,000 degrees C, a lot of these things would simply burn. But here we have the luxury of actually functionalizing grain boundaries because the processing temperature is so low. For example, here's an example from my lab showing calcium fluoride at the grain boundary, or you can put silica through putting TiOS in the precursor, or you can put polymer at the grain boundaries, which has certain function, or you can put molecules at the grain boundaries, and so on. All right, so let's talk about mechanical properties, mechanical reliability, because that's sort of the last hurdle in the commercialization of these solar cells. So these are multiple layers. At least you have to have the electrode, you have the ETL, the perovskite, the HTL, and the metal electrode, and the substrate. So there are multiple layers. They have different thermal expansion coefficients and different mechanical properties, and therefore it's very difficult. So they will basically contract and expand. And then if you have a tandem solar cells, then you have even more layers. So this is the perovskite solar cell, say, on top of the silicon solar cell, and therefore the mechanical stresses that are generated because of thermal expansion mismatch is very important. That's what I said. And also during service, so these solar cells have to be tested from minus 40 degrees to 85 degrees C, and therefore the thermal excursions can also generate residual, can also generate stresses. And then when you have flexible solar cells, then you have on top of this, you have an added applied mechanical stresses from bending, twisting, stretching, and so on. And this becomes even more important because all these materials have very poor mechanical properties, especially the perovskite. So the MAPBi3 perovskite has a Young's modulus of about 18, hardness of about 0.6. And if you look at the toughness here, K1C is only 0.2, GC is about 3. And the interfacial toughness here between the boundary, between the material and the ETL actually is quite low as well. So you can get damage and stress accumulation and interfacial fracture, performance degradation as the material is being made and handled and also used. Right? So this becomes very important. So a lot of the material scientists, of course, are familiar with Ashby maps. I'm plotting this two properties, fracture toughness, K1C, and Young's modulus. So here are the usual suspects, the metals and alloys, polymers, and here you have the technical ceramics and foams and so on. Here are glasses, here's silicon. And this MAPBi3 sits over here. So it's in this white space. So it has a very unusual combination of mechanical property that we're not used to. So it has low Young's modulus and also low fracture toughness. Or I should say that the mechanical properties of these materials have not been adequately characterized. And just to give you an example here, so we've been working on directly measuring the mechanical properties of these crystals. So this is MAPB-BR3, so instead of I3, you can make good crystals here. And we have measured this directly in compression and measure a Young's modulus of about 13 GPa for this particular material. But most of the results actually in the literature are based on nano indentation. But these materials actually creep like crazy. And therefore, for example, depending on the dwell time, you can get a Young's modulus anywhere from 23 gigapascals down to 5 gigapascals. And this is the direct measurements here. That is the sort of the representative value, right? So you have to be very careful about these, excuse me, measurements. Anyway, so let's compare the mechanical properties of MAPBi3. So this is the Young's modulus compared to glass, silicon, sodium chloride, and so on. It's even softer than sodium, or even more compliant than sodium chloride. This is hardness values, and these are toughness values. Again, as I said, they're quite brittle, and they also have very high thermal expansion coefficient, almost 50 times 10 to the power minus 6. All right, so just wanted to say something more editorial. So if you look at the research progression of all commercial devices, including photovoltaics, like computer chips and all sorts of devices, capacitors, and so on, now a lot of people are interested in efficiency first, then scalability next, and then have to be stable. But at the end, all of these things have to be reliable in order to survive in a commercial application. And therefore, this is sort of the final hurdle, this reliability, and perhaps could be the next frontier in this perovskite research. So now let's look at the solar cell like this. And now if we, as I mentioned, these materials are relatively brittle. So if I bend this, it will crack like this, right? But the cracks by themselves actually reduce the area by like only 1%. Also, if it cracks afterwards, there's no shorting or anything like that. But you have to bear in mind that when a crack appears like this vertical crack appears, it provides a free surface for propagation of a more dangerous interfacial crack. And interfacial cracks will kill the device. So interfacial cracks really originate from edges, right? But the cell is quite big, and therefore there are few edges. But if you have vertical cracks, and you're creating new edges inside the material, and that can be dangerous. So we need to worry about cracking of these materials, of these perovskite. This is an example that shows this. Anyway, so we studied the cracking and healing of these materials. So for example, this is a MAPBI3 perovskite on a polymer substrate. And this is made at 100 degrees Celsius. So the residual stress we calculated about 52 megapascals. And we measure about 45 using the sine square psi method. And it's in plane equibiaxial stress. And so that's what I plotted. So this is actually a range here. Typically you find a range, right? And now what we do is we bend it on a mandrel to have a constant radius of curvature, and we can calculate the tensile stress in the film. Due to bending, it's about 153 megapascals. And this is sufficient to actually crack the material because this material is relatively brittle, right? And as soon as you crack it, you can see the cracks. The residual stress is relaxed and goes down to about 8 or nothing, right? Now, when you take the same film, cracked film, and you bend it backwards in compression and get equal and opposite compression, 153 megapascals, and what happens is that the residual stress is restored, and we can actually see that this cracks have healed. And so this is just mechanical healing at room temperature only for 30 seconds. Just bend it up opposite way 30 seconds, and you're restoring the mechanical residual stress. If you thermally annihilate without bending it, compressive bending, then it also heals. And that is thermal healing, right? So you can have this restoration, which basically is a true indication of crack healing by just moderate compression or heating. And this is the work of my former PhD student, Srinivas Yadavalli. We studied this as a function of time, and you can see that it's time dependent. This is mechanical healing, and this is thermal healing. So it's a time-dependent, stress-induced, thermally activated phenomena, and it can be attributed to ion migration, which is very easy in these halides, which gives rise to this healing of the cracks. Right? That's a general effect. In the FAPBI3, a different kind of perovskite, we see the same thing. You crack it, and you mechanically heal it, or thermally heal it, and the cracks are healed. So basically what we can say is that what is good in these materials is that it can be made solution processing, but the bad thing is they can break easily, but then you can also heal them easily. So this is all part of this story of these interesting materials. All right, so now instead of looking at the cracking of these materials in bending, let's say, now another important aspect is delamination. So when I pull these solar cells apart, delamination can occur and fracture here. And this can happen intergranularly along the thin film. And so we use the sandwich geometry here. This is the sandwich geometry, about 4 centimeter long sample, sandwich between glass plates. You have to use epoxy and things like that. And then we pull on this, and we use the compliance method here. And we can actually calculate what the crack size is, because it's very difficult to measure the crack size. And then the peak load PC we use to determine the toughness, or GC, of these interlayers, right? So if you look at the fracture surface after fracturing this the sandwich, on this side you see perovskite grains, intergranular fracture, and it's black because perovskites are black; they absorb light. And if you look at the other mating surface, it also has perovskite grains and intergranularly fractured. It's also black, right? And if you measure the toughness, it's about 0.4 joules per meter square, which is really very, very low, right? So as you can see, the grain boundaries are very weak in these materials. Now, when you increase the grain size, so the grain size is larger than the then the thickness of the film. So you have these vertical grain boundaries. Then what happens is that the fracture occurs at the interface here, right? Because there's no grain boundaries to fracture. So the next weakest layer is the interface. And again, looks black on this side because of perovskite. And on the other side, you have some little grains stuck to the substrate, but this is clear, which is basically there's no perovskite, hardly any perovskite here, which means that it is happening at the interface. And the toughness, adhesion toughness, has gone up from 1.4 to 1.14. So we have increased the toughness by almost a factor of 3 by going from a fine grain material to a coarse grain material, shifting the intergranular fracture to interfacial fracture. Right, so it's another advantage of coarse grain thin films. And this is the work of my PhD student, John Dye. But we need to increase this even further. We need to go to, say, single crystal values, and that's about 3 joules per meter square, right? In order to, so we need to toughen this interface, right? So that the failure can occur within the single crystal and reach this limit, right? And so John did a lot of this work, and we use this mixed halide perovskite composition. Again, I don't want to go into the details, but this is a more stable perovskite composition and also a good combination of efficiency. And we have used self-assembled monolayers at the interface. And this is a silane-based self-assembled monolayer, and it's terminated in iodine. So what happens is that tin oxide, for example, this is the tin oxide surface, which is the ETL or electron transport layer, always has hydroxyl groups, right? And so if you add this self-assembled monolayer, which is silane and terminated with iodine, you get this reaction and you get cross-linking and attachment. And this is a very strong attachment, as many of you know, with self-assembled monolayers. But now the terminal group is iodine. Now, when the perovskite is deposited on top, it is expected to bond very strongly to iodine compared to the OH group. And therefore, we can toughen the interface, and we keep this very short so that we don't affect, or in fact, we enhance the optoelectronic properties of this interface, right? And of course, we have done control studies where the terminal group is replaced, I is replaced with hydrogen. So there's no bonding between or little bonding between hydrogen and the perovskite, and a different halogen, such as bromine, right? And this is work just came out in Science magazine recently. So this is SEM images of the perovskite films and the XRD. So the SAMS is underneath, and the SAMS basically does not affect the microstructure or the phase. I just want to show you that. That's what basically purpose of this slide is. And now we measure the interfacial toughness using the same method. And if you look at the fracture surface, you see again perovskite grains from the bottom. And on the other side, it's relatively clear with few perovskite grains stuck. And you have increased the toughness by about 50% over no SAMS in this particular composition to ISAMS, and we're approaching the single crystal value of the perovskite. And we've done DFT calculations to understand what is going on in here. So this is the SAMS, and this SAMS is terminated with iodine. This is the perovskite, and the perovskite has lead and iodine. So what happens is that you can actually get bonding between the undercoordinated lead in the perovskite and the iodine from the SAMS. So the iodine termination group is very important. In addition, we get hydrogen, what's called halogen bonding between the iodine in the perovskite and the iodine in the SAMS. And the iodine actually bonding and halogen bonding is the strongest, bromine being the next strongest, chlorine and then fluorine being the least strongest, right? And therefore, you can actually see that bromine actually is lower, and then hydrogen is even lower when there is iodine is replaced by hydrogen, right? Now let's look at the photovoltaic performance. So these are the solar cells, and they basically look about the same because the SAMS is a molecular layer at the interface, called this molecular glue. Now, this is what the photovoltaic performance looks like. So here we plot current density and voltage, and many of you may not be familiar with seeing these. And this is all the values here. So what is called VOC, or open circuit voltage. So open circuit voltage is here. So you want the open circuit voltage to be as high as possible, but it's really controlled by the band gap. This is called the short circuit current, and the short circuit current also you want high as possible, but there's always a trade-off. If you increase VOC, or if you increase the band gap, then less light is absorbed, because only the light that is energy higher than the band gap will be absorbed. So it's like a seesaw, right? And then this is the fill factor, or this is the maximum power point, and this is the fill factor. So you basically want this to be as high as possible, this to be as high as possible, and the curves to be as square as possible in order to get high efficiency. Anyway, so this is the efficiency, and we are reaching about 21% in the SAMs. So by adding SAMs, are we not only increasing the toughness, but also increasing the performance of these materials, of these solar cells. And this is a hypothesis of why this is happening. And this is some statistics. Of course, we have normally do many different cells, and what it shows is that the performance is primarily attributed to the VOC, increase in VOC because of the interfacial good contact interface. Now let's look at operational stability. So we basically let these solar cells run at maximum power point for at one sun, unencapsulated room temperature, and we monitor the performance. And if you look at the hydrogen or no SAMs, then the life is about 700 hours, and T80, which is loss of 20% of life, remaining 80% life. And these are about 4,000, which is really unprecedented in these solar cells at this time. Anyway, so what we've done here is that improved efficiency, stability, and also the reliability. Now, what we do is actually take the solar cells that have been tested and try, in order to understand, to learn what's going on, we do postmortem characterization. With no SAMs, what you see is that you have voids at these interfaces, you have delamination and large voids. And if you look at the fracture surface, they're reflected in the voids and the delamination here. With just hydrogen SAMs, you don't see the voids, but delaminations. The hydrogen SAMs, you got rid of the OH molecules because of the SAMs, but the toughening was not there. And therefore, this is a relatively weak interface, and therefore it damages after continuous running of the solar cell. But the iodine SAMs looks like almost pristine. It hardly shows any damage at the interface. It's some damage on the fracture surface. So combination of this iodine and elimination of hydroxyl group basically gives you these interesting properties, right? And so we sort of established this connection between stability and reliability of these solar cells. Again, this is the work of John Dye. Now, what's next? So the next thing is that we have toughened this interface, but now the fracture will move to the next toughest interface, and maybe into the perovskite and into the HDL and so on, like the link, the weakest link in a chain, right? So the next thing we've done here is to actually toughen the perovskite or pseudo toughen the perovskite itself, right? And the way to do this is actually done in flexible solar cells. And so as I said, we toughen the perovskite, and the way to do this is we have used a in situ grown low dimensional perovskite on the surface. Again, I don't have time to go into the reasons to do this, but not only does it seal the cracks that can open up and like a adhesive, but this also gives us very good optoelectronic properties for this interface. So the photocarriers can be easily extracted. And so this not only, I guess, see that it improves the efficiency, but I'll show you that it also increases the stability. So stability is very good of this layered structure. And then flexible solar cells, of course, what is important is the bending fatigue. And we built a device that does this bending fatigue test. And you measure the performance of the solar cell after a number of cycles. And you can see this is up to 20,000 cycles, and this one without the adhesive layer obviously drops off much faster than the one with the adhesive layer, right? And so we've enhanced efficiency, stability, and reliability. Again, there's a lot of science, underlying science that goes into it, and if you're interested, you can look at this paper that has been published recently. All right, so I think I'm out of time here and leave some time for questions. So I would like to thank my contributing group members, and that is John Dye, who's a current PhD student, a staff member, Hector Garces, Srinivas Yadavalli, who's now a postdoc, Min Chen is a postdoc. By the way, he did the work on those flexible solar cells, and now he's at NREL, former PhD student, now is assistant professor, Hadash Sternlake, Christina Ramirez, And these are the collaborators, one at Brown University and other places. And a lot of the work was funded by the National Science Foundation, Office of Naval Research, and Department of Energy. With that, I really thank you for your attention, and I'm happy to answer any questions.
Thank you, Professor, for today. It was a wonderful talk covering various aspects of the perovskite solar cells. I request the audience members to type any questions they have, either in the Q&A or in the chat box, and I can read it out. Maybe by the time some questions come in, I have a few questions of my own.
Yes.
So there was this work that you showed of initial delamination or fracture test or interface toughness test.
Yes.
And can you hear me? Sorry,
you're
my
breaking
connection
up.
seems unstable.
You're breaking up.
So the double cantilever, maybe I'll type my questions too. Can you hear me now?
Yes, but you're breaking up.
Okay, I'll type.
Yeah, there is a question from Dr. Ishwar Prasad. Does the fatigue loading has any effect on the performance of solar cell? Did you unload intermittently and check?
Yeah, so the way that we do the fatigue test is that we cycle for a number of cycles and then stop the test and then measure the performance of the solar cell with the 4 parameters, and then put the solar cell back in the same place. We have a fixture that aligns it exactly the same way, and then continue the fatigue test. I don't know if that answers your questions. So we did unload intermittently. And so that plot that I showed here, so this plot that I'm showing here, so this is all these is measured intermittently for the solar cell efficiency. PCE is power conversion efficiency. Okay, Jaya has a question, right? Yeah. So what is the thickness of the film in case of adhesive failure? Does the crack not deflect into the MHP layer again? Did you try any textured film in place of single crystals? Okay, so the film thickness is about 500 to 600 nanometers. In case of it, does it crack not deflect into the MHP layers? So we looked at the entire surface, and it's actually quite easy to pick out because perovskite is dark, and actually you can pick it out in an optical microscope. So you see some undulations, but it's primarily at the interface. It's mostly clear, but some grains, because the grain size, when I say show vertical grain boundaries, not all of them are like that. Sometimes you have tiny grains which get stuck, and the grain boundaries are relatively weak, and they get left behind on the tin oxide interface. Did you try any textured films in place of single? So these are not single crystals. These are all grain, and these are all polycrystalline materials. So let me just go back to that slide, maybe.
Right. I meant you said that if it was single crystalline, it would be better. So of course we cannot make it single crystalline, but is it possible to make them textured? Are they even anisotropy in that sense?
Right. So typically they are all textured because there is a preferred. Okay, let me just see if I can get out of this. So they're all typically textured because there's one when you get grain growth, the one orientation is preferred. So they're typically all textured. I don't know if that answers your question. But what happens, what I'm saying is that there are some tiny grains also, like this is idealized vertical grain boundaries where the entire grain is the thickness of the film. But sometimes you can get tiny grains here and so the grain boundary there is weak, and therefore you can see these little grains stuck on the other side.
Right. Maybe one more question I had was the mechanism of crack healing. It was wonderful to see sort of got back on its feet, but
right. So basically this is the hypothesis, and that's why we did the time-dependent studies. So diffusion in these materials at room temperature is very easy compared to metals and ceramics we used to. Okay? Because ions sort of move around, and it's actually a problem in solar cells because ions can actually migrate during the operation of the solar cells. Fortunately, the sunlight doesn't shine at night, and therefore it can actually equilibrate when it's resting. But ion migration is very easy. So when you have a crack, and when you put the crack together, and when you apply pressure, you can get ion migration of really all the species, which is what gives you the healing. And this can be, as you know, in ceramics, people have done this, but only in ceramics that the stress, for example, is not enough because the diffusion coefficients are so low. You have to heat it to very high temperatures in order for this to occur. But in these materials, this happens at relatively low temperatures, and with pressure, it happens at room temperature. So it's really the easy ion migration that occurs in these halide crystals and materials is what's responsible.
Yeah, that was very interesting to see. Jaideep Malik has a question. So you showed some RP phases or layered perovskites. Are these layered or MAPI perovskites?
So these are not MAPBI3, these are layered perovskites. And the layered perovskites are basically, let me just show you, go back to this. So this would be MAPBI3 here. So that is a 3D perovskite. So this would be MA and PBI3. The layered perovskite, you can have N equal to 1. So there's actually no MA or FA here. It will be just the lead iodide, for example, or bromide, in this case, mixed. And N equal to 2, you'll have 2 layers, and this would be MA or FA or cesium, for example. And then you have these ligands that bond this. So it's basically similar to Van der Waals crystals, and that's why we call them low dimensional. This particular is Redelson Popper, and this basically, when it's aligned, it's Dion Jacobson. So in the layer perovskite that we have used, the N is approximately equal to 3, N is approximately equal to between 1 and 2. And the bonding we use is called a CBA molecule, and that CBA molecule provides that ligand. And with excess PBI2, and we just reacted with CBA, and that forms these perovskite. But it's primarily N equal to 1, can be some N equal to 2 with some FA inside, but it's mostly N equal to 1.
He's continuing with the follow-up. Which one is better, 3D or layered?
Right. So I would say that for something like this, 2D is better because when you're bending something, then you need the mechanical property to be anisotropic mechanical property to be good mechanical property like the in this direction. So for example, if you grow 3D, then it never grows perfectly. You'll grow in all different directions and you'll get a messy layer. So something like this cannot be achieved in 3D. It'll just basically just grow randomly. And so if you want to control a layer like this, which basically goes inside the nooks and crannies of the grooves and seals these cracks, then it's best to grow a 2D, and it's also strong in the direction that we need it in, right? And so that's the idea. Also, the second part I didn't explain is that 2D perovskites are very good for optoelectronic or photocarrier transmission and passivation of these defects at this interface. So you want to kill 2 birds in a stone, is to increase the mechanical integrity, but also improve the charge carrier properties of the interface. And that's why we get improvement in solar cell efficiency also. As mechanics people, we know that there's lots of different kinds of glue. You can just use Gorilla Glue or super glue to glue things and they will never break. But the device will be dead, of course, right? Because you cannot transfer photocarriers across.
Right. Yeah, maybe another question I had was again on fracture toughness. When you mentioned vertical cracks versus the cracks which maybe are parallel to the interface.
Yes.
You mentioned that the perovskite material itself has a lower fracture toughness than the interface. So in that case, are you comparing the vertical cracking direction or the direction like in terms of cohesive failure of the layer? Like the in-plane toughness or the vertical toughness, and are they different?
Okay, so you're talking about as I mentioned, these are relatively large grain materials, and so a vertical crack most likely would be along the grain boundary, because even if you make the grain size large, the grain boundaries will be vertical, right?
Right.
And so I would say that the vertical cracks are primarily along grain boundary, but there are exceptions. For example, FAPBI3, we saw that actually breaks in transgranularly. And this is the interfacial fracture at the interface. So what we have seen so far is that the interfacial fracture toughness is lower than the fracture toughness of the perovskite itself. Correct?
Lower, is it? Okay, sorry, I think I got it.
Yeah, it's basically, so that's what, so this is the interface we have looked at so far. So this shows, so that's the grain boundary toughness, this is the interfacial toughness, and this is single crystal is about 3. Okay. So if you were to fracture it along here, then it'll be about 3.
Right, okay, got it. Yeah, I guess there are no more questions from the audience. So I would like to thank, on behalf of the organizers, Professor Nitin Padutare for sparing his time and joining us and sharing all the wonderful work that he's been doing most recently on the perovskite solar cells. Thank you, sir, for coming over really early in the morning for you. And yeah, I think we can, sorry, if you had to say something.
Yeah, thank you. Thank you so much for the kind invitation. Yes, Kiran, go ahead.
Thank you so much. Yeah, Professor Jaya, thank you very much for chairing the session. It's really very good. Thank you so much. See you.
Yeah, thank you, and we'll hopefully meet in person soon.
Sure. Yeah. So participants, tomorrow we have there is third day of the conference. Evening 5:50 validatory section starts. Professor Director IIT Indore, Professor Nilesh Kumar Jain is coming as chief guest, and Professor Tata Narsingh Rao, ARC International Director, is coming as special guest. There will be Best Poster Awards, Best Presentation, Oral Presentation Awards, and Research Excellence Awards. So I request all the participants, registered participants and members to attend the valedictory function. And also, from again, four more keynote talks are there tomorrow. I request members to attend to them. So today, with this, we are ending the session. Thank you, one and all. Hi, Chandramohan.
Hi, Kiran.
Oh, thanks for.
Yeah, it's our pleasure.
Yeah, thank you so much for sharing session.
Tomorrow what time?
Is last day. Huh?
Tomorrow?
Yeah. Tomorrow 9 o'clock again it starts. Ishwar garu.
Kiran, see, this is regarding this poster session, no? So can we go the link at the link and so that students are available at the time?
Yes.
The poster session. We given the link, no?
No. Yes.
6:15 to 7:30. So can we go there right now?
Yes. People are available. We asked them to be available on the time. So reviewers can go there, and people will be available actually.
From now we can go and judge. No? Now we can go and judge.
400 to 900 posters, we can evaluate.
Yeah, sure. Because Rajesh also checked with me. I told actually, okay, this time they're going to be available. I will go and check it.
Yeah. Up to 7:30 today, there will be a poster session. I asked people to be available on the Gmeet links. So yeah, thank you.
Thank you very much. Thanks.